In this course, you will learn the foundational principles of DevOps, understand its life cycle, and discover the benefits it offers. You will explore how DevOps integrates with containers and microservices, synergizes with agile methodologies, and optimizes software delivery within the cloud architectures. Let's look at the learning objectives. So, in this course, we will describe DevOps, review the principles of DevOps, explain the DevOps lifecycle, explore the pillars of DevOps, list the benefits of DevOps, describe DevOps containers and microservices, differentiate between DevOps and Agile, and finally, review the integration of DevOps practices with cloud architecture. DevOps Introduction. DevOps is a collaborative approach that merges software development or dev and IT operations or ops. It aims to streamline the software delivery process, promote shared accountability, and enable faster and more frequent releases of high quality software. DevOps emphasizes automation, continuous integration and delivery, which is CI/CD, and a cultural shift towards increased collaboration between development and operations teams. Let's continue on the DevOps. So, DevOps is a mindset. It is just more than tools. DevOps embodies a focus on continuous improvement and customer centric development. So, there is efficiency that drives rapid releases. The goal is to streamline software delivery, therefore, allowing for frequent updates and the creation of a minimum viable product or MVP to get early feedback. Then there is incremental development for continuous evolution. Instead of large, infrequent releases, DevOps encourages an iterative approach. Small feature additions are made regularly, therefore, gathering feedback along the way to guide the product's evolution. Principles of DevOps. So, there are certain principles of DevOps. So, we are going to just look at these. First, we are going to just talk about what these principles are, and then on the subsequent slides, we are going to look at each one of these in detail. So, the first one is collaboration, which is breaking down silos between development and operations. Then comes the automation, which is streamlining processes for speed and efficiency. Then there is continuous integration and continuous delivery, which is more commonly known as CI/CD. It is about frequent code changes and deployment for rapid updates. Then there is continuous monitoring, which is proactive performance tracking and issue identification. Let's move to the next slide to look at some more principles. So, in continuation from the previous slide, so now we are going to look at some more principles of DevOps. So, the next one is infrastructure as code, which is also known as IAC, and it is used for managing infrastructure through versionable code, which means you drive the infrastructure using a version based code. Then there is customer centricity, which is about prioritizing feedback and user needs. Then there is shared responsibility, which is about ownership across the entire software lifecycle. Then there is continuous improvement, which is about embracing a culture of experimentation and learning. Now we've looked at all these principles, so let's move ahead and look at each one of these in detail. So let's start with collaboration. Now, DevOps isn't just about tools, it is all about collaboration. Remember that DevOps is a combination of development and operations disciplines. That combination was created because it is more efficient for those teams to work as one of their own entities. But it doesn't stop there. DevOps teams are more efficient when they work in collaboration with other teams, particularly stakeholders like sales and project managers, customers, and so on. In fact, if you talk to DevOps purists, you will find that the real key to DevOps is communication. That's it. It is the process, collaboration, and efficiency that are all important, but none of it will work without good communication. And DevOps is all about communication and collaboration. So when you talk about collaboration, so that is the foundation of DevOps. It emphasizes the merging of development, which is the dev team, and the operation, which is the ops team, to foster better communication, shared goals, and a reduction in bottlenecks. Then there are cross functional teams, which we have talked about, something like stakeholders, sales, project managers. Now, this encourages knowledge sharing and skill development, therefore, breaking down traditional barriers and enhancing overall efficiency. So, we previously talked about getting other teams involved, particularly the stakeholders, sales, project managers, customers. So, this is the cross functional team. So, there could be your dev teams, there could be your IT teams. So, everybody gets together and works as a collaborated effort. Let's now talk about automation. So there is efficiency booster. Now automation helps you automate the repetitive tasks across testing, deployment, and infrastructure management, therefore freeing up teams for higher value activities. Think about this. Now, if you have to perform a repetitive test, why not just automate it? If you have to deploy an application repeatedly and or deploy its versions repeatedly, then why not automate it? So it will bring more efficiency. Then obviously, if it is automated, then it will reduce errors. It will minimize the potential for human errors, therefore leading to improved consistency and faster delivery. Now, this is the reason if you automate it, everything is happening in the same manner. So if there is an error at one particular place, all deployments or integrations will face that error, and that you will be able to track in the first attempt itself. Once you correct that, all the subsequent deployments or integration will happen in the same way. All the testing will happen in the same way. So therefore, there are no reason that you will have more errors than the manual ones. So therefore, automation will reduce errors. Then there are tools. You can utilize various automation tools spanning the development and operation spectrum. You can have different tools that are available in Google Cloud Platform or GCP. We'll be talking about some of these tools later on in the course, and you will see that these tools span across different domains of software development. So there will be tools in the testing, there will be tools in deployment, integration, delivery. So the entire life cycle of continuous integration and delivery or deployment can be automated. So we'll be talking about these tools later in the course. Let's now talk about continuous integration and continuous delivery. So continuous integration is something where developers merge their code changes frequently, which is typically more often or multiple times a day, into a shared and central repository. So it is not that the developer will sit down and write some code, but once a week that code integration is happening. There are more frequent updates onto that code into the central repository. Each code merge triggers an automated build and testing suite. So when the code is merged, there is an automated build that gets generated and testing is initiated. Now, the goal of continuous integration is to catch integration issues as early as possible. If a code change breaks the build or fails test, developers are notified immediately, therefore allowing for quick fixes while changes are fresh in their minds. Now, this also promotes collaboration. The shared repository encourages frequent code sharing, improving visibility and fostering a team mentality. Then there is continuous delivery or CD. Now, CD also stands for continuous deployment. So, we'll be talking about that as well later in the course. Now, CD extends or continuous delivery extends CI or continuous integration by ensuring that new code changes are not only built and tested, but also automatically prepared for deployment into environments like testing, staging, or production. Now, continuous delivery can be automated all the way to production, which is continuous deployment, or include a manual approval step before release is deployed. The choice depends on the organization's risk tolerance. So it depends whether the organization wants to release the final build through manual approval process or automate that process as continuous deployment. So there are certain goals for continuous delivery. So there are faster release cycles. Automation removes bottlenecks, therefore letting changes flow quickly to end users. There are reliable deployments. So there are consistent deployment processes that reduce errors and stress. Then, with continuous delivery, you get rapid feedback. New features reach customers faster, therefore allowing teams to gather feedback and iterate quickly. Now, let's talk about the CI/CD typical workflow. So on the screen, you would see that workflow is shown. So there is developer that commits the code. Developer pushes changes to the shared repository. Then there is CI triggers automated build and test. Now there is a CI system that will run a predefined test suite, which could include unit tests, integration tests, and so on. Then there is fast feedback. Now, if the test fails, developer fixes the issues. If the test is successful, a deployable artifact is created. Then there is CD deploys to environment. Now, based on the pipeline configuration, the artifact is automatically deployed to a staging or testing environment. Further testing, which could be manual or automated, may take place. So it depends how you have configured your CI/CD pipeline. Then there is release to production, which could be manual or automatic. A final decision leads to the release being deployed to a live environment. Now, having talked about CI/CD and the process it typically works in, what are the key takeaways? So, the takeaway is that CI/CD transforms software delivery from a risky, infrequent event into smaller, continuous process. This leads to higher quality software, faster innovation, and a more responsive user experience. Let's now talk about continuous monitoring. So there are certain features of continuous monitoring. So first one is proactive. Now this is a shift from reactive to proactive. Traditionally, monitoring often focused on reacting to alert triggers after a failure. Continuous monitoring shifts this paradigm to early detection of potential issues and degradation, therefore enabling teams to intervene before major outages occur. Then there is visibility. Modern applications are complex web of microservices, databases, cloud infrastructure, and user interactions. Continuous monitoring provides a holistic view of system health, therefore revealing bottlenecks or anomalies that could impact user experience. Then there is a point of beyond technical metrics. While CPU usage, memory, or error rates are essential, continuous monitoring also encompasses user experience, business metrics, and the security indicators to gain insights into how the software truly performs. So, the question is how continuous monitoring works. So, you define what to monitor. So, you need to define the key performance indicators or KPIs. You need to define the metrics, logs, and events that align with application health and user experience. So, there are certain tools that you would need to select. So, for example, you would have infrastructure monitoring. You would need to track system resources, which could be servers, network, storage. Then there could be application performance monitoring or APM, which will measure code level performance and user interactions. There could be logging and analytics, which could centralize logs, therefore providing a searchable historical record. Then there are incident management tools, which streamlines issues, ticketing, and communication. Now, other than define what to monitor and tool selection, you would also have data visualization. So it could present collected data in dashboards and reports for easy interpretation by different stakeholders. Then there could be alerting, which can set intelligent thresholds and triggers to notify teams of potential problems and anomalies. Then there would be continuous improvement, which can analyze trends and patterns to refine monitoring strategies and improve overall system resilience. Now, having talked about this, let me just also spend a quick minute to talk about the benefits of continuous monitoring in DevOps. So it could minimize downtime. So issues are caught early on, therefore minimizing user disruptions and business impact. Then there are faster root cause analysis. Rich data aids troubleshooting and accelerates problem resolution. Then there are informed decision making. Data driven insights support capacity planning, optimization efforts, and feature development. Then there is culture of reliability. Proactive monitoring enforces the importance of building healthy, robust systems within the DevOps teams. So, what are the key takeaways for continuous monitoring? Continuous monitoring is the radar of DevOps environment. It empowers teams to stay ahead of potential problems, therefore enhancing the software stability and ultimately creating a better experience for end users. Let's now talk about infrastructure as code or IAC. Now, in the good old times, what used to happen was if you had to deploy an application, so what needed to happen before that? You had to set up a server. Now, if that server had to be set up across three different environments, which could be testing, staging, and production, then you had to multiply that effort into three times into setting up that particular server. Now, in this particular scenario, nothing of that sort happens. Now, so infrastructure as a code helps you remove all this kind of bottlenecks. So, traditionally, setting up server configurations, network rules, and deploying infrastructure resources was a manual and error prone process because you had to do everything manually. So, you may not be able to replicate the same environment from testing to staging to production. Now, IAC or infrastructure as code changes this radically. IAC involves using declarative configuration files, which can be written in languages like HCL, YAML, or domain specific languages to define the desired state of your infrastructure. These files define what resources should exist, their properties, and relationships. Then there is version control. Just like the application's code base, IAC files are kept in version control systems, which could be something like Git, therefore allowing tracking of changes, rollbacks, and collaboration. Then there are certain benefits of infrastructure as code. So anything you do in the cloud typically has a lot of benefits because a lot of things are automated. Now, IAC also benefits from automation and speed. So provisioning or modifying infrastructure becomes a matter of executing code, therefore eliminating manual steps and significantly boosting speed. Then there is consistency and repeatability. IAC ensures environments are identical, which could be your development, testing, or production, therefore reducing configuration drift and environment related issues. And of course, with all this, you have reduced errors. IAC minimizes the risk of misconfigurations during manual setup. Then there is scalability. IAC allows for rapid scaling up or down of infrastructure on demand, therefore supporting flexible growth. Then obviously there is something called disaster recovery. In case of failures, IAC enables you to quickly rebuild complete environments based on the code definitions. So typically, how do you achieve IAC? So there is a typical process that you would follow. So you write the configuration file, you check them into a repository like Git, which means you do the version controlling, and then there is execution. Now, once the execution is done, then you have the environment up and running. So there are certain popular IAC or infrastructure as code tools. So there are various popular IAC tools. So for example, Terraform and Ansible are two key tools that you can use. Let's now talk about the customer centricity. Why customer centricity matters. Success in digital age isn't about building most features. Now, it's not just the features, but about providing the solutions that truly solve problems, improve experiences, and delight users. So, in the good old days, I had seen some of the applications where there were tons of features which had no use for the customer or the user at all. Now, there were lots of features that were being built into applications which you may not end up using at all. So, now here we are not talking about that. We are talking about building those features that will truly solve problems and are any use to the users. So, there is competitive advantage. Customer-centric companies understand their users deeply, resulting in more relevant products and services, therefore fostering long-term loyalty. So, for example, it is something like saying that I am building a product, but I don't know what users want, versus a company that goes out, takes the user inputs and builds a product. So obviously, the company is going to benefit more because they have built a product which is customer centric rather than another company building a product on their own without doing extensive research on the user needs. Then there is innovation driver. Closely aligning with customer needs sparks innovation, therefore allowing teams to develop features that have a genuine and positive impact. Now, if you go out and ask customer what they want and you innovate based on that, obviously customers are going to love your products. So there are certain elements in the customer centricity in DevOps. So it has to be embedded in the culture. It is not just a department's responsibility. Every member of the DevOps team, which could involve developers, testers, and operations, needs to understand and prioritize the user perspective. So they all should be on the same page, on the same platform. They should all know what the customer wants and they should understand in the same manner. So there are feedback loops. So there should be continuous feedback mechanisms that are established at every stage. So there is early development, which is based on user research, prototypes, and then there is post release, which is based on usage metrics, support tickets, and direct user surveys to gauge satisfaction. Then there are going to be cross team collaborations. Customer insights must be shared across the organization so that everyone from developers to product managers see the bigger picture. Then there are metrics that matters. So you should track user-centric metrics. So it could be adoption, engagement, and satisfaction score along with technical KPIs, which could be uptime and performance. Let's now talk about shared responsibility. So in the traditional model of development, so there was the dev team, there was the ops team. Now, both had distinct responsibilities and they would not interfere into each other's work. Now, DevOps is somewhat different. In the traditional development model, the software would be built by the development teams and they would hand it over to the operations, which is the ops team. Now, ops is responsible for deployment, troubleshooting, etc. Now, this was a very fragmented approach which led to finger pointing. Developers blames ops for deployment failures or vice versa. There was lack of end-to-end visibility. Devs may not understand the operational constraints their code runs in. There was a slower response time. It takes ages to get fixes released as issues bounce between teams. Now, DevOps changes all this. So it is a shared responsibility, which means all relevant stakeholders feel accountable for the software success throughout the entire life cycle. Now, dev owns their code in productions. Developers are responsible not only for writing the code but also for its operational health, which is performance, reliability, and security. Ops expertise is brought in early in the development process to prevent deployment issues and design for scalability. Then there is cross-skilled team members. DevOps encourages the growth of individuals with hybrid dev and ops skills, therefore further solidifying the collaboration. Now, what are the benefits do you get out of this shared responsibility? So, of course, there is improved quality. When everyone cares about the whole product, errors are brought earlier and a great focus is placed on non-functional requirements, which is something like performance and security. Then there is faster problem resolution. Troubleshooting becomes collaborative, therefore drawing on diverse perspectives and leading to a quicker fixes and less downtime. Then there is proactive approach. There is shared ownership that inspires a preventive mindset. Teams are invested in making the system resilient from the get-go. Then there is higher morale. Now, breaking down the silos reduces friction, increases trust, and makes work more rewarding for everyone. Now, what is the key takeaway for shared responsibility? Now, shared responsibility is not about making everyone do everything. That is a misconception. It is about fostering an environment where expertise is shared communication flows freely, and the ultimate goal of delivering great software fuels collective action. Let's now talk about continuous improvement. So there is technology evolves rapidly. Now standing still means falling behind. Continuous improvement ensures your team is constantly adapting, mastering new tools and optimizing processes. So it is also obvious that customer needs change. There is a dynamic market that is out there. Continuous improvement ensures your software align with evolving user needs and expectations. Now, what happens if you don't do continuous improvement? You're going to be stagnant. Your product will not change. They will not have innovation. So, therefore, you have to go with the customer needs. You have to figure out what their needs are and continue to improve your product. Then there is mistake happens. Continuous improvement turns failures into valuable lessons, therefore reducing the chances of repeating the same errors. Now we have understood what continuous improvement is. So what are the key elements of continuous improvement in DevOps? So there is cultural shift. Now, it is not one-time project. Continuous improvement can never be a one-time project. It has to be embedded into the team's DNA. Then there is Kaizen approach. Now, Kaizen is a Japanese philosophy which focuses on numerous ongoing small improvements made by everyone in the organization. This approach is perfect for DevOps. Everybody keeps making small improvements. You can understand what your product is going to be like. Then there is experimentation. Teams are encouraged to try new approaches, test hypotheses, and not fear intelligent risks. Now, there is a blameless post-mortem that is also there as a key element in continuous improvement. When things go wrong, the focus is on analyzing what happened and how to prevent recurrences, not on assigning blames to individuals. There are data-driven decisions, metrics, monitoring data, and user feedback informs which areas to focus improvement efforts on next. DevOps lifecycle. Now, DevOps lifecycle has a continuous nature. The emphasis on feedback, iteration, and constant improvement echoes the infinity loop symbol often used to represent DevOps. This highlights that it is not a linear process with a defined ending, but an ongoing cycle. So you have development, integration, testing, monitoring, feedback, deployment, operations, and then it circles back to the development once again. So this is not a linear but iterative with feedback from later stages feeding back into the earlier ones. DevOps emphasizes collaboration between development, operations, and other stakeholders through this entire process. Many tasks are automated to streamline the process and reduce manual errors. The focus remains on delivering value to users by continuously improving the software based on their needs. Let's break down the key phases of DevOps lifecycle. Let's first start with development. This is where the actual software development takes place. Developers gather requirements and then they write code to create new features or improve existing ones. So there is code review that also happens. You have to figure out whether the written code is correct or not, and that is what is included in the development. Then you move to the integration, which is typically the continuous integration. The new code is merged into the main code base, therefore triggering an automated build process. The CI system or the continuous integration system compiles the code and runs unit tests plus basic integration tests to catch issues early on. This is what happens in the automated build and test step. Then there is version control. Each integration step is versioned. For example, it could be Git where you're versioning your code and therefore allowing for rollback if needed. So every piece of code is versioned. As and when, for example, if you rolled out a new code, but it sort of crashed your application or that particular component within your application, you can always roll back that code from the Git repository or wherever your code is versioned. Let's now talk about testing. So there is functional testing. Testers which will run the manual tests or automated tests simulate user scenarios, therefore ensuring the new functionality performs as intended. Then there is regression testing. Test suites verify the new features don't break existing functionality of the software. Now, what happens if new features break the functionality of some other feature within that particular application? So again, in the previous slide, we talked about version controlling. That is where you would be able to roll back this new code so that the old feature can work as it was expected to work. So there is user acceptance testing or UAT. Stakeholders test the features in a staging environment, verifying it meets their needs. Then there is performance testing, which is typically optional. You can run load and stress tests that will assess how the software performs under heavy usage. So, for example, you have launched your application in a staging environment, but it can take the load of only 5,000 concurrent users. Now, what happens if the user count increases to 10,000? How will your application behave? Will it crash? Will it slow down? Or there will be other impacts that might be visible. So you want to check that out before releasing your application into the production environment. Now, the reason I said it is an optional test, because if you're dead sure that your application is perfectly fine, your servers that would be running the application are in a cluster form or they are running with the load balancers, then it is a different story. But still, it is a recommended step, but not everybody chooses to use it. So, for example, a small software company may not choose to run the performance tests, but typically a medium-sized or large organization, they will always go for performance testing and they will perform the load and the stress test to ensure that their applications can handle millions of users depending on what their scenario is. Then there is monitoring. So there is deployment monitoring, which immediately after the feature goes live, it closely monitors the errors or unexpected performance impacts. Then there are performance metrics. It is the data on performance indicators, typically the response time or resource usage, that are tracked to identify bottlenecks. Then there are user behavior analysis. Now, analytics tool provide insights into how users interact with new features, therefore aiding in future improvement. Now, there are certain features if the users don't even use, let's say there were 1 million users, and if they did not use some set of features or one particular feature, then obviously it means that feature probably is not required. That could be one assumption. But if there is one feature where it gave trouble to a lot of users out of that 1 million users, then obviously there is some problem under certain condition that feature fails to work. So you might want to check that out. Let's now talk about feedback. There are different ways you can gather feedback. So there are user surveys or interviews. You can get direct feedback from users that can reveal their satisfaction and pinpoint areas for enhancement. Then there are data-driven analysis. You can monitor logs and usage metrics, which will provide a quantitative view of feature usage and potential performance issues. So, for example, you can do a lot of analysis based on how many users tested your applications. You can take that data and create dashboards and view in the graphical form in graphs and other kind of inputs you can get on that dashboard and see what is the user feedback, how is user experiencing your particular application. Then there are feedback loop integration. Now, this insight flows back to the planning phase, shaping the next iteration of development. Let's now talk about deployment. A plan is established for releasing the changes to production. So, for example, it could be blue-green deployment or canary releases to minimize the user disruption. Now, this is done through deployment strategy. You need to have one before you even think about deploying an application. So there is automation, so which could be automated deployment or continuous deployment. Now, there are deployment tools that package and push the changes to production with minimal manual intervention. So either you could have the continuous delivery or you could have the continuous deployment depending on what you want to do. So in the continuous delivery, there is a approval stage that is there, which means you have to have a manual intervention. In the continuous deployment, you don't need any kind of manual intervention. It is automated. Now, the goal of good deployment strategy is to release new features or updates in a manner that minimizes downtime and disruption for end users. So, let's talk about some of the strategies. So, there is a blue-green deployment. Now, there are two identical production environment exists, which is called the blue and the green. At any given time, one is live, that is the blue one. New code is deployed to the inactive environment, which is green. After testing, traffic is switched over to green, therefore making a new live environment. Rollback is simple. Just redirect traffic to blue. In short, what you have is two similar environments. One is called the blue, one is called the green. Now, when you want to deploy code, you deploy it on green, which is inactive. Once the code is successfully deployed, you make it live. Now this becomes blue. Then the other one becomes green, because now that blue which was existing earlier, it is now turned into green because it is now inactive. So in case anything goes back in the new blue environment which was earlier green, you roll back, you simply bring up the older blue one live. Then there are canary releases. A new code version is deployed to a small subset of users first. Monitoring and feedback are gathered. If successful, the rollout gradually depends on the rest of the user base. This minimizes the blast radius of issues. Then there is rolling deployment. Servers or instances are updated one at a time or in batches. This avoids complete downtime but takes longer as users might be on different versions temporarily. So now how do you know which one to choose? So there are different factors that will influence the strategy of choosing the kind of deployment you want to do. So it could be something like downtime tolerance, how much downtime is acceptable during deployment. Another one could be feature complexity. Then it could be infrastructure or the user base size. So for example, feature complexity, is the change risky or can it be rolled back easily if needed? For infrastructures, does the architecture depend on strategies like blue and green? It could also be user base size. A gradual rollout, canary deployment that is, might be better for a massive user base to catch unexpected issues early on. Let's now talk about operations. So there is availability and uptime. Proactive monitoring ensures reliable access to the software and its new features. Then there is infrastructure management. Resources are scaled as needed to support the software, especially if usage patterns change. Then there is patching and security. There are regular updates and security patches are applied to the software system. So this was the brief introduction of these 3 points. So let's take each one of them and talk about them in detail. So there is availability and uptime. Now the goal of availability and uptime is to minimize downtime and ensure that the software and its features remain accessible to the users. You need to use tools that can continuously monitor system health, performance, and user behavior. Alerts are triggered for anomalies, therefore allowing teams to intervene before a minor issue turns into a full-blown outage. So you may want to use some of the key metrics like error rates, response times, and resource utilization. And you could also use the self-healing systems, for example, automated mechanisms that can detect problems and attempt self, therefore further reducing the need for manual intervention. Then there is infrastructure management. Now, there is scalability. You need to ensure infrastructure can handle variations in load. This may involve adding servers during peak demand and scaling down during low use period. Then there is infrastructure as code. Treating infrastructure as versioned, testable code enables consistent automation and rapid scaling. Then there is elasticity. This is the ability of the infrastructure to scale up or down automatically based on demand. Now, this is achieved through cloud services, and all these cloud service providers, for example, GCP, which is Google Cloud Platform, AWS, and Azure, all have this feature by default. Then there is resource optimization, which is about right-sizing instances and choosing the appropriate cloud services to optimize cost efficiency. Let's now talk about the third point, which is patching and security. So there is One critical thing that we have to talk about, that is the continuous vigilance. Now, security in most companies, it is a one-time task, which it is not. Security isn't one-time thing. Regular updates and vulnerability scans are essential. Then there is a patch management that needs to be put into place, which is a process for identifying, testing, and deploying software updates and security patches. This includes dependencies, the operating system, and the application itself. Then you have to be running vulnerability scanning. You have to use proactive tools that can scan the system for known vulnerabilities. Then you have to also follow security best practices, which is about enforcing security policies, security testing integrated into CI/CD pipeline, and secure coding principles that your development team needs to follow. Pillars of DevOps. So there are essentially four pillars of DevOps. So there is people, process, tools, and culture. So let's talk about each one of them. Now, when you talk about people, it is DevOps that depends on collaboration and communication across previously isolated teams. Building trust, fostering mutual respect, and encouraging knowledge sharing are essential to create high performance cross functional teams. Then comes the process. It is the streamlined and agile processes form the foundation for efficient software development and deployment in a DevOps environment. This includes practices like CI/CD and frequent and iterative releases. Then comes tools. There are a wide range of tools that support DevOps practices. Now, these tools can include version control tools such as Git, CI/CD tools, which could be Jenkins or Circle CI. It could be infrastructure as code tools, something like Terraform or CloudFormation. It could be monitoring tools like Prometheus and Datadog, and collaboration tools, which could be Slack or Jira. Then there is culture. Now, this is the most important pillar. Culture underlines successful or unsuccessful DevOps implementation. Now, if your team is not able to adopt the DevOps culture, then there is going to be a failure in implementation of DevOps. So now the successful DevOps implementation includes a shared mindset focused on continuous improvement, embracing experimentation and learning from failures, breaking down silos and fostering cross functional collaboration, and prioritizing customer needs and user feedback. So, how does it all fit together? While tools are an important part of DevOps, it is the intersection of people, processes, and culture that truly enable this transformative approach to software delivery. So, there are people. The right team with collaborative skills and a shared vision brings DevOps alive. Then there is process. Well-defined agile processes provide the structure and workflow for achieving efficiency and quick iterations. Then there are tools. Automation and collaboration tools support the processes and allow people to work efficiently. Culture. A strong culture of experimentation and shared responsibility provides the guiding framework for people, processes, and tools to achieve continuous delivery of value to users. Let's now talk about the working pillar of DevOps. So, how do the pillars of DevOps work together? So, there are different pillars that integrate with the other ones. So, there is people plus culture. A DevOps mindset means teams come together, sharing responsibility for creating quality software. This fosters open communication, therefore, breaking down us versus them mentality that hinder progress. Then there is culture plus process. The DevOps focus on experimentation and continuous improvement, aligning perfectly with agile development processes. This allows teams to move quickly, deliver software in smaller increments, and react promptly to feedback. Then there is process plus tools. Now, this is something that CI CD pipelines can exemplify. Development processes that prioritize frequent integration and testing are made immensely smoother by tools that automate code builds, run tests, and package software for deployment. This eliminates manual bottlenecks and reduces the chances of error during the deployment cycle. Let's unpack this a bit more. So there is this process. CI/CD as a process is the backbone of speedy and iterative DevOps. Then there are automation tools. Now these tools become the powerhouse that execute the process. Then there is continuous integration. Tools like Git, Jenkins take the burden of merging code, triggering automated tests, and catching problems early. Then there is deployment and delivery, which is continuous deployment and continuous delivery. Now, there are tools that automate preparing software releases and managing the process of rolling them into different environments, which could be testing, staging, or production. Let's now talk about the importance of pillars. So, why the pillars matter for DevOps? Now, DevOps is about more than just buzzword. This introspection is where the cultural shifts, collaboration, shared accountability are translated into tangible improvements. Let's talk about the importance of pillars. So, why these pillars matters for DevOps? So, there is philosophy realization. DevOps is more than just buzzwords. This introspection is where the cultural shifts like collaboration and shared accountability are translated into tangible improvements. Then there is error reduction. Manual tasks are inherently error prone. This is what we talked about earlier as well. Automation scripts or CD pipelines execute consistently every time. Now, this is the benefit of having automation into your integration and deployment process. This is because everything is automated. You set it once and let it run. Then, no matter whether you run it once or you run it 1,000 times, it's going to give you the same results. So, fewer errors mean fewer production issues and less time spending firefighting, therefore, positively impacting users. Then you have speed. Automation eliminates bottlenecks caused by manual handoffs or processes. Small, frequent releases become norm instead of large, risky, big bang ones. This enables teams to respond rapidly to feedback and market change. Then there is frees up developers. Less time spent on repetitive deployment or infrastructure translates to more time for building features and innovating. This can boost job satisfaction as developers see their work directly impacting users more quickly. So, what could be some of the tangible examples that we can talk about in this scenario? So, there is automated test coverage. Now, there are tests integrated into CI/CD pipeline prevent broken code from reaching production, therefore reducing errors that impact users. Another tangible example could be infrastructure as code. Instead of time-consuming server configuration, development teams define infrastructure needs in code, therefore enabling fast provisioning and consistency between environment. Then there is containerization. Package applications for easy deployment across environments, therefore enabling teams to focus on the code, not the underlying infrastructure complexity. So now in the overall scenario, the magic isn't just about the speed or error reduction in isolation. It is the cumulative effect. Devs have the tools to own their code in production, breaking down the silos. Shorter cycle mean quick experimentation and getting new values to users sooner. The magic isn't just about the speed or error reduction in isolation. It is the cumulative effect. So there are empowered teams. Devs have the tools to own their code in production, therefore breaking down the silos. Then there is faster iteration. Shorter cycle means quick experimentation and getting new values to users sooner. Then there are happier users. Reliable software that evolves to meet the needs of the users and build their trust. Now, in the overall scenario, DevOps tools aren't magic wands. Success depends on the right processes, culture, and how effectively team leverages the tooling. Benefits of DevOps. Now, there are several benefits of adopting DevOps. These benefits materialize gradually as a team adopts DevOps practices and invests in the right tools. Don't expect an overnight transformation. True success relies on fostering collaboration, a shared sense of ownership, and a commitment to continuous improvement. Now, there are several benefits that are listed on the slide. So let's go ahead and talk about each one of them. So the first one is higher efficiency. There is automation, which eliminates manual tasks in testing, deployment, and infrastructure management, therefore freeing up valuable time for teams. With the streamlined collaboration, you have reduced handoffs and improved communication between dev and ops team that leads to smoother workflows. So there are several tools that you would use to gain higher efficiency. So there are going to be CI/CD tools, something like Jenkins, Circle CI, and GitLab CI. Then there are several automation tools, something like Ansible, and of course, then there are scripts. Now, how do all this comes together? You have automation of builds, testing and deployment, and infrastructure provisioning that will dramatically speed up the processes and frees up the team members' time from repetitive work. That is where you gain the higher efficiency. Now, all this needs to come together. So you have the automation, you have streamlined collaboration, and then, of course, you have the tools. The next key point is then you have better reliability. We spoke about the CI/CD tools earlier. We talked about its processes. Now, automated testing early in the process catches bugs faster, therefore preventing costly issues in the production. For better reliability, you also use infrastructure as code. There are consistent environments that reduce errors caused by configuration drifts. Now, how does infrastructure as code helps you build consistent environments? Remember, we talked about scripts or configuration files that you can use to rebuild your infrastructure. For example, the same file can be used to rebuild your testing environment, staging environment, and even the production environment. So there is one file that can help you build consistent environment. So you don't have any kind of configuration drift. Everything can be replica of the other environment. Now, for better reliability, you also have monitoring. Proactive detection of issues allows for quick resolution before major failures. So you have to continuously monitor your infrastructure, your environment, and with the continuous monitoring, you will be able to detect any issues before they even occur. So this is proactive monitoring rather than reactive. Now, for better reliability, there are several tools that you can use. So there are testing frameworks, for example, Selenium and JUnit. Then for infrastructure as code, there is Terraform and CloudFormation. And for monitoring tools, there is Prometheus and Nagios. Now, how does all this help in better reliability? Early bug detection via automated testing, consistent and reproducible environments through IAC or infrastructure as code, and proactive problem identification through monitoring all serve to enhance system reliability and prevent outages. Then the next key point is faster updates. Now, for faster updates, you need to make small and frequent releases. DevOps encourages breaking changes into smaller and more manageable releases, therefore reducing the risk. Then for faster update, you also have automated deployments, which removes slow manual steps, therefore making updates reach users quickly. So for faster updates, there are several tools that you can use. Now, for the CI/CD pipelines, you have Jenkins. For containerization, there is Docker and Kubernetes. Now, how all this helps you make faster updates? Automated pipelines shorten the path from code to production. Containers streamline packaging and deployment across environments. Now, how do they help you in deployment across environments? They are portable. The containers are portable, which means you can take one container from Windows environment and you can port it to Linux environment, or from your on-premises environment to cloud. You can port these containers. So that is the reason containers are pretty much popular when you are using DevOps. Together, all these enable smaller and more frequent releases. Then the next key point is increased user experience. For increased user experience, there is responsiveness to the feedback. Shorter release cycles enable teams to incorporate user feedback more rapidly, therefore refining the product to much better needs of the users. So what happens is when there are shorter release cycles, obviously the feedback flows much quicker to the DevOps teams and they are able to incorporate that feedback into the next release or the next version they are going to produce or deploy to the users. Now, for the increased user experience, there are fewer bugs. Enhanced reliability directly transfers to fewer disruptions for users because you are making smaller releases and you also have the option of rolling back. Therefore, you can make one release, and if that doesn't work for some reason, you can roll it back to the previous version and make that happen. So, obviously, there are fewer bugs, and because there is testing and automated testing happening at each stage of DevOps lifecycle, then you have better chances of catching those bugs and therefore letting fewer bugs slip out, if any. So, what are the tools that you use for increased user experience? So, there are feedback tools. So, for example, you can have surveys and analytics platforms. So, there is a tool called Launch Darkly, which is a feature flagging tool. So, these are the tools you use for increased user experience. Now, how all this gets combined for increased user experience? You gather and analyze user feedback to guide rapid environments, while feature flags allow for controlled rollouts, getting new values to user without disrupting their overall experience. Now, the last point on the slide is reduced failures. To reduce failures, you need to have a proactive approach. Monitoring emphasizes early detection of potential problems, therefore reducing severity of incidents. That is your proactive approach. Now, for reduced failure, you also need to have faster rollbacks. Automation and version control makes reverting to a previous working state easier. So, just a minute back when I said if one release doesn't work, you can always roll back, and that is only possible if there is a versioning happening. Now, if every version or every piece of code is being versioned in a version control system like Git, then you are able to roll back to the previous code and use that particular version. So there are certain tools that you would use for reduced failures. There is monitoring, which is done through Prometheus. There is log aggregation, which can be done through ELK stack. And then there is incident management, which can be done through PagerDuty. So how does all this come together? Proactive monitoring and log analysis help identify potential issues early. Incident management tools streamline communication and response when failures do occur, therefore minimizing their impact. Let's move to the next slide and look at some more benefits of DevOps. So the next point is automation integration in development. So when you talk about automation integration in development, there is shift left testing. Now, shift left testing is a unique concept that is basically used in DevOps. Now, what happens is in a typical life cycle of software development, when do you do the testing? You do it towards the end. However, this is not the case with shift left testing. Now, this is the integration of automated testing early in the development cycle, which improves code quality before deployment. So, this means you start testing right from the start when the development starts, and you incorporate that testing into every phase there onwards and keep testing every piece of code that is getting developed rather than waiting towards the end. Then there is security as code. Security checks and scans are baked into the pipelines. So these are the CI/CD pipelines where there are security checks and scans happening for vulnerable code or code defects. Therefore, now this kind of security as code helps you prevent vulnerable code from reaching production. So, for example, if there is SQL injection vulnerability that is there in the code, it will get detected. Or if there is any other kind of code defect that is there which can make your application or your code vulnerable, then that will get detected. Now, for automation integration in development, there are certain tools that you would use. So there is static code analysis. For example, SonarQube is one product that you can use. Then there are security scanners. So there is OWASP, ZAP, and Snike is another tool. So how does all this help you? It helps you find bugs and security flaws early in the development cycle, therefore saving time and preventing costly production issues. Let's now talk about reduced backup complexity. So for reduced backup complexity, there is IAC, which is infrastructure as code, and versioning. Backup configuration can be defined in code, therefore allowing for rapid restoration of data and environments in case of disasters. So there are several tools that you can use to reduce backup complexity. So there is IAC, which we have talked about earlier. There is Terraform that you can use for infrastructure as code. Then there is cloud backup solutions. So there are different tools that you can use. So every service provider or the cloud service provider that you use, it would have its own backup tools. So you can use those. And for versioning, there is Git that you can use. Now, how does all this come together? Versioned infrastructure and backups enable quick restoration in case of data loss or disaster. Then there is increased infrastructure orchestration. Now, for this, you get scalability, automated provisioning and configuration of new infrastructure in response to demand. So, as and when you need to scale up your infrastructure or scale it down, you can use tools to do that. So, for example, you can use tools like Chef, Puppet, Ansible, and Kubernetes, which is basically used with containers. And then there are self healing systems. You have tools that can automatically replace unhealthy instances, therefore enhancing reliability. Now, for example, there are certain things that you can do. For example, if there is an issue with one server, it can automatically be shut down and another server can replace it. Or if there is too much workload on a particular server, another instance can automatically be brought online. You don't have to do anything manually. Now, how does all this help? It helps you to streamline infrastructure management. It helps you to enable rapid scaling based on demand. And it also helps you to support self healing systems and therefore increasing overall reliability. The next point is faster utilization monitoring. Now, obviously, you need to monitor your utilization of resources. In cloud, anything that you use will cost you money. So, therefore, you need to be very watchful of what kind of resources you are using. If something is not being used, you need to ensure that it is either shut down or deleted or destroyed so that you don't incur cost. Now, this is what is cost optimization is all about. You need to track resource usage across infrastructure to identify underutilized resources and find cost savings. Most of the cloud service providers, including Google Cloud Platform, Azure, or AWS, they give you tools which help you predict resource utilization and the cost that you would incur over a period of time. For example, Google Cloud Platform or GCP helps you predict costs for next couple of weeks or months. You can figure that out based on your current utilization. So you need to be very watchful. If, for example, if you are not using a virtual machine and it continues to run, it is better you should shut it down. And if you don't need it, you should basically go ahead and delete it. Otherwise, you would keep incurring costs. And of course, this also has to do with capacity planning. Based on your capacity planning, you would incur cost. Now, if you don't do appropriate capacity planning, so for example, if you over provision your resources that you don't need, for example, you have 10 virtual machines that you brought online, but you are using only 2 of them, you are going to incur cost for the rest 8 of them. Cloud service provider is not responsible for those resources. It is you. As the owner of that particular account in the cloud, you are responsible for your own resources in your cloud environment. So you need to monitor trends to ensure sufficient resources for peak load. So it should not happen that you under provision your resources. If you need 4 servers or 4 virtual machines to be brought online because that is the requirement, you should do appropriate capacity planning and bring them online. So what are the tools that you can use? There are different tools that you can use. So there is Datadog, there is New Relic. Every cloud service provider will give you tools for proper resource utilization and monitoring. Then comes the point of faster one-click deployment. Now, this is part of basically mature CD pipeline or the continuous deployment pipeline. A single click can trigger a complete deployment process from build to production. So which means once you check in your code, it can automatically generate the build. It can automate the testing process. It can also deploy that particular build into production. So there are certain tools that you would use. So for example, you can have tools for mature CI/CD pipelines that can be integrated with testing and deployment stages, potentially involving container orchestration. And Kubernetes is the tool that you would use for this. Now, how all this fits together? Basically, a single action triggers a fully automated process, therefore dramatically reducing the deployment time and human error potential. DevOps, containers, and microservices. DevOps provides a framework for rapid, iterative development and deployment, therefore emphasizing automation and continuous feedback. Containers like Docker package applications and their dependencies into portable, lightweight units, therefore enabling them to run consistently across different environments. Microservices are an architectural approach where applications are built as smaller, independently deployable services focused on specific functions. Together, these technologies create a powerful synergies. DevOps pipelines automate the building, testing, and packaging of microservices into containers, therefore ensuring agility and consistency. Container orchestration tools like Kubernetes manage the deployment, scaling, and networking of these containerized microservices across clusters, therefore aiding in complex deployments and self-healing capabilities. This combination fosters flexibility, fault tolerance, and enables teams to make small, frequent updates with minimal disruption, therefore aligning seamlessly with the core principles of DevOps. The combination of DevOps, containers, and microservices accelerates software delivery, improves reliability, and makes applications much easier to manage and scale. Here is what you get when you use the combination of all three. So there is agility. Teams release features and fixes in small and more frequent updates. You also get quality because there is consistent environment through containers and isolated microservices that lead to more reliable software. Then there is efficiency. Reduced deployment overhead and optimized resource usage is what brings in the efficiency. Then there is customer satisfaction, which is you get because there is the ability to respond quickly to feedback and market demands. Let's look at how these combinations can work. So there is DevOps plus microservices. Now, there is a modular development. Microservices encourage breaking down applications into smaller, independently managed components. This perfectly aligns with the DevOps emphasis on ownership and rapid iteration. Teams can update or fix specific service with agility. Now, why do you call it the modular development? The entire concept of microservices is that you don't build a single application as one component. You build smaller components that can be plugged in and plugged out, which means, for example, if there is a reporting function, the entire application will work by connecting different components together. Reporting is just one component. Now, if there is an issue with reporting, the entire application will continue to work. There is no impact on the rest of the components. So you can just plug out that reporting component, fix it, and plug it back in. And that same component can be used across different applications if you want. Now, with DevOps and microservices, there is independent scalability. Individual microservices can be scaled as needed, aligning with DevOps' focus on delivering value quickly in response to market changes or user feedback. Then, with DevOps plus microservices, you get resilient systems. You can isolate services in microservices architecture that helps you reduce the risk of cascading failures, which is a focus shared by DevOps principle of reliability. Let's now talk about DevOps and containers. So with DevOps and containers, you have encapsulated environment. Containers package an application with all its dependencies. This ensures code behaves the same regardless of where it is deployed, therefore streamlining testing and deployment in a DevOps environment. So this basically means you can port your containers from staging to testing or testing to staging or production, you can port them anywhere you want. You can take that same container from your on premises environment and port it to the cloud environment. So containers are nothing but a package where everything is bundled in for an application. So you have the libraries, you have dependencies, you have the application code, everything that is there in one single package, and you can just move that package around wherever you want to. Now, with DevOps and containers, there is also CI/CD efficiency. Containers enable rapid creation and destruction of test environments, therefore facilitating CI/CD workflow central to DevOps. Then there is faster rollback. Now, if an issue arises, containers allow teams to roll back to the previous version quickly, therefore aligning with the DevOps focus on minimizing downtime. Let's now talk about microservices and containers. So when you have this combination, so there is portability. Containers package each microservices along with its dependencies, therefore making them portable and easy to deploy across different environments, which could be your development, test, or production environment. Then there is resource efficiency. Containers allow for efficient use of resources, therefore maximizing the potential of microservices architecture. Then there is ease of management. Tools like Kubernetes further simplify the orchestration of containerized microservices, therefore helping manage updates, scaling, and networking. This empowers the operations side of DevOps. DevOps and Agile. In this topic, we are going to discuss the differences between DevOps and Agile. While DevOps and Agile have a complementary relationship, there are key differences in their focus and implementation. So let's go ahead and talk about that. Let's first look at Agile. Now, Agile is a software development methodology emphasizing on iterative development, flexibility, and customer collaboration. On the other hand, DevOps extends beyond development. It aims to bridge the gap between the development and operations team for seamless software delivery. Then, the core values of Agile are focused on iterative development, flexibility, and customer needs. On the other hand, DevOps focuses on collaboration and breaking down the silos. So basically, it brings along a lot of stakeholders. So it could be the customer, it could be the DevOps team, it could be the testers, or it could be the ops team. So it brings everybody together. So therefore, breaking down the silos, and it automates the delivery pipeline. So basically, you can say that you can also do one-click deployment from where generating the build to deploying that particular build. It's a one-click process. You can automate that entire CI/CD pipeline. Now, for Agile, there are popular frameworks like Scrum and Kanban that provide specific processes and practices for team to implement. On the other hand, DevOps leverages tools for automation, and there are tools like infrastructure as code, CI/CD pipelines, and monitoring. Now, main focus of DevOps is a broader cultural shift along with tools and practices. Tools themselves are not going to do anything. The teams that are working on software development using DevOps practices, they need to have a cultural shift. They need to have their mindset according to DevOps practices, and that is where they are going to be able to use these tools properly. So, for example, they need to collaborate. They need to have the sense of shared responsibility. There needs to be automation of processes. There needs to be continuous feedback and improvement, and they should be able to deliver value to the customer quickly and reliably. And then when you talk about Agile, there is input gathering during product development. So you keep getting input from the stakeholders and you keep building your product. On the other hand, DevOps basically uses the operational data for future releases. So it will keep on gathering data and then it will keep on building future releases based on that particular data. Let's now talk about Agile and DevOps working together. In the previous slide, I did mention that Agile and DevOps complement each other. Now, DevOps and Agile work incredibly well together because Agile's iterative approach that creates smaller, manageable code changes that are perfect for DevOps CI/CD pipeline. DevOps focuses on automation, which helps agile teams rapidly push those changes into production, therefore, further shortening time from idea to customer. Both Agile and DevOps prioritize feedback loops. Agile gathers input during the product development, while DevOps gathers operational data to inform future releases. Now, think of Agile as a methodology for how a development team builds the best possible software quickly. DevOps is about how the entire organization delivers that software to users with speed, reliability, and responsiveness to feedback. Integration of DevOps practices with cloud architecture. Integrating DevOps practices with cloud architecture offers immense benefits for streamlining deployment cycles and enhancing application quality. So, when you have DevOps and cloud architecture, they will boost each other, they will complement each other, and this is what we are going to talk about in this particular topic. So, first point is infrastructure as code, or IAC, plus cloud, which gives you agility. Cloud platforms offer on demand provisioning of resources, something like servers, networks, and storage. And IAC, on the other hand, it helps you describe infrastructure need as code. So, as a result, as and when you want to make changes to your architecture, which means you want to be scaling up or adding storage or scaling down, it can now be made up and deployed just like application code, therefore vastly increasing speed and reducing error. Then the next point is CI/CD pipeline plus cloud elasticity, which equals to faster deployment. Cloud environments easily scale up and scale down based on demand. Your pipeline builds and tests codes and then can deploy directly to your cloud infrastructure. As a result, instead of waiting on manual hardware setup, test environments can be spun up quickly, releases rolled out smoothly, and scaled based on real time needs. The next point is monitoring plus cloud observability, which equals to better quality. Cloud providers offer built in monitoring tools for resource usage, logs, and performance metrics. DevOps emphasizes constant monitoring for early issue detection. As a result, performance issues, bottlenecks, and even potential security threats can be spotted and addressed quickly, therefore improving the overall quality and reliability of the applications. Then you have microservices plus serverless plus cloud, which equals to resiliency and efficiency. Now you have microservices which can decompose applications into smaller and modular services. Then you have serverless or functions as service, which is known as FaaS. Now, cloud functions let you run code without managing servers. As a result, individual components can be updated independently. If one fails, it doesn't take down the entire application. Serverless often reduces compute costs in the cloud environment. Let's now talk about impact on deployment cycles and quality. The cloud eliminates hardware delays while DevOps automation smooths the delivery pipeline. Then there is more frequent releases. The ease of deployment encourages smaller, incremental updates aligned with DevOps principles. Then there is better reliability. Monitoring and flexibility of the cloud allows for quick troubleshooting and minimizing downtime. Then there is enhanced agility. Teams can quickly adapt infrastructure and deployment to meet changing needs, which is crucial in the DevOps approach. Now, let's talk about an example. Imagine updating a feature in traditional app versus cloud-based DevOps environment. What would you do in the traditional environment? You would make a code change. Then there is a lengthy provisioning of test servers. Then you would test the application, and then you would deploy the application using manual methods into the production environment. Now let's talk about how would you do this with cloud DevOps. You would make a code change. There is a CI/CD pipeline. There is automated test environment in the cloud. Testing would take place, and there is an automated deployment to scalable production environment. Now there is obviously a noticeable difference between both the methods, traditional versus cloud DevOps. In traditional, you are doing everything manually. The longest time you would spend is provisioning the test servers. You would have to build those test servers, and then you would have to deploy your code onto those test servers, and then you would do the manual testing, or maybe you would run the automated test, and finally you would do the manual deployment. Whereas nothing of that sort happens in the cloud environment. You would make a code change, CI/CD pipeline will get triggered, there is an automated test that would run, testing would take place, and then there is an automated deployment. Depending on if the tests have passed, your code gets deployed in the production environment, and that is the end of story in the cloud DevOps environment. Obviously, there is a saving of a lot of time that happens in the cloud DevOps. Now we have reached the end of this particular course. Now there are various topics that we talked about. So we talked about the DevOps introduction. We talked about the principles of DevOps and the DevOps lifecycle. We also talked about the key pillars of DevOps. And then moving on, we talked about the benefits of DevOps. And then we talked about the synergy between DevOps containers and microservices. And then we did talk about the differences between DevOps and Agile and how do they complement each other. We also discussed that particular part. And later on in the course, we talked about the integration of DevOps practices with cloud architecture. So what's coming up next? It is going to be the Google Cloud Platform Fundamentals course. In this course, you will learn the fundamentals of Google Cloud Platform or GCP, including its components, setup, and core services tailored for DevOps workflows. You will explore the power of automation within GCP, compare it to the other cloud platforms, and gain hands-on experience demonstrating its capabilities in common DevOps scenarios. There are several objectives we are going to cover. We will review the components of GCP or Google Cloud Platform. You will set up a GCP account. You will also navigate the GCP console. You will explore GCP's core services for DevOps. Then, towards the middle of the course, you will describe the tools and resources available in GCP for DevOps, and you will then provide an overview of the tool of automation in DevOps within GCP. Then, towards the later part of the course, you will list the benefits of using GCP for DevOps projects, compare GCP with other cloud platforms for DevOps, and then configure GCP for a DevOps workflow. Then finally, you will also investigate common DevOps scenarios. GCP components encompass a wide array of services and tools designed to meet various needs in cloud computing. They are categorized into several groups based on their functionalities. And this is what we are going to talk about in the upcoming slides. We are going to take each and every category and discuss that. So let's start talking about these components. So you have management. Now, it is basically used for controlling costs, and it helps you establish identity and access management and use APIs. Management category includes services like APIs and services, which is used for managing cloud service APIs. Then there is billing, which is basically used for billing and cost management tools. Then there is IAM and admin. IAM stands for Identity and Access Management, and it is used for resource access control and administrative functions. Then there is Google Cloud Setup, which is used for setting up and deploying best practices foundations. Then there is admin for Gemini, which is used for purchasing and managing subscriptions. The next category is compute, which is used for running scalable virtual machines and containers. It includes services like Compute Engine, then there is Kubernetes Engine, VMware Engine, Anthos, and Batch, which is jobs as a service. The next category is storage, which is used for storing long-term, short-term virtual machines and Firestore securely. It includes services like cloud storage, file store, storage transfer, PowerScale, and NetApp volumes. The next category is analytics, which is used for collecting, storing, processing, and analyzing large volumes of data. It includes services like BigQuery, PubSub, Dataflow, Composer, Dataproc, Dataprep, Datafusion, and Looker. The next category is networking, which is used for managing, connecting, securing, and scaling networks. It includes services like VPC network, network services, network connectivity, network security, network intelligence, network service tiers, spectrum access system, and telecom network automation. The next category is then distributed cloud, which includes services like edge, appliances, and serverless for managing edge infrastructure, devices, and applications powered by serverless functions and containers. The next category is serverless, which includes applications or services like cloud functions, cloud run, and service integration. The next category is databases, which is used for creating, managing, and migrating relational and non relational databases. It includes services like Database Center, SQL, Data Store, Firestore, Spanner, Bigtable, Memory Store, Database Migration, MongoDB Atlas, Neo4j Aura, Redis Cloud, and Alloy DB. Now, in continuation from the previous slide, let's talk about more components. Then there is observability, which is basically understanding the behavior, health, and performance of applications. It includes services like logging, monitoring, error reporting, and trace. Then there is operations, which is used for building, operating, and managing applications of Google Cloud. It includes services like Profiler, Capacity Planner, and App Hub. Then there is security, which is used for meeting policy and compliance objectives. It includes services like security and compliance. Then there is CI/CD, which is continuous integration and continuous deployment, which is used for integrating and delivering continuously. It includes services like Cloud Build, Container Registry, and Source Repository. And other services in this is Artifact Registry, Cloud Deploy, and GitLab. The next category is artificial intelligence, which is used for leveraging machine learning products. It includes services like Vertex AI, Translation, Document AI, Search for Retail, Talent Solution, Agent Builder, AI Task, CCAI Platform, Discovery Engine, Speech, and Vertex AI Vision. Then there is integration services, which is used for enabling applications and microservices to work together seamlessly. It includes services like Cloud Scheduler, Cloud Tasks, Workflow, Event Arc, Application Integration, Integration Connectors, Apache, and Developer Connect. The next category is tools, which is used for discovering productivity resources for the cloud. It includes services like Identity Platform, Deployment Manager, Service Catalog, Active Assist, Carbon Footprint, Apache Kafka on Confluent, Splunk Cloud, Cloud Workstations, Migration Center, and Web3. The next category is Web3, which includes Blockchain Node Engine for fully managed blockchain node hosting. Finally, then there is the last category, which is the other Google products, and that is not there on the slide, but I would like to mention it. And that category basically focuses on exploring gaming and Google Maps platform products. It includes services like Google Map Platform, Immersive Stream, and Google Workspace. Now, all these categories that we have talked about, and we have also talked about different services and tools within these categories. Now, each cloud service provider keeps on evolving their cloud computing platforms. So, don't be surprised if you don't find any of these services or tools in any of these categories that I have mentioned. There might be changes in the cloud platform, but as of now, these are the services and tools that are listed under those mentioned categories that we have talked about. Process of setting up a GCP account. Now, when you want to set up a GCP account, if you already do not have one, there are certain prerequisites that you need to follow. So, one is that you need to have a Google account. So, for example, you would need to have a Gmail account. You will basically need to use that particular account to set up your GCP account. And if you don't have a Gmail account, for example, you would need to first create that. And then, second, you need to have a credit card. While GCP offers a free tier with limited usage, you will need a valid credit card for billing purposes if you plan to exceed free tier limits. So you will not be charged within the time period when you are using the free tier. So there are about $300 of free usage that you would get, which extends over 3 months. But they still require your credit card, because when you're setting it up, they will charge you a certain amount, a very minimal amount, just to ensure that your credit card is functional and it is valid. Once you set up your account, you will be able to use the free tier. And I would like to also highlight that when you set up your free account, you create some resources, you use certain services. Let's say, for example, if you set up a database, once your need is over, go ahead and delete those. There is certain money in that. You will be charged against that. But once that amount is over, even if you are within the free tier limit, you will start being charged. So, therefore, you need to be very careful how much services you use. So let's go ahead and now and look at the process of setting up a GCP account. So to start with, you need to go to the GCP website. So this is cloud.google.com, and you need to click on the Get Started for Free button, or there could be similar wording. So like I said in the previous video, there might be changes in the platform. So it doesn't matter what it is, but look for something called Get Started for Free, something of that sort. Then the next one is sign up and verification. You will need to complete that process. You will need to provide the information. You will need to fill in the form with your personal details, country of residence, billing address, and agree to Google Cloud Platform's terms of services. Then there will be verification. You might receive a verification SMS or phone call to confirm your account. The next step that you need to do is, once you have successfully signed up, you would need to create a project. You would need to define a project name, choose a descriptive name for your first GCP project. This will be the container for all your cloud resources related to specific application or use case. And then you would also need to do billing setup. You would need to link your credit card to your payment methods for this particular project. Then you would need to enable APIs. So there are certain services or tools that you would need to use. So when you are starting, the essential API should automatically be enabled. If you need more specialized services, for example, if you want to enable a certain database service, or you want to use certain analytical services, you would need to enable those additional APIs. So for example, AI services or Maps API, you would need to enable them. And then the next step is to explore the free tier. You need to familiarize your services with the GCP free tier. It gives you access to many popular GCP services within limited quota and time frames. You can find details on the GCP free tier page. And then you would need to apply the security best practices, and this is one of the highly recommended steps. You should perform the IAM, or identity and access management setup. You would need to carefully set up IAM rules to control who can access which resources. You should consider the principle of least privileges when using IAM. And you can also create multiple projects. It is often recommended to use separate GCP projects for distinct environments. So, for example, if you are going to be setting it up for development, staging, or production, this is basically, you can replicate those environments, but this is also to enhance security and proper organization of your resources. So that was the last step. You have successfully completed the process of setting up a GCP account, and now it is the time to start using GCP. You can explore GCP console, which is the web interface. You can also install the cloud SDK for command line interaction in your local development environment. Let's now talk about the important considerations. GCP services generally follow a pay as you use model. While the free tier is a great start, exceeding the limits or using premium features means you will be charged. You need to understand how much you are spending. That is going to be a key to maintaining control of your expenses within the GCP environment. So, there are some tools that you can use. So, for example, you can use the billing dashboard. GCP console provides a visual overview of your cost and spending trends. Then there are billing reports. You can get detailed cost breakdowns, filterable by projects, resource types, and there are other filters available as well. Then there are budget alerts. You can set customizable thresholds to receive notifications via email or PubSub when your costs approach or exceed your defined budget. So the next point is free tier expiration. Now, GCP's free tier offers several always free services with limits and a credit based trial for other products. It is great for testing, but it is not a long term solution. You should know the free tier limits and full pricing for the services you are using. You should have a plan for how you will handle the move to a paid account. This might involve adjusting your usage, optimizing resources, or exploring cost saving options. Then the next point is cleanup. You should basically be aware of the unused resources. Leaving unused resources running can lead to ongoing and unnecessary costs. For example, you might just leave virtual machines running and there is nothing happening on those virtual machines. So that is going to be charged. Old data in storage buckets, infrequent access storage tiers, they are going to be charged. And if you have unnecessary snapshot of disks, get rid of them, delete them because they are also going to be charged. Now, there are certain strategies for cleanliness. You should identify the unused resources. You should use GCP tools and reports to spot idle resources. You should automate deletion. You can set up schedules or use scripts to automatically remove unused items after a set time. Then there are resource labeling. You can label resources with project names or owners for better tracking and targeted cleanup. Now, just to quickly recap, in this particular topic, what we talked about is the prerequisites for setting up a GCP account. We also talked about the process of setting up a GCP account. And then we also talked about some of the important considerations regarding the GCP account. So, for example, cost and monitoring and budgeting alerts. We also talked about the free tier expiration and the cleanup. Illustrate how to navigate the GCP console. Now, to be able to navigate to the GCP console, there are certain prerequisites that you need to meet. You need to have the GCP account. So, if you don't have a paid account, a free tier is sufficient. You also need a web browser and internet connectivity. Now, to be able to access the GCP console, what you need to do is you need to navigate to this particular URL, which is the console.cloud.google.com. So once you go there, you will need to authenticate yourself. And once you are logged in with your GCP account credentials, you will get to this particular screen, which is the home dashboard. So you will need to familiarize yourself with this particular dashboard. So there is the navigation bar. So there is this project, there is the search bar, and then there are other things like Cloud Shell, there is notifications, and then there is help. And there is this hamburger icon, which if you click, it will give you all the categories of services that we spoke in one of the earlier topics. So you can use all this projects selection that you can do. So there is a default project that you can set. And now notice, once I click on this drop down arrow, there are different projects that I can work with. I can also create a new project. Now I'm going to just go ahead and cancel this out. And if I need to search for services, I can use this search bar. So for example, if I need to search for cloud build, and I can then select it right from the search results. So this is another thing you can do from this. And you can also click on this if you're somewhere else and you want to come back to the dashboard. You can just click on this Google Cloud icon and you can come back here. And you can also access certain categories. So for example, API and services, you can go to billings, you can go to compute engine, or you can even just click on this view all products icon, and it will give you list of all the products that this platform has. So of course it will list them category wise, and you can just scroll through and access any of these products or services under a specific category. So for example, under analytics, you can use BigQuery or PubSub or Dataflow, Composer. Similarly, if I just scroll down, there is networking and VPC network. Access your VPC private cloud. You can configure your network services, network connectivity, network security. So similarly, let's say if I just go ahead and click on databases, it will quickly jump on databases, and then there are different types of databases that are there. There is data store, firestore, spanner, bigtable, memory store, and then there are other services like database migration. So this is basically it about the console. Now, more you explore it, more you're going to learn about it. So when you initially log on to the console, it might be an unknown territory, but more you use it, more you will be familiar with it, and more easy it would become for you to use it. And one thing is there that it is constantly evolving. So you might see certain changes all of a sudden. One day you just log in and you find that entire interface has been changed or some things are missing. Now that is going to be there many a times when you log on to your console. Now, to be able to overcome this, you should use GCP's extensive documentation to learn more about the specific services and capabilities and what has changed. And you should also use the GCP communities to know certain things if you are unable to figure them out, even though GCP's documentation is pretty extensive. Now, just to quickly recap, in this particular topic, what we have done is we have looked at the GCP console and we talked about certain places in the GCP console. So, for example, we talked about the search bar, we talked about the hamburger menu. So, these are certain things that we talked about. GCP's core services for DevOps. There are several GCP's core services that are used for DevOps. So we are going to be talking about these services in this particular topic. So let's start with Compute Engine. GCP's Infrastructure as a Service, or IaaS, offering provides flexible virtual machines for running applications and workloads. You can choose from standard machine types, optimize memory and CPU, and use machine types for specific needs. Then there is source code management and version control. Now, for that, you can use tools like Dataform, which helps you keep track of your development. Now, Dataform uses Git to keep track of each change you make to your particular code. Now, the next point is build and continuous integration, which is CI. Now, for that, you can use tools like Cloud Build and Cloud Code, which is basically used to work entirely in the cloud native environment. And you can use Cloud Code to kickstart your CI CD pipeline. Let's now look at some more core services for DevOps. So there is a tool called Cloud Deploy, which is Google's managed continuous delivery services specifically tailored for continuous delivery to GKE, which stands for Google Kubernetes Engine. Now, GKE is a managed Kubernetes service for deploying, managing, and scaling containerized applications. GKE simplifies building and running production-grade Kubernetes environment. Then there is monitoring and logging, in which you have cloud monitoring, which is a comprehensive monitoring suite for GCP and hybrid cloud environments. It can collect metrics, logs, and events and use customizable dashboard and alerting mechanism. Then there is cloud logging, which is a centralized log aggregation and analysis service. It can store, search, analyze, and monitor log data from GCP resources and applications. Then there is Infrastructure as Code, or IAC. It has Cloud Deployment Manager, which is the GCP service for creating and managing infrastructure using declarative configuration files or templates. This promotes consistency and repeatability in your deployments. Let's go ahead and look at some more core services for DevOps. There is Data Analysis and Insights. It has tools like BigQuery, which is a serverless data warehouse for analyzing massive data sets using SQL. It informs data-driven decisions for development. Then there is Dataflow, which is a managed service for building data processing pipelines. Then there is PubSub, which is a real-time messaging service decoupling systems for event-driven architectures. Then there is Observability. It includes tools like CloudTrace, which visualizes request latencies for distributed systems, especially useful for microservices. Then there is Cloud Debugger, which debugs code in production without affecting performance. The next one is serverless computing, which includes tools like Cloud Functions, which execute small and focused code snippets in response to events and triggers. Then there is Cloud Run, which executes containerized applications that respond to HTTP requests without managing the underlying infrastructure. Let's now look at some additional services. So there is Cloud Identity and Access Management, or IAM, which provides granular access controls for GCP resources. It can manage roles and permissions to ensure appropriate access levels in your DevOps practices. There is Security Command Center, which is a central hub for security visibility and vulnerability management across your GCP environment. It can help you identify potential risks and get recommendations for remediations. The next one is API Gateway, or Apache, which manages, secures, and scales APIs. This is useful for exposing services and managing communication throughout your DevOps toolchain. There is Cloud PubSub, which is a real-time messaging service for decoupling components and building event-driven architecture. Just to quickly recap, we talked about the core services for DevOps in the GCP environment. So we talked about Compute Engine. We also talked about source code management and version control, build and continuous integration. We also talked about deployment and continuous delivery, monitoring and logging, and infrastructure as code. Towards the later part of the topic, we also talked about observability, serverless, and then we also talked about Cloud IAM, API Gateway, and Cloud PubSub. List tools and resources available in GCP for DevOps practitioners. In one of the previous topics, we did talk about certain tools and services that are available for DevOps practitioners. Now, just to quickly recap that, so there are tools that are under development and version control category. So, for example, you have cloud source repositories, you have cloud code. Then for CI/CD, you have cloud build, artifact registry, cloud deploy. Then for infrastructure management, you have cloud deployment manager. So similarly, there were different categories of tools that are available for DevOps. Now, the way to access these tools is very easy. One way is you can go through view all products, you can click and you can go to specific categories and look for those tools. Another easy way is simply you can just say cloud build and then you have cloud build in the search results. Another thing you can do is, for example, if you want to access cloud IAM, then again, you can access identity and access management from here. And now, if you want to use other tools like Cloud Deployment Manager, similarly, what you need to do is Cloud Deployment Manager. You can just simply search here and you will be able to get that tool in the list. And all you need to do is select that. And then if you want to use any other tool like Cloud Code, you can simply type that and there you go. You will have different documentation and everything, and you will have different set of tools that you can access, or you can simply go to the marketplace and search for those tools. Now, these are the tools that are available. And for example, another tool that you might want to access is BigQuery, which falls under the data analysis and insights, and you can access that from here. Now, I talked about view all products. Once you click on this, you can go to that particular category and you can access those tools. So this category is now loaded. So for example, if we want to access Cloud IAM, I need to go to security, and under security, I can search for this. So there is security, there is compliance. For CI/CD, there is cloud build, container registry, source repositories, artifact registry, cloud deploy, GitLab. Now, all these tools are used by the DevOps practitioners, and you can use them if you want to set up your CI/CD pipelines. Now, there are additional resources that you can access. So, for example, you can go to the GCP marketplace and you can also access the Google Cloud documentation. Now, GCP Marketplace is a place where you will be able to find several tools that are not listed here. Those will be third party tools that you can integrate into your GCP platform for your CI CD pipelines or for your DevOps development. Now, just to quickly recap, we talked about certain tools. We talked about Cloud Build, we talked about Cloud Source repositories, and these are the tools that are available for DevOps practitioners. Role of automation in DevOps within GCP. In this topic, let's talk about why automation matters for DevOps. So, there are certain reasons. So, there is speed. Automation eliminates manual, repetitive tasks in development, testing, deployment, and infrastructure management, therefore, drastically accelerating delivery life cycles. Then there is consistency and reliability. Automated processes reduce the potential for human error, therefore leading to more consistent deployments and a more reliable overall system. Then there is scalability. Automated infrastructure scaling and resource provisioning allows your applications to handle fluctuating workloads and demand surge smoothly. Then there is collaboration. Automation reduces silos by defining workflows that involve both development and operations team, therefore leading to better information flow and shared responsibility. Let's now talk about how GCP automates DevOps. GCP provides a powerful toolbox to streamline and automate DevOps processes, therefore fostering a faster release cycle and improved reliability. GCP facilitates automated CI/CD pipelines with services like Cloud Build, Artifact Registry, and Cloud Deploy, therefore streamlining the path from source code to production. Infrastructure as code or IAC concepts are empowered through Cloud Deployment Manager, therefore ensuring consistency and reducing manual configuration. Serverless offerings like Cloud Functions and Cloud Run minimize operational overheads, therefore, letting you focus on code. GCP's integrated monitoring and auto-scaling features ensure your applications remain performant while optimizing costs. Security is tightly woven into the automation with Cloud IAM and Security Command Center, therefore enabling proactive security management. So let's look at some of these components which help you automate DevOps. So there are CI/CD pipelines, you have Cloud Build, Artifact Registry, and Cloud Deploy. Then there is infrastructure as code, which is through Cloud Deployment Manager, and it helps you define and provision the infrastructure, which could include your networks, VMs, which is virtual machines, and databases using declarative templates. This enables versioning, repeatability, and consistency across environments. Then there is serverless computing, which is through Cloud Functions and Cloud Run. Cloud Functions write event driven functions that automatically execute code in response to triggers. For example, if there is a file upload or database change, it could trigger piece of code. And this helps you minimize infrastructure management. Then there is Cloud Run, which is basically to deploy containerized applications without needing to provision servers. The next point is monitoring and auto scaling, which is done through cloud monitoring and GKE, which is Google Kubernetes Engine and Compute Engine. Now, cloud monitoring helps you collect metrics and logs, therefore allowing for automated alerts when issues arise. Then there is GKE and Compute Engine. Autoscaling features adjust resources based on usage patterns, therefore optimizing performance and cost. The last point is security automation, which is through Cloud IAM. It helps you automate the management of permissions and access control. Then there is Security Command Center, which is used for proactive threat detection and recommendations for remediation that can trigger automated responses based on predefined policies. Let's now talk about the impact for DevOps team. GCP's automation tools enable DevOps team to release faster. So there are shorter cycle from code change to deployment thanks to automated processes. Then it also helps you build more reliable systems, which means there are reduced errors and increased consistency due to automation. Then there is focus on innovation. Teams spend less time on manual tasks, therefore freeing them to focus on improving their applications and driving value. So let's talk about an example. Imagine deploying a code change. Now, traditionally, there will be manual builds, testing across environments, coordination with ops for server provisioning, which could be slow and error prone. Now, let's take the same scenario with GCP DevOps. A code change triggers cloud build, artifacts deploy to artifacts registry, and if successful, Cloud Deployment Manager updates production with new image, therefore leveraging cloud monitoring for health check. Just to quickly recap, in this particular topic, we talked about why automation matters for DevOps. We talked about speed, consistency, and reliability, scalability, and fostering collaboration. Then we talked about how GCP automates DevOps. So we talked about CI/CD pipeline, IAC, serverless computing, monitoring and autoscaling, and security automation. And then we talked about impact for DevOps team. We talked about releasing faster, build more reliable systems, and focus on innovation. And then we also talked about a quick example which compared traditional and GCP DevOps. Let's look at the benefits of using GCP for DevOps teams. We will look at each one of these items in detail in the upcoming slides, and these items are speed and agility, scalability and elasticity, reliability and resilience, collaboration and integration, security and compliance, and cost efficiency. So let's go ahead and look at each one of them in detail. So let's talk about speed and agility. So there is rapid provisioning. GCP's on-demand infrastructure, which includes virtual machines, databases, and networks, eliminates delays associated with hardware procurement and setup. Then there is CI/CD automation. Tools like Cloud Build and Cloud Deploy streamline pipelines, therefore facilitating frequent code releases for faster feedback and iteration. Then there is serverless options. Cloud Functions and Cloud Run reduce the overhead of managing infrastructure, therefore allowing developers to focus on code. Let's now talk about scalability and elasticity. So there is autoscaling. Compute Engine and Google Kubernetes Engine can automatically scale up or down based on demand, therefore ensuring your applications can handle traffic peaks and optimize costs. Then there is global reach. GCP's global network allows you to deploy applications closer to your users for reduced latency and improved performance. Let's now talk about reliability and resilience. So there are managed services. GCP's highly available managed services such as BigQuery, Cloud SQL can reduce operational burden and increase infrastructure reliability. Then there is advanced networking and load balancing. Features like load balancing and multiple network tiers help you distribute traffic and build fault-tolerant applications. Then there is disaster recovery. Backup solutions and multi-region deployment options protect your applications from unexpected outages and data loss. Let's now talk about collaboration and integration. So there are shared workspaces. GCP's project-based structure makes it easy for development and operational teams to work together within a single environment. Then there is seamless tooling. GCP's CI/CD monitoring and IAC tools are designed to work together, therefore creating a cohesive DevOps experience. Then there is marketplace. Pre-built solutions and integrations accelerate your project setup and workflows without starting from scratch. Let's now talk about security and compliance. So there are robust security controls. Cloud IAM provides fine-grained access management. Security Command Center monitors for vulnerabilities, therefore adding a proactive layer of security. Then there are compliance standards. GCP's certifications for various industry standards such as PCI DSS, SOC, and HIPAA simplifies meeting compliance requirements. Let's now talk about cost efficiency. So there is pay per use. You only pay for resources you actually consume. Then there is sustained use discount. Automated discounts kick in for resources that run for extended periods, therefore helping reduce long-term costs. Then there is free tier, which provides access to many GCP services within usage limits, therefore allowing for experimentation and evaluation at minimal cost. Just to quickly recap, in this particular topic, we talked about the benefits for DevOps teams. We talked about speed and agility, scalability and elasticity, reliability and resilience, collaboration and integration, security and compliance, and cost efficiency. Comparison of GCP with other cloud platforms for DevOps. Let's break down this table and provide a detailed explanation of each cloud service provider's strength from a DevOps viewpoint. Let's first talk about market maturity. GCP is an established player with strong focus on innovation. They constantly introduce new features and updates, therefore pushing the boundaries of cloud technology. This makes them a good choice for those seeking cutting-edge solutions. AWS is the market leader with a long history and proven track record. They offer a extensive breadth of services. Their focus on stability and reliability makes them ideal for mission-critical workloads. However, their update cycle might be slower when compared to GCP. Azure is a strong contender, particularly popular with enterprises and .NET focused environments. They leverage Microsoft's established presence and integrate seamlessly with the developer tools that Microsoft has. The next point to discuss is compute options. GCP offers a wide range of virtual machine types and they can cater to diverse needs. They have a flexible and a powerful Kubernetes platform, which is known as GKE or Google Kubernetes Engine, and robust serverless options with Cloud Functions and Cloud Run. They are ideal for scaling applications based on demand. AWS, on the other hand, provides a wide array of instances which are known as EC2 with various configurations. They have a mature Kubernetes service which is known as EKS and were pioneers in serverless computing with AWS Lambda. The sheer number of options can be overwhelming, but it ensures you can find the perfect fit for your workload. Azure offers a diverse virtual machine options, so they call it Azure VMs, and they do it along with well-integrated Kubernetes service or AKS. Their serverless offerings, which is Azure Functions, is a particularly .NET friendly, therefore making it a great choice for those environments. The next point to discuss is CI/CD tools. GCP provides seamlessly integrated tools like Cloud Build for building code, Artifact Registry for managing artifacts, and Cloud Deploy for automating deployments. This tight integration streamlines the CI/CD pipeline. AWS, on the other hand, offers excellent CI/CD support through a suite of tools. So they have Code Pipeline for orchestrating workflows, Code Build for building code, and Code Deploy for automated deployments. This provides a robust and flexible approach. Azure provides a robust CI/CD tooling like Azure Pipelines and Azure DevOps. These tools offer great functionality and integrate well with Visual Studio, therefore making them a natural choice for Microsoft development environments. The last point is infrastructure as code or IAC. GCP uses Cloud Deployment Manager for declarative configuration templates, therefore allowing you to define infrastructure in code. This promotes versioning, repeatability, and consistency across environment. AWS, on the other hand, relies on CloudFormation as the established IAC standard. CloudFormation is a mature and widely adopted tool with extensive documentation. Azure Resource Manager or ARM templates and strong PowerShell support for IAC. This approach is familiar to those already working with PowerShell scripting. Let's continue to the next slide and look at some more comparison. Now, in continuation from the previous slide, let's look at some more comparison between AWS, GCP, and Azure. The next point of discussion is monitoring and observability. GCP has excellent tools like cloud monitoring, cloud logging, and cloud trace that provide comprehensive insights into your applications and infrastructure. These tools are intuitive and easily integrated with other GCP services. AWS has comprehensive monitoring services like CloudWatch for metrics and logs and X-Ray for distributed tracing. They offer extensive visibility and customization options, but the configuration can be more complex. Azure offers insightful monitoring via Azure Monitor and Log Analytics. It provides a strong baseline for understanding applications and infrastructure health, especially within the Microsoft ecosystem. The next point of discussion is security and compliance. GCP features advanced security controls and compliance certifications, therefore, making it a great choice for regulated workloads and security conscious organizations. AWS provides an extensive array of security services and features, as well as strong record of meeting compliance standards. They offer excellent protection and flexibility. Azure delivers robust security solutions with emphasis on enterprise workloads. They integrate well with Microsoft security tools and provide a familiar experience for existing Microsoft customers. The next point of discussion is cost management. GCP features transparent pricing, sustained use discount for predictable workloads, and a generous free tier for exploration. Their cost management tools are user friendly and provide good visibility into spending. AWS has complex pricing models but offers potential for cost optimization with careful planning and usage of tools like reserved instances. Azure offers competitive pricing with several free service offerings. It is a good option for existing Microsoft customers due to potential licensing discounts and existing relationships. The next point of discussion is learning curve. GCP is generally considered as one of the more user friendly cloud platforms with helpful documentation and a clean web console. This makes a great starting point for those new to cloud computing. AWS can be overwhelming for beginners due to sheer number of services and configuration options. However, they offer extensive documentation and tutorials. Azure is familiar for those coming from a Microsoft ecosystems with existing experience using tools like Visual Studio and PowerShell. Let's continue to the next slide and look at some more comparison. In continuation from the previous slide, let's look at some more comparison. So the next point of discussion is serverless functions. GCP has Cloud Functions, which is GCP's event-driven function service. You can write code snippets that can respond to triggers, for example, database change or HTTP request. It handles the underlying infrastructure entirely, so you focus on code logic. Then AWS has AWS Lambda, which is the pioneer in serverless functions. It offers extensive language support and deep integration with other AWS services. It is a mature and powerful choice for building event driven architectures. Azure has Azure Functions, which provides strong language support, especially for .NET and seamless integration with Azure ecosystem. It is a great fit for developers already familiar with Microsoft technologies. The next point of discussion is configuration management. So GCP has Cloud Deployment Manager, which enables infrastructure as code. It defines infrastructure using declarative templates, therefore ensuring consistency and automating deployment, which is invaluable for repeatable DevOps processes. AWS has AWS System Manager, which is a suite of tools for managing configuration across AWS environment. It allows patching, inventory management, and remote execution for both cloud-based and on-premises infrastructure. Azure has Azure Automation, which automates infrastructure configuration and operational tasks with PowerShell and graphical workflow tools. It integrates well with Azure resources to streamline management in Azure environments. The next point of discussion is Identity and Access Management, or IAM. Google has Google Cloud IAM, which provides centralized control over access to GCP resources. It implements fine grained permissions for secure user and service account management. Therefore, It is crucial for controlled access in the DevOps pipelines. AWS has AWS IAM, which is a robust IAM system with granular permission across AWS services. It supports complex role hierarchies and cross account access, and it is essential for managing access within large organizations with multiple resources. Azure has Azure Active Directory, which integrates on premises entities with Azure Cloud. It provides seamless access control, especially for hybrid cloud environments with an existing Microsoft footprint. The last point of discussion is networking. GCP has Virtual Private Cloud or VPC, which isolates network resources within your GCP project. It defines security rules, subnets, and routing for secure communication between serverless functions and other resources. Amazon has Amazon VPC, which provides logical isolation of your cloud resources within AWS. It offers comprehensive control over your network configuration, security groups, and subnets for complex private network setups. Azure has Azure Virtual Network, which is similar to VPCs. It lets you logically isolate resources within Azure. It provides fine grained network configuration and integrates with on premises network for hybrid setups. Just to quickly recap, in this particular topic, we compared GCP with AWS and Azure. We talked on various points. We talked about the market maturity, compute options, CI CD tools, infrastructure as code. And other than that, we talked about the serverless functions, configuration management, IAM, and networking. Initial GCP configuration for a DevOps workflow. Now, in this particular demo, we will set up the cloud source repositories and configure cloud build. That is all what we are going to do because this is the initial configuration that is the main topic of this particular demo. Now, to be able to achieve this, there are certain prerequisites are that you need to have a GCP platform account. That is by default because if you don't have an account, you won't be able to work in the GCP platform. And you also need to have some basic familiarity with GitHub, and then you need to have a GCP project. Now, if you don't have a GCP project, you would need to create one. And then you need to enable certain APIs. So there is Cloud Build API, there is a Cloud Source Repository API, and App Engine Admin API. Now, if these APIs are not enabled, you will be prompted to enable them. And for this particular demo, we have already enabled them. Hence, we will not repeat these steps. If you need in your own environment, you can enable them through the APIs and services page. So now let's set up the cloud source repository. So to be able to do that, we are already on the cloud source repositories page. Now I'm going to click on this button called Go to Cloud Source Repositories. So there is certain information that is being displayed after June 17, 2024. New customers will not be able to use cloud source repositories. And if somebody has been already using it, they will not be impacted. Now, to be able to create a repository, I need to click on this Add Repository button. I already have one repository configured, but for this particular demo, we are going to go ahead and create a new one. So I'm going to click on Add Repository. And there are two options: create a new repository, which is going to be an empty repository, or you can connect to external repository. So I'm going to select this option and click on Continue. Now, for this, there are certain requirements. So you need to have the project. So I'm going to just click here and type SKS. This is our current project, SKS01. And for Git provider, there are GitHub and Bitbucket. So I'm going to select GitHub. And now this gives me the associated accounts. I've already configured this. Now, if I want, I can connect to a different account, or I can choose my account. Along with this particular account, whatever the repositories I have on this GitHub account, they are already listed because it will scan and download the list of repositories. Now, if a repository name is disabled, that means it is already connected to that particular repository. So we are not going to connect to this one. There is another one that we are going to be connecting to, and that is called Python doc samples. I'm going to select this, and then I am going to go ahead and click connect selected repository. Now this process of connecting repository starts. It usually doesn't take much time. And once this is connected, that particular repository will appear in our list of connected repository. So like I said, we already have one repository connected, and now we've got the notification that it's connected to Python doc samples repository as well. So I'm going to click on OK. So I need to sync from GitHub. So I'm going to click on this particular option. And now if I just go back to Cloud Source repositories page and click all repositories, notice that this is now listed. So previously I had first web app 01, and now I also have Python doc samples. So this is the work that we have to do in Cloud Source repository. Now let's hop over to Cloud Build and go to triggers. This is where we need to create a trigger. Now, once we create the trigger, it will be able to detect the changes in the Cloud Source repository and automatically initiate a build. Right now, we are not going to create a build, but I'm going to show you how to create a trigger because the main topic is initial configuration. In the later courses, we will also see how to create a build, and we will also add an approval to that particular workflow before the build is created. So these activities are going to happen in the later demos in other courses, which are going to follow this particular course. So I'm going to go ahead and click on create trigger. Now I need to define a name. So I'm going to say SKS-Z01, and I'm going to leave the region as is. Event, I'm going to leave the default one, push to a branch, and source. Now, this is going to be first gen or second gen. Now, if you need to connect to a GitHub repository, you should select second gen. And here I am going to select my repository. Now, in case you have not configured second gen repository, it will ask you to configure that. And that is going to be a basic process of connecting to GitHub again, and from there selecting a particular repository. There is the branch, that is the main branch, and then there is the cloud build configuration file or YAML JSON file. So I'm going to go ahead and keep that as is, and then we can have the inline. Now I need to open the editor and then type the commands here. We are going to leave step as is, and then the next set of arguments that I'm going to type is GCR. So this is the basic commands we're going to have in the cloud build.yml file. So I'm going to click on done. And now there is a particular service account that if you want to select. Now, if you don't select a service account, it's going to take the default cloud build service account. So I'm going to go ahead and select this particular service account. So there are two service accounts that are there. So we are not going to select, and we are going to let it choose the cloud build service account for this particular demo. And all I'm going to do is just review the configuration once again. So there is the name, there is the region, event is pushed to a branch, it is second gen, and repository is there, the branch is there, configuration is cloud build configuration file, and it is inline YML file, which is called cloud build.yml. And we chose not to select any service account. And notice that require approval before build executes. So we will get to this in another demo later on. Now, after configuring all this, I'm going to go ahead and click create. Okay, so it seems to have a problem with the commands that I entered. So what we are going to do is we are going to go back to this editor, and I'm going to just go ahead and paste the new code or the new set of lines. And let's see, once we do that, I'm going to again try to click on create, and hopefully this time it should not throw an error. All right, so this time it has successfully created. Now this, you have to remember that YAML has to be with perfect indentation. And this was intentionally shown to you so that in case you have one space extra here and there, it is going to throw an error, which we just saw. So you need to ensure that indentation is perfect. Now, in this particular demo, what we have done is we have created the source repository, and we have also created a trigger. Now, if I click on run, it should initiate a build in the app engine. So we need to commit and push any changes to your master branch in the cloud source repository. Once we do that, Cloud Build will automatically be triggered and start building and deploying your application to App Engine. Once the build is complete, you will see a message indicating the App Engine URL where your application is deployed. So you can take that URL and you can see whether your application is actually running. With this, we have seen the initial configuration of the DevOps workflow. Scenario 1: Automated CI CD pipeline. A development team sets up a CI CD pipeline that automatically builds, tests, and deploys code changes to a production environment. Any failed test triggers notifications and rollbacks. This allows them to deliver updates more frequently, collaborate effectively, and catch issues early in the development cycle. Now, in this particular scenario, so, what are the core DevOps principles that were used? So, there was automation. Now, this pipeline replaces manual processes for building, testing, and deploying code. This reduces the potential for human error and therefore leading to more reliable and consistent deployments. Automated rollbacks upon failed tests minimize the impact of potential bugs, making it to production, increasing the overall system reliability. The another principle that was followed was continuous integration. Developers are encouraged to commit code in smaller and more frequent chunks. This leads to better collaboration as changes are integrated and conflicts are resolved sooner. The automated testing in the pipeline acts as a safety net, therefore allowing developers to receive rapid feedback on code changes and catch integration issues early. Another principle is continuous delivery. By automating the path from code commit to production ready state, the team ensures new features and updates are always ready for release. This enables faster delivery of value to customers. The rollback mechanism builds confidence, therefore, empowering the team to experiment and deploy more frequently because they have a way to quickly recover if needed. Now, overall, this scenario clearly demonstrates how DevOps principles lead to faster release cadence. There is automation and frequent integration streamline the path to delivery. There is improved quality, automated tests and early feedback help catch errors sooner, and there is greater collaboration. The CI/CD pipeline encourages a shared responsibility for code quality and a focus on customer value, which is a serverless CI/CD service. You can build triggers, flexible configuration, and you can also perform native integration with other GCP tools to streamline the build and test process. Then there is artifact registry, which is a secure repository to store build artifacts, which could be container images, packages, etc., therefore making them readily available for deployment. Then there is Cloud Deploy, which manages continuous deployment pipelines, particularly for GKE based applications, therefore ensuring a seamless rollout of changes to production. Let's now talk about scenario 2: scalable infrastructure for variable workloads. A team with a seasonal e commerce application experiences drastic workload fluctuations. They use autoscaling to automatically adjust resources based on real time demand, therefore, ensuring a positive customer experience while optimizing costs when traffic is low. So, there are certain DevOps principles that are used. So, there is automation. Autoscaling eliminates the need for manual adjustment to server capacity. The infrastructure dynamically responds to changes in load, therefore ensuring the application remains available without human intervention. This reduces operational overhead and allows teams to focus on the other tasks. Then there is cost optimization. By scaling resources down when demand decreases, the team avoids paying for idle compute capacity. This leads to a more efficient use of cloud resources and a direct impact on cost saving. Then there is customer centricity. Autoscaling ensures the application performs consistently even during unexpected traffic surges. This directly translates to a positive user experience as customers can access the site without slowdowns or errors. By preventing downtime during peak traffic, the team also protects revenue stream during critical periods. So let's now talk about how this scenario highlights the outcome of DevOps principle and what they lead to. So there is resilience. The systems can automatically adapt to changing demand, therefore maintaining availability and performance. There is cost effectiveness. Resources are used efficiently, therefore eliminating unnecessary spending. Then there is customer satisfaction, which ensures a seamless experience, therefore fostering customer loyalty and trust. Now, let's see how GCP facilitates this entire scenario. So, there is compute engine. If using virtual machines, auto-scaling groups can be configured to dynamically adjust the number of instances based on metrics like CPU utilization or request volume. Then there is Google Kubernetes Engine or GKE. For containerized workloads, GKE's cluster autoscaler can scale the number of nodes in Kubernetes cluster based on the pod resource requirements. Then there is Cloud Functions or Cloud Run. For truly event driven, highly dynamic scaling, serverless options react in real time for varying workload. Let's now talk about scenario 3, proactive monitoring and alerting. A team sets up comprehensive monitoring, therefore collecting metrics and logs across their applications and infrastructure. They configure alerts based on key performance indicators and error thresholds. This allows them to take action before problems impact users, therefore increasing uptime and improving overall customer experience. Let's see what are the DevOps principles that are used here. So there is continuous monitoring. The team doesn't wait for failures to happen. They proactively track system health indicators, therefore allowing them to identify potential issues early and prevent downtime. This leads to increased reliability and system stability. The next principle is feedback loop. Monitoring data becomes a powerful tool for optimization. This data lets the team understand performance bottlenecks, pinpoint inefficient code, or identify infrastructure weaknesses. They use this information to iteratively improve both the applications and underlying systems. Then there is shared responsibility. Monitoring breaks down the silos. Developers can see how their code performs in production, therefore enabling them to write more efficient and resilient code from the start. Operations team can understand applications requirement, therefore facilitating the creation of an infrastructure that better fits applications needs. Overall, this scenario shows how DevOps principles lead to a few benefits. So there is proactive problem solving. Issues are detected and resolved before they escalate into major outages, therefore leading to greater uptime. Then there is data driven improvement. Monitoring provides insights, paving a way for continuous optimization of code, infrastructure, and processes. There is team collaboration. A shared understanding of system health fosters collaboration between developers and operations, therefore encouraging a shared responsibility for system performance. Let's now see how GCP facilitates all this in this particular scenario. So it has several tools. So there is cloud monitoring, which collects metrics for GCP services and custom applications. You can create dashboards, set alerts based on thresholds or anomalies, and integrate with notification channels such as emails, webhooks, and PubSub. Then there is cloud logging, which is a centralized logging for visibility into application errors, events, and audit logs. You can query and analyze logs to aid in troubleshooting. Let's now talk about scenario 4, infrastructure as code for reproducible environments. A team needs to consistently provision development, testing, and production environments, therefore ensuring that configurations between them are identical. They use IAC to maintain consistency and enhance collaboration. Let's see what all DevOps principles are used here. So there is consistency, which prevents environmental drift and surprises during deployments, therefore improving reliability by ensuring that all environments are configured identically. Then there is collaboration. Infrastructure definitions become part of the shared code base, therefore fostering cross-team understanding and breaking down silos between development and operations. Then there is versioning, which helps you track infrastructure changes alongside application code changes, therefore providing a clear audit trail and ability to revert to previous configurations if issue arises. Overall, this scenario shows how DevOps principle leads to several benefits. So there is reduced deployment risks. Consistency eliminates the potential for surprises or errors. due to manual configuration differences between environments. Then there is cross team alignment. IAC promotes collaboration, therefore empowering both the development and operations team with a shared understanding of the infrastructure. Then there is auditable history. A versioned, code driven approach to infrastructure enables better tracking and rollback capability. Let's now talk about how GCP facilitates all this. So, there is Cloud Deployment Manager, which helps you define infrastructure using declarative templates that can be either YAML or Python, and this can include networks, virtual machines, load balancers, firewalls, rules, etc. Then there is integration with version control systems. Now, these templates are version controlled. For example, you can use Git for this, therefore, enabling collaboration, tracking changes, and providing a clear history of infrastructure modifications. This promotes a shared understanding across development and operations teams. Then there is repeatable deployments. Templates are used to easily replicate productions like environment for development and testing, therefore minimizing discrepancy and deployment errors. Let's now talk about scenario 5, secure deployment and access control. A team working with sensitive data designs a secure deployment pipeline. They carefully architect IAM roles and apply security controls to meet regulatory standards. So let's see what all DevOps principles that are used. So there is shared responsibility. Security becomes a fundamental concern throughout the software lifecycle, not merely an afterthought, therefore leading to a more robust and secure application. Then there is compliance. Tools and processes help the team proactively address compliance requirements and security best practices throughout the development and deployment. Then there is customer centricity. Prioritizing security helps safeguard user data, protect applications from attacks, and build trust. Overall, this scenario shows how DevOps principles lead to several benefits. So, there is proactive security. By prioritizing a secure by design approach and implementing fine grained access controls, the team minimizes security risks and safeguards sensitive data. There is enhanced compliance. GCP tools aid in meeting regulatory requirements, therefore facilitating the development of compliant applications. Then there is increased customer trust. A focus on security fosters trust and demonstrates a commitment to protecting user data. Let's see how GCP facilitates DevOps in this particular scenario. So there is Cloud Identity and Access Management, or IAM, which provides fine-grained access management across GCP resources. It enforces the principle of least privilege, therefore ensuring users and services have only the permissions they need to perform their tasks. This minimizes the risk of unauthorized access and data breaches. Then there is Security Command Center, which proactively identifies potential security issues and vulnerabilities along with remediation guidance, therefore helping the team stay compliant and ahead of threats. This continuous monitoring and assessment foster a secure by design approach. Just to quickly recap, in this particular topic, we talked about 5 different scenarios. So there was automated CI/CD pipeline, there was scalable infrastructure for variable workloads, there was proactive monitoring and alerting. Then the next scenario that we talked about was infrastructure as code for reproducible environments. And the final scenario, the last scenario that we talked about was secure deployment and access control. In this course, we talked about various different topics. So we are going to just quickly summarize that. So there was components of Google Cloud Platform, and then we talked about the process of setting up a GCP account and navigating the GCP console. Then we talked about GCP's core services, tools, and resources available for DevOps. Now let's quickly move to the next slide to look at some more topics that we covered. Then there was the role of automation in DevOps within GCP. The next thing we talked about was benefits of using GCP for DevOps projects and comparing it with other cloud platforms. And we talked about an initial GCP configuration for DevOps workflows, and we talked about 5 different DevOps scenarios and how DevOps principles help you achieve those and how GCP facilitates those scenarios. So, what's coming up next? It is designing the resource hierarchy course. Introduction. In this course, you will master the art of designing an effective resource hierarchy within Google Cloud Platform or GCP to optimize resource management, security, and operational efficiency. You will discover how to leverage projects, folders, and the powerful concept of organizations for exceptional cloud governance. Let's now talk about the course objectives. In this course, we will look at several objectives. So we will identify projects and folders in Google Cloud Platform or GCP. We'll also look at the principles for project organization, considering factors like billing, quotas, and environment separation. We will also define the GCP structure and components like organizations, folders, projects, and resources. Moving on into the course, we will list the strategies for logical grouping of resources to reflect business structure, development environments, and security requirements. Then, towards the end of this course, we'll also set up shared networking in GCP. We'll describe the identity and access management, roles, permissions, and policies in GCP. Then, towards the end of the course, we'll create a service account in GCP and then manage a service account. Concept of projects and folders in GCP. In GCP, projects and folders provide a way to organize and manage your resources. So, for example, if you talk about projects, a project is a fundamental unit of organization within GCP. It serves as a container for all the resources you use to build, deploy, and operate your applications. These resources can include compute instances, cloud storage buckets, cloud functions, and many other resources. So each project in GCP has a unique ID and name. Resources can belong to only one project at a time. When you create resources in GCP, they are associated with a specific project. Each project has its own settings for resources, billing, and permissions. Billing is done at the project level, and projects can have identity and access management policies to control access to a project's resources by defining roles and permissions for users and service accounts. Projects also enable you to isolate specific concerns and manage resources independently for different teams, departments, or applications. Let's now talk about folders. Folders are an optional layer of an organization that help you group related projects together. They are particularly useful for large organizations with many projects. Folders can contain projects and other folders, therefore create a hierarchical structure within GCP organization. Folders help you organize and manage projects based on organizational structure, business units, or departments. Folders are not mandatory, they are optional. A project can exist on its own without belonging to a folder, and folders themselves cannot hold resources directly. The resources have to belong to a particular project. Now, folders provide a convenient way to apply policies, budget controls, and billing settings to a group of projects collectively. So, if you have multiple projects and you put them in folder, you can apply the set of policies, budget controls, or billing settings to that particular folder, and therefore, any project within that particular folder will have those policies applied. And you can also set the identity and access management policies at the folder level to apply them to all child projects that belong to that particular folder. Folders inherit identity and access management policies from their parent folder or organization, therefore allowing you to manage access control centrally and consistently across multiple projects. You can create a folder hierarchy with multiple levels, therefore allowing you for granular control and delegation of permissions. Let's now talk about the analogy of projects and folders. So, here is an analogy to understand the relationship between projects and folders. Think of a project as a department within a company. It has its own employees, which are resources, and budget, which is basically the billing. Folders are like regional offices. They group related departments, which are project in our case, together for better organization and potentially shared policies. Let's now talk about benefits of projects and folders. So there is scalability. The hierarchical nature of folder allows for seamless scalability. As your organization's need grow, you can easily add new projects and nest them within the existing folders. This ensures that even a large cloud environment remains well structured and manageable. Then there is billing and cost management. Each project has its own billing account, therefore enabling you to track costs associated with specific group of resources independently. This detailed tracking facilitates accurate cost allocation, budgeting, and optimization efforts. You can monitor resource usage at the project level and make informed decisions about resource allocation. Then there is organization. The projects and folders create a hierarchical structure to organize your GCP resources. This makes it easier to manage, locate, and track specific assets within your cloud environment. You can group related resources into projects and then further organize these projects into folders, therefore aligning with your organizational structure or specific use cases. Then there is policy inheritance. Identity and access management and organization policies can be applied at the folder level and inherited by all projects within that folder. This simplifies policy management and ensures consistent governance across resources. Then there is security of resources. Projects act as isolation boundaries, therefore separating resources and their associated configurations from one another. This prevents unintended interactions between different parts of your infrastructure, enhances security, and simplifies troubleshooting. Then there is access control. Granular access control is achieved through identity and access management policies, which can be applied at both the project and folder levels. This allows you to precisely define who can access, modify, or delete resources, therefore, enhancing security and ensuring compliance with internal and external regulations. Just to quickly recap, in this particular topic, we talked about projects, what they are. We also talked about folders. We also discussed an analogy of projects and folders. And then we talked about several benefits of projects and folders. Principles for project organization. Now let's look at the principles for project organization in GCP, starting with billing management. Now, there are several factors that come into play when you talk about billing management. So, there is project granularity. Maintaining separate projects for different applications, teams, or cost center allows for clearer cost attribution and budget tracking. Then there is billing accounts. Associating each project with a specific billing account offers flexibility for different spending limits or funding sources. Then there is alerts and budgets. Setting up billing alerts and budgets for each project helps monitor spending and prevent unexpected charges. Then there is cost allocation tags. In addition to billing accounts, you can use cost allocation tags to label resources and gain even more granular insights into your spending patterns across different teams, services, or environments. This allows for more detailed cost analysis and optimization. Let's now talk about quota management. The next principle for project organization is quota management. So there is resource isolation. Isolating resource usage by project prevents one project from impacting another by exhausting quotas. Then there are project quotas. Monitoring project level quotas for resources such as compute engine instances or cloud storage capacity is essential for resource management. Then there is requests for quota increases. Requesting quota increases for specific projects based on their resource demands ensures sufficient capacity for operations. Then there is resource monitoring. Regularly monitor project level quota usage to identify potential bottlenecks or underutilization. GCP provides tools like cloud monitoring and billing reports to track resource consumption. Then there are custom quotas. In some cases, you may need to request custom quotas for specific services or resources that exceed the default limits. This can be done through GCP console or API. Let's now talk about environment separation. So there is separate development, staging, production projects. Creating separate projects for development, staging, and production environments ensures rigorous testing before changes reach production and protects sensitive data. Then there is feature branches. Using separate projects for feature branches during development isolates deployments and resource utilization. Then there is short-lived environments. Exploring cloud functions or serverless options for short-lived environments ensures efficient resource utilization. Then there is shared services. Consider using a shared services model where common resources such as networks, load balancers, or databases are deployed in separate projects and shared across the development, staging, and production environments. This model can improve resource utilization and cost efficiency. Let's now talk about the additional considerations. There is naming conventions. Using clear and consistent naming conventions for projects and folders improve their organization and searchability. Then there is IAM or Identity and Access Management Policies. Leveraging identity and access management policies at both project and folder levels controls access and permissions for different users and teams. Then there is project lifecycle management. Establishing a process for managing project life cycles, including creation, deletion, or archival of inactive projects, ensures efficient resource utilization and cost management. Then there are organization policies. Beyond the identity and access management policies, GCP also offers organization policies that allow you to enforce constraints on resource configurations and usage across your entire organization. This helps maintain consistency and governance. Then finally, there is cost optimization. Regularly review your resource usage and consider cost-saving measures such as committed use discounts, sustained use discounts, or custom machine types for compute engine instances. Just to quickly recap, in this particular topic, we talked about principles for project organization, we talked about billing management, quota management, environment separation, and we also talked about the additional considerations in which we did talk about naming conventions, identity and access management policies, project lifecycle management, organization policies, and cost optimization. Organizations, folders, projects, and resources. Now let's talk about the components of GCP, namely organizations, folders, projects, and resources. Let's start with organizations. It is the top level resource. The organization node is the root of the GCP resource hierarchy. Organizations represent companies, large departments, or other broad entities. Let's now talk about the benefits of organizations. You can centralize your identity and access management control across all GCP resources within an organization. You can consolidate billing and aggregate reporting. You can also have the ability to structure resources hierarchically for complex setups. Let's now talk about folders. It is a subdivision within an organization. Folders provide an additional layer within an organization. You can use them to group related projects. But like we discussed earlier, folders are optional. You don't need to have them. But if there is a need to club multiple similar projects, you can use folders and group them together within that particular folder. So there are several benefits of using folders. You can have granular identity and access management policy inheritance. Policies can be set at the folder level and they will flow down to the projects. You can also have logical grouping for better management, especially in the large organizations. Then there are projects, which is the core building blocks. Within folders, projects are the fundamental units where work is done in GCP. Now, important thing to note is that if there are no folders, projects can still exist independently within an organization, or they can even be outside the organization if, for example, as an individual entity, you have created an account in GCP, you can still create projects. But when we are talking in the context of organizations, then they will fall within that particular organization. So projects have different components. So there are resources. Projects contain actual GCP resources that you use. So for example, there could be virtual machines, databases, cloud storage buckets, and many different kind of other resources. There can be identity and access management policies. Each project has identity and access management policies that control access and permissions for users and service accounts. You can also have the billing for resource usage at the project level, and you can track that resource usage and bill them at the project level. The last one is resources. Within a project, resources are the individual components you use to create applications and services within GCP. Now, these resources could include compute. So there could be compute engine virtual machines, there could be Kubernetes clusters, there could be cloud functions or cloud run. Then there is storage. It could include cloud storage buckets, cloud SQL databases, and big table instances. Then there could be networking, which could have VPCs, load balancers, and DNS. There could also be big data and analytics. So you could have BigQuery, Dataflow, and PubSub. And then it could also be artificial intelligence and machine learning or AI ML. So you could have the AI platform, pre-trained ML models, and TPUs for training. Let's now look at the organization. So we briefly talked about what organization is. So we are going to talk a little bit more about the organizations. Organizations are the highest level of hierarchy in GCP. They represent the top level entity that contains all GCP resources associated with an entity, such as a company or an institution. Organizations serve as the root nodes for the hierarchical structure and provide centralized management and governance across all resources within the organization. An organization is associated with a billing account and serves as a billing entity for all projects and resources within it. Let's now talk about folders. We did speak about folders earlier in this topic. Let's go into a little bit more depth. Folders are used to organize resources within an organization into hierarchical groupings. They provide a way to logically group projects and resources based on organizational structures, business units, or departments. Folders can contain other folders or projects, therefore creating a hierarchical tree-like structure. They inherit identity and access management policies from their parent folder or organization, therefore allowing for consistent access control and management across resources. What it is trying to say is if you have a folder and then there are more folders within that folder, whatever policy you apply at the parent folder level, the subfolders or the folders contained within that parent folder will all inherit those policies. This is what it means. Let's now talk about projects. Projects are containers for resources in GCP and represent a logical grouping of related resources. Each project has its own set of resources, permissions, and settings, which can include billing, identity and access management policies, and APIs. Projects serve as a unit of isolated resources, therefore allowing teams to work independently and manage resources separately from other projects. They are typically used to organize resources for specific applications, environments such as development, testing, or production, or even teams. So, for example, you could create multiple projects. One could be for one specific team, one could be for development team, another one could be for staging, and then one can be for testing team. Now, whatever resources they are using within their projects, they are going to be isolated. So, for example, the development team resources will not interfere with the testing team resources. Let's now talk about resources. Resources are individual components and services hosted within GCP projects. They include virtual machines, storage buckets, databases, networking components, and various other GCP services. Resources are created and managed within projects and can be organized and accessed based on projects and folder hierarchy. Each resource is associated with specific configurations, access controls, and usage metrics, and they interact with each other to deliver functionality and services. So, for example, you could have multiple resources. There could be a virtual machine, there could be storage. Now, the virtual machine can use that particular storage, and all these resources are located within one particular project. Just to quickly recap, in this particular topic, we talked about organizations, folders, projects, and resources. Strategies for logical grouping of resources. Resources can be logically grouped to reflect business structure, development environments, and security requirements in GCP. So let's go ahead and start with strategies based on business structure. So there is project per department. You can group resources relevant to a specific department, for example, marketing, HR, or finance, within separate projects. What this means is you can have a project for marketing, another one for HR, and another one for finance. This improves billing clarity and aligns with organizational silos. So once you do this, you would know how much HR department is spending, how much finance department is spending, and how much marketing department is spending. You can also create projects per application. You can dedicate a project to each major application or service. This helps manage dependencies and isolates impact zones. Then there are project per business unit. For large organizations with distinct business units, creating separate projects for each unit aids in cost tracking and management autonomy. Let's now talk about strategies for development environments. So, there are projects for development, staging, and production. There are separate projects for different environments. This ensures strict isolation and helps streamline the deployment process. Then there are projects per feature branch. For projects with active feature development, you can consider temporary projects aligned with major feature branches. This supports parallel development and testing without disrupting the main environments. Now, feature-based development and testing allows team to iterate quickly and release new features with confidence. Let's now talk about strategies for security requirements. So there is grouping projects based on sensitivity. You can group resources based on data sensitivity or compliance requirements. Projects with highly sensitive data can have strict identity and access management policies and network isolation. Then there is grouping projects by trust level. You can maintain separate projects for internal workloads versus externally facing services to manage the attack surface. Then there is grouping by security zones. You can divide resources into security zones based on their sensitivity and security requirements. For example, you can create separate projects or folders for public facing services, internal applications, and highly sensitive data. Within a project, you can use folders to group resources based on security levels and apply identity and access management policies. For example, a folder for production workloads with restricted access versus a folder for development resources. Then there is grouping by compliance requirements. You can organize resources to comply with regulatory or compliance requirements such as HIPAA or GDPR. You can ensure that resources related to sensitive data are isolated and subject to appropriate access controls and auditing. Let's now talk about the additional considerations. So there is network design. You can plan VPCs and subnets strategically. You might segment networks based on business functions, environments, or security needs. Then there is access control or identity and access management. You can combine project level and folder level identity and access management for granular control. You can consider the principle of least privilege. Then there is labeling. You can use labels liberally on resources to categorize them for search, filtering, and billing analysis across different groupings. Now, one of the key points is that there is no single perfect grouping strategy. The ideal approach depends on the size and complexity of your organization, application architecture, and compliance requirements. You should balance the need for organization with the overhead of managing a complex project structure. Just to quickly recap, in this particular topic, we talked about the strategies for logical grouping of resources. We talked about strategies based on business structure, strategies for development environments, strategies for security requirements, and then we also talked about additional considerations like network design, identity and access management, and labeling. Setting up shared networking. Now that you are aware of GCP concepts and resource organization, let's take a look at shared networking in GCP. Shared Virtual Private Cloud or VPC is a fundamental concept in GCP networking that enables you to connect resources from multiple projects to a common VPC network. Now, these projects are of two types. So, there is a host project, which is the GCP project designated as the host owning the shared VPC network. Then there are service projects, which are the GCP projects that attach to and utilize the resources of the shared VPC network. Let's now talk about the benefits of shared VPC. So there is centralized network management. Administrators manage a single VPC network in the host project, therefore simplifying network design, firewall rules, routes, and IP addressing. Then there is seamless resource communication. Compute instances, load balancers, and other resources across different projects can communicate privately using internal IP addresses as if they were all part of the same extended network. Then there is isolation and security. Shared VPCs enforce project boundaries for administrative tasks. Even though resources share a network, project owners retain control over their resource management and security policies. Let's now talk about setting up a shared VPC. So, there are different steps that you would need to follow. You start with creating a host project. You need to designate or create a project to act as a host for your shared VPC. Then you create a shared VPC network. Within the host project, you need to create a VPC network with subnets in the desired regions. The subnet configurations will define the IP ranges available to resources across attached projects. Then you grant permissions. In the host project, you allow designated service projects to attach to the shared VPC network by using identity and access management permissions. Then you attach service projects. In each designated service project, you need to attach the necessary subnets from the shared VPC. And finally, you configure resources. You can create virtual machines, Kubernetes clusters, or other resources within service projects using the attached subnets. Let's talk about the additional considerations for a shared VPC. So there is shared VPC admin. A special identity and access management role exists to grant cross project administrative privileges specifically for a shared VPC network. Then there is custom subnet modes. A shared VPC supports both auto mode and custom mode subnets, therefore providing flexibility in how IP addresses are allocated. Then there is no support for legacy networks. Legacy networks do not support shared VPC configurations. So, therefore, whenever you are trying to work with a shared VPC, you need to basically know these considerations so that you are aware. Let's not talk about the best practices for securing a shared VPC. There is a principle of least privilege. You should carefully manage identity and access management roles and permissions for both shared VPC administration and resource access within the shared network. Then there are firewall rules. You can implement well defined, granular firewall rules to control traffic and isolate resources within the shared network as needed. Then there is network segmentation. You can use subnets intelligently to further divide your shared VPC and enhance network security. Just to quickly recap, in this particular topic, we talked about what a shared VPC is. We talked about the host project and the service project, and then we talked about the benefits of using a shared VPC. We also talked about setting up a shared VPC in which we create a host project, we create a shared VPC network, grant permissions, attach service projects, and configure resources. Then we talked about the additional considerations for a shared VPC. And then finally, we talked about the best practices for securing a shared VPC. In these best practices, we did mention principle of least privilege, firewall rules, and network segmentation. Identity and Access Management, or IAM. Identity and Access Management, or IAM, is a GCP security mechanism. You can call it the gatekeeper for GCP resources that controls who or what can access and perform actions on GCP resources. It provides a centralized and comprehensive approach to manage permissions across GCP environments, therefore, ensuring that only authorized users and services have necessary access levels. Identities define who, permissions define what, roles define how, and policies define where. In GCP, identity and access management serves as the primary security mechanism responsible for controlling access to GCP resources. And we are going to talk about identities, permissions, roles, and policies in the upcoming slides. Let's talk about identities. Identities represent entities such as users, service accounts, or groups within GCP. They are the cornerstone of identity and access management, defining the who aspect of access control. Identities encompass a wide range of entities from individual users within Google accounts to automate processes represented by service accounts. By defining identities, identity and access management establishes the basis for access control within GCP. It helps you determine who has access to what resources. Identities define the who aspect of IAM, therefore determining who has access to what resources. Let's now talk about permissions. Permissions specify what actions an identity can and cannot perform on GCP resources. These actions can include read, write, create, delete, and modify, among many other permissions depending on the type of resources and the level of access requires. So these are basically individual set of privileges that are assigned to an entity. IAM provides a robust set of predefined permissions that can be assigned to entities, therefore ensuring fine-grained control over resource access. So in short, permissions basically do nothing but they indicate the allowed or restricted actions that an entity can perform. So these are individual privileges that you would specify the type of action that a user or maybe a service account can perform on a particular resource. So for example, you can allow a user to create another user, but then you may not allow that user to have permission to modify any kind of storage buckets or a vice versa. So there are different permissions that you can assign to a particular user. Now, there are roles that you would typically assign to a particular entity, but we are going to get to those roles later on. And now when you're talking about these permissions, they can be assigned at a granular level to control access to individual resources or grouped into roles for easier management. So this is what we just talked about, that ideally you should be assigning different roles to different entities, but there are times when you would have to assign specific permissions. So we are going to look at roles in the upcoming slide. Now let's talk about roles. In the previous slide, we talked about permissions, which are individual privileges. Now roles are bundled together and they are the collection of permissions. They define how a person is going to be assigned a certain set of permissions. So roles determine the set of actions that an identity can perform within a specific scope, such as project, folder, or organization. For example, administrator has the complete control. So there are certain default permissions or the roles that are going to be assigned to that particular administrator. Now, you may have another user or entity named John. You may allow only view permission on certain resources, but not allow John to modify that particular resource. GCP offers a variety of predefined roles tailored for common use cases, ranging from basic roles such as owner, editor, and viewer to very specific and specialized role for GCP services such as compute engine admin or storage object viewer. Now, these are predefined roles that exist. But if you need to create any specific custom role, you can do that also. You can assign specific set of permissions in that particular role and assign that role to an entity. So that can also be done. But before you create something custom, you should scan and figure out whether a similar role does exist within the GCP environment or not. Roles follow the principle of least privilege, therefore, granting the minimum permissions necessary for an identity to perform its job effectively without minimizing the risk of unauthorized access or misuse. So, when we are talking about these predefined roles, they do act on the principle of least privilege. So, you would have the bare minimum set of privileges or the permissions to perform a specific task. So, there would be storage admin or there would be any other admin like compute engine admin, but these entities who have this particular role, they will be able to perform that particular task only. So for example, a compute engine admin cannot be a storage object viewer if that permission or that role is not assigned. Let's now talk about the policies. Policies are the set of rules or configurations that dictate access control decisions within the cloud environment. They define who can do what. So, this means what an identity can do or what an identity can perform a certain action on which resources. So, there are three critical components in a policy: who, what, and which resource. Who is the identity? What is the action? And which is the resource? So the policies are the where aspect of identity and access management, specifying where access controls are applied and enforced within the cloud infrastructure. Now, these policies are written in the JSON format and attached to GCP resources such as projects, folders, or individual resources to control access at different levels of the resource hierarchy. Identity and access management policies consist of bindings which map members such as users, service accounts, or groups to roles, therefore effectively granting those members the permission associated with the roles. When a user or service account attempts to perform an action on a resource, GCP evaluates the applicable identity and access management policy to determine if they have the necessary permission and enforce access control decisions. Now, if a user or the service account has that particular permission, the access will be allowed, otherwise, the access will be denied. Let's now look at the example of IAM policy. In this example, the policy grants the storage object viewer role permission to view objects in cloud storage to both the user Alice at example.com and service account myapp within my project. Let's now talk about the key considerations. So there are certain key considerations that you would need to apply when you are working with the identity and access management. So you start with predefined roles. GCP provides a wide range of predefined roles that cover common use cases. Now, in case you need a role that does not exist or is not predefined, then you create custom roles, but you need to do it carefully because permissions are going to be critical. You don't want to grant more than required permissions. So you would need to have granular control, and you would need to basically follow the principle of least privilege. You should regularly review and revoke access. You should periodically review your IAM policies and remove unnecessary access to maintain security. Now, this is not one-time task. Like it says, regularly. You would need to continuously and regularly, on a defined interval, you should sit down and review these policies. You should review these policies. You should review the roles and see, for example, if John has quit the organization, you have deleted his account, but that role will still be there. So if that role was created specifically for John, maybe you don't need it anymore. So go ahead and delete that role. You should use service accounts for applications. Now, there are typically two types of accounts. So there are user accounts and there are service accounts. User accounts are meant for users, and there are service accounts which are meant for applications to use. So when your application needs to interact with GCP services, you should use service account to grant them the required permissions. You should not use the user accounts. Let's now talk about working IAM elements. So there are certain steps that are performed when the elements of IAM are in practice. So there are user or the identity initiates an action, GCP checks the policies and roles, permissions are evaluated, and the permission is granted or denied based on the privileges that you have. So let's start with user or identity initiates an action. A user represented by an entity within GCP, such as a Google account, attempts to perform a specific action, such as viewing data in a BigQuery table. This action could be initiated through GCP console command line interface, or it could be via an API call. Then, once user initiates the action, GCP checks policies and roles. When the user attempts the action, GCP evaluates the permissions associated with the user identity. It checks the policies attached to the resource being accessed as well as the roles assigned to the user. Then the next step is permissions are evaluated. If the user's role include a role that grants the necessary permission for the action on the resource, the action is allowed. GCP verifies that the user's assigned role have permissions required to perform the requested action. For example, if a user has been assigned the role of BigQuery data viewer, which includes the permission to view data in BigQuery tables, the policy attached to the table permits users with this role to view data. The user is authorized to view the table's data. Then permission is granted or denied. If the user's role does not include permission for the action on the resource, GCP denies the action. The user is informed that they lack the necessary permissions to carry out the requested operation. Let's now talk about the use cases of identity and access management, or IAM. So the first one is controlling access to resources. IAM allows you to restrict access to various GCP resources such as virtual machines, databases, and data stored in cloud storage by specifying who can create, edit, or delete them. For example, you can create IAM policies that grant specific users or groups the permission to create virtual machine instances while restricting others from modifying or deleting the existing instances. This fine-grained control over resource access helps organizations enforce security policies and prevent unauthorized modifications or deletions, thereby safeguarding critical infrastructure and data. The next use case is managing user roles. IAM enables you to manage user roles by assigning predefined roles provided by GCP or creating custom roles tailored to specific responsibilities within your organization. Predefined roles such as BigQuery data viewer comes with a predefined set of permissions suitable for common use cases. These roles can be assigned directly to users or groups to grant them access to specific resources or services. As a guideline, you should always look for predefined role. If none meets your requirement, then you should create a new custom role. Additionally, custom roles can be created by selecting the necessary permissions from a comprehensive list and defining roles binding to assign these roles to users or groups based on their responsibilities or job functions. By managing user roles effectively, organizations can ensure that users have the appropriate level of access required to perform their tasks efficiently while adhering to the principle of least privilege. The next use case is enforcing security policies. IAM serves as a critical component for enforcing security policies within GCP environments, therefore enabling organizations to implement security best practices such as the principle of least privilege, which dictates that users should only be granted the minimum permissions necessary to perform their job responsibilities effectively. By leveraging IAM, organizations can enforce this principle by carefully assigning roles and permissions to users, therefore ensuring that they have access only to the resources and actions required to fulfill their duties. IAM also allows organizations to implement their other security measures such as multi-factor authentication and role-based access control to further enhance security posture and protect against unauthorized access or data breaches. The next use case is automating access control. Integration of IAM with automation tools enables organizations to automate access control processes and dynamically manage permissions based on workflows and events. For example, organizations can utilize tools like Google Cloud Functions or Cloud PubSub to trigger IAM policy updates in response to changes in the resource configurations or user roles. Automation helps streamline access management workflows, reduces manual overhead, and ensures that permissions are consistently applied and updated in accordance with organizational policies and requirements. By automating access control, organizations can enhance operational efficiency, enforce security policies more effectively, and adapt to changing business needs and resource requirements in real time. Just to quickly recap, in this particular topic, we talked about the identity and access management. We talked about identities, permissions, roles, and policies. Then we also looked at the example of an IAM policy, and then we looked at the key considerations. We talked about certain considerations such as start with the predefined roles or creating custom roles carefully. Then we talked about the working IAM elements, how this IAM process works basically. When a user initiates an action, GCP checks for policies and roles, permissions are evaluated, and then permission is granted or denied. Then, towards the end, we talked about certain use cases of IAM. Service account in GCP. A service account in GCP is a special type of Google account that represents a non-human identity, such as an application or a virtual machine, rather than an individual user. Service accounts are used to authenticate and authorize applications and services to interact with GCP resources programmatically without the need for human intervention. Let's look at the reasons why service accounts are required and what are their key features. So first one is the automation and programmatic access. Service accounts are essential for automating tasks and enabling programmatic. They allow applications and services to interact with GCP APIs and services, perform actions, and manage resources on behalf of the users and other systems. Then there is authorization. Service accounts are associated with roles and permissions within IAM in GCP. This means the access to GCP resources via service accounts is governed by IAM policies, therefore ensuring only authorized actions are performed. Then there is security. Service accounts help enhance security by providing a dedicated identity for applications and services. Each service account is associated with a unique cryptographic key pair, which can be used for secure authentication and communication with GCP services. Then there is least privilege. Service accounts follow the principle of least privilege, meaning that they are granted only the minimum permission necessary to perform their intended tasks. This reduces the risk of unauthorized access and minimizes the potential impact of security incidents. Then there is resource allocation. By using service accounts, organizations can isolate the access and activities of individual applications or services and enhance accountability and control over resource usage. Overall, service accounts play a crucial role in GCP by enabling secure and controlled access to resources. They also adhere to best practices in identity and access management. Let's now talk about the service account versus normal user account. The table on the slide highlights the key differences between the service account and normal user accounts in GCP, therefore emphasizing their respective purposes, authentication methods, mode of interaction, permission management, and the lifecycle management. Let's talk about the purpose first. A service account represents applications or services that require programmatic access to GCP resources. On the other hand, normal user account represents human users who interact with GCP resources through web consoles or even the command line interfaces or CLI. Then there is authentication. Service account primarily uses key pairs or OAuth 2.0 tokens for authentication, therefore allowing automated processes to authenticate without human intervention. On the other hand, normal user account is typically authenticated using a username password combination along with additional security measures such as two-factor authentication or 2FA. Then there is interactions. Service account interacts with GCP resources via API calls, software development kits or SDKs or other automation tools. On the other hand, normal user account interacts with GCP resources through web consoles, CLI tools, or other user interfaces that require manual input and interactions. Then there is permission management. Service account provides more granular control over individual actions, therefore allowing fine-tuning of permissions for specific tasks or workflows. On the other hand, normal user account often has broader permissions tied to job roles or responsibilities, therefore granting access to a wide range of GCP resources and services. Then there is lifecycle. Service account is created and deleted as needed to support automation and application requirements. Its lifecycle is typically managed through programming. On the other hand, normal user account is managed by IT administrators or the users themselves, and its lifecycle may be tied to organizational policies, employee status, or user preferences. Let's now talk about the use cases of a service account. A service account can be used in various situations, so we are going to talk about some of these use cases. So there is compute engine instances. Service accounts are commonly used with compute engine instances to grant them access to other GCP services such as cloud storage or BigQuery for tasks like reading, writing, or processing data. When creating a compute engine instance, you can specify a service account to associate with the instance. This service account acts as the identity for the instance when it interacts with other GCP services. By assigning appropriate roles and permissions to the service account, you can control the level of access granted to the compute engine instance, therefore ensuring that it can perform its intended tasks securely and efficiently. Then there is cloud functions. Service accounts play a crucial role in enabling cloud functions to trigger other GCP services or manipulate data within a project. Each cloud function is associated with a service account which determines the permissions available to the function when it interacts with other GCP resources. By configuring the appropriate roles and permissions for the service account associated with a cloud function, you can ensure that it has the necessary access to perform its designated actions, such as reading from or writing to cloud storage, invoking other cloud functions, or interacting with databases like BigQuery. Then there are custom applications. Service accounts can be used to authorize custom applications running outside of GCP to securely access and interact with GCP resources. To integrate a custom application with GCP services, you can create a service account and generate a set of credentials such as a JSON key or OAuth 2.0 access token, which application can use to authenticate itself to GCP APIs. By assigning appropriate roles and permissions to the service account associated with the custom application, you can control the scope of actions it can perform within GCP, therefore ensuring that it adheres to the principle of least privilege and only accesses the resources necessary for its functionality. Then the next use case is data processing workflows. Service accounts are integral to enabling automated data processing workflows in GCP, therefore allowing data pipelines to transfer and transform data between different GCP services seamlessly. In data processing workflows, service accounts are used to authenticate and authorize the various components involved in the pipeline, such as data ingestion tools, data processing frameworks, and storage services. By granting appropriate roles and permissions to service accounts associated with each component, you can orchestrate complex data processing tasks securely, therefore ensuring that sensitive data is accessed and processed only by authorized entities. The last use case is CI/CD pipelines. Service accounts are instrumental in automating build and deployment processes within CI/CD pipelines by granting them access to the necessary GCP resources. In CI/CD pipelines, service accounts are used to authenticate and authorize the CI/CD tools such as Jenkins, GitLab CI/CD, or Cloud Build to interact with GCP services for tasks like building container images, deploying applications, or running tests. By configuring the appropriate roles and permissions for service accounts associated with CI/CD tools, you can ensure that they have the requisite access to perform their designated actions securely and efficiently, therefore facilitating streamlined and automated software delivery processes. Just to quickly recap, in this particular topic, we talked about what a service account is and what are its key features. We also differentiated between a service account and a normal user account. And then we talked about various use cases of a service account. So, for example, we talked about compute engine instances, cloud functions, custom applications, data processing workflows, and CI/CD pipelines. And basically, in these use cases, we did talk about how service accounts are used. Summarize the process of creating and managing service accounts. Now, there are service accounts that you can use with services and compute resources like virtual machines. So these service accounts are not meant to be used by the users. So whenever you need to configure an application and it needs an account, you would rather use a service account than a user account. So therefore, you can configure a service account in IAM or identity and access management. So you need to create it first and then you need to manage these service accounts. So let's go ahead and get into IAM and admin. Now, once you are in IAM and admin, notice that in the left pane, there is something called service account. So I'm going to just go ahead and click on this, and then it shows currently there are no service accounts in this project called SKS 001. So I need to click on this option called create service account. And it's a pretty straight, simple process. You don't have to do a lot of configuration or anything like that. All you need to do is give a name to the service account. So for example, if I say storage SKS storage admin. All right. So this is the service account. Now I can also give a description, but notice that service account ID, it automatically takes it up from the service account name. So I'm not going to just add any description, but in real life scenarios, you should provide a service account description. So what I'm going to do is I'm going to just go ahead and click on create and continue. So this starts the process of creating a service account. Now this particular service account is created. And now what we need to do is get on to the next step, which is grant this service account access to project. Now I need to select a role. So to be able to do that, I need to click on select a role dropdown. But notice that it says it's an optional step. So for the time being, you can skip this particular step, but let's go ahead in any case and select a service role. So what I'm going to do is I'm going to type storage, and now I need to basically select a particular role. So what I'm going to do is compute storage admin is what I'm going to assign to this particular service account. And then I need to click continue. And before we do that, there is add another role. So I can add multiple roles just like I would do to a particular user account. But for the time being, we are just going to skip that and we are going to click on continue. Now, this is another optional step, which is grant user access to this service account. So for example, I need to just type a name and I need to select service account admin role. So for the time being, we can just go ahead and skip that. We don't need to do that. And I'm going to go ahead and click done. All right. So this SKS storage admin service account is now created. Now, status is enabled. Name is SKS storage admin. There is no description. There is no keys that are assigned. Obviously, since there are no keys, there are no key creation date. And OAuth to client ID is this. Now, if I click on these three dots, which is the actions, I can do all these activities. I can manage details. I can manage permissions, manage keys, view metrics, view logs, disable this particular service account or delete it. Now, there is a fundamental difference between disable and delete. Now, if I disable it, I can enable it and reuse this particular service account. But if I delete it, I can't use it anymore. This will be deleted. So therefore, we have to choose if we want to disable or delete very carefully. So in short, just to recap, now we created a particular service account and we also talked about the actions that we can perform for managing this particular service account. Course summary. In this particular course, we talked about projects and folders in GCP. We talked about the principles for project organization and components within the GCP structure. And then we talked about strategies for logical grouping of resources. Let's move to the next slide and look at some of the more topics that we did discuss within this particular course. Continuation from the previous slide, let's look at some more topics that we did talk about in this particular course. So we did talk about setting up shared networking. We did talk about identity and access management or IAM in GCP. And towards the end, we did talk about what a service account is, the differentiation between service account and normal user account in GCP. And then we also did talk about creating and managing service accounts. So what's coming up next? It is the course on infrastructure as code or IAC and its tools in GCP. In this course, you will learn to define infrastructure as code or IAC principles, understand the concept of immutable architecture, and discover powerful IAC tools compatible with Google Cloud Platform or GCP, including Terraform, Helm, and Config Connector. You will gain practical experience implementing IAC on GCP and explore best practices through examples and case studies. Let's now talk about the course objectives. In this course, you will learn to define infrastructure as code or IAC. You will also learn the principle of immutable architecture in cloud environments. And then you will also learn the relationship between IAC and immutable architecture in the cloud environment. Moving on into the course, you will learn to identify the key IAC tools compatible with GCP. And then moving on, you will also learn about the steps for making infrastructure changes using Cloud Foundation Toolkit. Towards the later part of the course, you will learn to compare Terraform, Helm, and Config Connector for GCP ISE solutions. Towards the end of the course, you will learn to use the Terraform for deploying GCP resources and then GCP's best practices for infrastructure as code. You will also analyze a case study of implementing ISE in a GCP project. Define infrastructure as code or IAC. Infrastructure as code or IAC is an approach to manage and provision computing infrastructure through machine readable configuration files or scripts rather than manual processes. It allows developers and operations teams to define and deploy infrastructure resources such as virtual machines, networks, and storage in a repeatable and automated manner. With IAC, infrastructure configurations are expressed as code, typically using declarative or imperative programming languages such as YAML, JSON, or domain-specific languages like HashiCorp Configuration Language or HCL. These configuration files define the desired state of the infrastructure, including its topology, properties, and dependencies. By treating infrastructure as code, organizations can leverage version control systems such as Git to track changes, collaborate on configurations, and maintain a history of infrastructure modifications. This enables reproducibility, consistency, and traceability of infrastructure deployments, therefore facilitating agile development practices and ensuring that infrastructure changes are predictable and auditable. IAC also promotes automation by allowing infrastructure provisioning processes to be automated through continuous integration and continuous deployment or CI/CD pipelines. This streamlines the deployment life cycles, reduces manual errors, and accelerates the delivery of applications and services. That's essentially what IAC does for computer systems. Instead of manually setting up servers, networks, and other components by clicking buttons and typing commands, you simply write the code that describes your entire infrastructure. So this, in nutshell, means that you don't have to do any kind of manual provisioning. You simply take the configuration file or the script, you run it, and you can repeatedly set up the same infrastructure. Let's now talk about the recipe for cloud resources. Think of IAC as a recipe for your cloud resources. So you have ingredients, which are the building blocks of your system, which could be servers, databases, and storage. And then you have instructions, which is the code you write that defines how these ingredients are put together, which means how many servers, how they connect, and what software runs on them. Let's now talk about the benefits of IAC. So there is reproducibility. You can use an existing script to recreate the same infrastructure without any manual intervention. It is like making multiple copies of the same infrastructure. Then there is consistency. You get the same result every time you set up your infrastructure, therefore eliminating errors caused by manual setup. Then there is speed. You automate the process that makes it much faster to set up new environments or replicate existing ones. Then there is collaboration. ISE code can be stored in version control systems like Git alongside your application code. This makes it easier for teams to work together, review changes, and roll back if something goes wrong. Then there is scalability. IAC makes it simpler to create large complex systems because you are managing code instead of manual configurations. Then there is cost control. By automating provisioning and deprovisioning, you can ensure that you are only paying for the resources you actually need. Let's now talk about the benefits of IAC for DevOps. So there is enhanced collaboration. IAC encourages collaboration between development and operations teams as infrastructure definitions become part of the code base. This improves communication and breaks down traditional silos. Then there is increased speed and efficiency. Automating infrastructure provisioning and management reduces manual errors and speeds up deployment times significantly. Then there is improved reliability. IAC ensures consistent environments across deployment, testing, and production, therefore, leading to fewer surprises and smoother deployments. Then there is cost saving. Automating the management of resources can optimize resource usage and reduce cost. Cost can be reduced at different fronts. So, one, you need less manpower. Second, there are less number of errors, which means the DevOps team can spend their time into building more systems or building more applications rather than fixing errors. Now, just to quickly recap, in this particular topic, we defined what infrastructure as code or IAC is. We also talked about the recipe for cloud resources, which includes ingredients and instructions. Then we talked about some of the benefits like reproducibility, consistency, speed, collaboration, scalability, and cost control. And then towards the end, we talked about the benefits of IAC for DevOps, which includes enhanced collaboration, increased speed and efficiency, improved reliability, and cost saving. Discuss the principles of immutable architecture in cloud environments. Immutable infrastructure is a design approach in cloud computing where infrastructure components such as servers, containers, or virtual machines are created in the state that cannot be modified after deployment. Once provisioned, these components remain unchanged throughout their life cycle, and any updates or changes are implemented by replacing them with entirely new instance rather than modifying existing ones. This ensures consistency, predictability, and reliability in the deployment and management of cloud infrastructure, which in turn reduces the risk of configuration drift and enhances security. This also enables rapid scalability and recovery. In the cloud, immutable architecture means that once you have created a server, container, or other resource, you cannot modify it directly. Instead, if you need to make changes, you create an entirely new version with the updates and replace the old one. It is like baking a fresh cake instead of trying to fix a burnt one. Let's now compare immutable versus mutable infrastructure. So, how does immutable infrastructure differ from mutable infrastructure? They are different in terms of configuration changes, maintenance, configuration drift, rollback, scalability, security, consistency, and automation. Let's understand these differences. Let's first start with configuration changes. In the immutable infrastructure, components remain unchanged after deployment, therefore promoting consistency and predictability. Changes are implemented by creating entirely new instances with updated configurations, therefore ensuring that each deployment starts from a known and consistent state of components. When you talk about mutable infrastructure, components are subject to modifications over time with changes applied directly to existing instances. This approach may lead to configuration drift where the actual state of the infrastructure diverges from the desired state due to manual changes. Let's now talk about maintenance. With the immutable infrastructure, maintenance is done through the deployment of new instances with updated configurations. By replacing existing instances with fresh ones, organizations ensure that the infrastructure remains consistent and free from accumulated changes or vulnerabilities. With mutable infrastructure, maintenance involves applying patches, updates, and configuration changes directly to the existing instances. While this approach may seem more straightforward, it can lead to configuration inconsistencies and dependencies over time. Let's now talk about configuration drift. With immutable infrastructure, configuration drift is minimized as components are always created from a consistent configuration. By deploying identical instances based on predefined configurations, organizations can avoid discrepancies between environments and ensure consistency. With mutable infrastructure, configuration drift occurs when manual changes accumulate over time, therefore leading to inconsistencies between environments. Without strict control and automation, maintaining consistency becomes challenging, therefore increasing the risk of configuration errors and security vulnerabilities. Let's now talk about rollback. With immutable infrastructure, rollback involves reverting to a previous version of the infrastructure by deploying a previous configuration or image. Since each deployment generates a new version, organization can easily revert to a known good state in the case of issues or failures. With mutable infrastructure, rollback typically requires undoing changes or restoring backups of existing infrastructure components. This process may be more complex and time consuming, especially if proper versioning and backup procedures are not in place. Let's move to the next slide and look at some more differences between immutable and mutable infrastructure. In continuation from the previous slide, let's look at some more differences between immutable and mutable infrastructure. Let's now talk about scalability. In immutable infrastructure, it enables rapid horizontal scaling by deploying identical instances to handle increased workload or traffic. By creating new instances instead of modifying existing ones, organizations can quickly adapt to changing demands and maintain performance and availability. With mutable infrastructure, scalability may be limited by the complexities of managing multiple instances and ensuring consistency across deployments. Manual changes and dependencies between components can hinder the ability to scale efficiently, therefore, leading to performance issues and operational challenges. Let's now move to security. In immutable infrastructure, security is enhanced by reducing the attack surface and ensuring that components are built from a known and secure configuration. By consistently deploying fresh instances based on predefined configurations, organizations can mitigate the risk of vulnerabilities and unauthorized changes. With mutable infrastructure, security risks may increase due to the accumulation of manual changes and potential misconfigurations over time. Without strict control and automation, maintaining a secure and compliant infrastructure becomes challenging, therefore, leaving organizations vulnerable to threats and attacks. Let's now talk about consistency. In immutable infrastructure, consistency is assured across environments by deploying identical instances based on predefined configurations. By rebuilding from a known configuration every time, organizations can minimize surprises and discrepancies between development, testing, and production environments. In mutable infrastructure, consistency may vary between environments due to differences in configurations applied manually over time. Without strict controls and automation, maintaining consistency becomes challenging, therefore, increasing the risk of deployment errors and operational issues. Then there is automation. Immutable infrastructure relies heavily on automation for provisioning, deployment, and management. Automation tools such as Terraform, Ansible, or CloudFormation are used to ensure repeatability, consistency, and efficiency in infrastructure operations. In mutable infrastructure, automation may be less prevalent, with manual interventions often required for updates and changes. Without automation, organizations may struggle to maintain consistency and efficiency, therefore leading to increased operational overhead and potential errors. Let's now talk about the core principles of immutable infrastructure. So the first one is don't change, replace. The fundamental rule is to treat infrastructure components as immutable. You should avoid making changes directly to running systems. If you need updates, create a new instance with modifications and swap it in. Then, automation is key. Immutable infrastructure relies heavily on automation tools such as Terraform, Ansible, or CloudFormation to manage the creation, deployment, and replacement of resources. This ensures consistency, repeatability, and reduces the risk of human error. Then there is use version control. Just like you would version your code, version your infrastructure configurations as well. This allows you to track changes, roll back to previous states, and maintain an audit trail. Then there is ensure consistent environments. By rebuilding from a known configuration every time, you guarantee that your development, testing, and production environments are identical, therefore minimizing surprises when you deploy. Then there is simplify rollbacks. If something goes wrong with a deployment, you can quickly revert to a previous known good version of your infrastructure. Let's now talk about why immutable. So there is predictability. You know exactly what's running because it is built from a controlled configuration. This reduces the risk of unexpected behavior or configuration drift. Then there is reliability. Since you are always deploying fresh instances, you avoid the accumulation of manual changes or patches that can lead to instability over time. Then there is scalability. It's easier to scale up or down when your infrastructure components are standardized and can be easily replicated. Then there is security. By rebuilding from a known secure baseline, you can reduce the attack surface and make it harder for vulnerabilities to persist. Then there is DevOps alignment. Immutable infrastructure aligns well with DevOps practices such as continuous integration and delivery, therefore promoting faster and more reliable deployments. Just to quickly recap, in this particular topic, we talked about immutable infrastructure, which is a design approach in cloud computing. Then we talked about several differences between immutable and mutable infrastructure. And then going forward, we talked about the core principles of immutable infrastructure, which included don't change but replace, automation, version control, consistent environments, and rollbacks. And then towards the end, we talked about why immutable, which is basically gaining the benefits of predictability, reliability, scalability, security, and DevOps alignment. Describe the relationship between IAC and immutable architecture in the cloud environment. Let's now talk about the relationship between IAC and immutable infrastructure. While immutable architecture proposes the idea of treating infrastructure as unchanging components, IAC is the practical toolset that makes the infrastructure achievable and manageable at scale. So let's look at how IAC makes immutable architecture possible. So there are several reasons that are listed on the slide. So first one is the defining the blueprint. IAC allows you to codify your entire infrastructure setup, including servers, networks, databases, and their configurations into machine-readable files. These files become the single source of truth for your desired infrastructure state. Then there is automation. IAC tools automate the provisioning and the deployment of infrastructure resources based on the defined code. This automation eliminates the need for manual configuration, thereby reducing the chances of human errors and ensuring consistency across environments. Then there is immutable changes. With IAC, changes are not made directly to the existing infrastructure. Instead, you modify the IAC code to represent the desired changes. Running the updated code triggers the creation of new resources with the desired configuration, therefore replacing the old ones. This immutability prevents configuration drift and ensures that each deployment is based on the same reliable blueprint. Then there is version control. IAC code is stored in version control systems such as Git alongside your application code. This allows you to track changes to infrastructure over time, revert to previous state, and if needed, collaborate effectively with other team members. Let's now talk about the benefits of IAC and immutable infrastructure relationship. So, IAC enables immutable architecture. By defining infrastructure as code or IAC and using automation, IAC makes it possible to create, deploy, and manage immutable infrastructure at scale. Then there is immutable architecture benefits from IAC. The immutability principle complements IAC by ensuring that the infrastructure always matches the defined code, preventing configuration drift and maintaining consistency. So when both these work together, they create a powerful workflow. The combination of IAC and immutable architecture allows for faster, more reliable, and more secure deployments and easier rollbacks and scaling. Let's look at the example of IAC and immutable infrastructure. Imagine that you need to deploy a web server. With IAC, you define the server specifications, which can include the operating system, software packages, and the security setting in code. Running this code automatically provisions the server in the cloud environment. Later, if you need to update the web server's configuration, for example, you might want to add a new security patch. You don't manually modify the running server. Instead, you update the IAC code and run it again. The IAC tool will create a new server instance with the updated configuration and replace the old one seamlessly. This ensures that your web server is always in a known and consistent state as defined by your IAC code. Just to quickly recap, in this particular topic, we talked about the relationship between IAC and immutable architecture. We also talked about the benefits of IAC and immutable infrastructure relationship. So, for example, we talked about IAC enables immutable architecture. Immutable architecture benefits from IAC, and together they create a powerful workflow. And then, towards the end of this topic, we did talk about the example of IAC and immutable infrastructure, in which we talked about a running web server and then upgrading it with a new security patch. Identify the key infrastructure as code tools compatible with GCP. In this topic, what we are going to do is we are going to talk about three different types of tools that are compatible with GCP, and these tools are IAC tools. So let's start with native GCP tool. You have Cloud Deployment Manager. This is Google's own IAC service that is designed specifically for GCP. It uses either YAML or Python templates to define and deploy resources, therefore making it ideal for managing complex GCP configurations and leveraging integration with GCP services. The next category is the general purpose IAC tools. So there is Terraform, which is the most popular and versatile IAC tool known for its cloud agnostic nature, declarative approach, and extensive provider ecosystem. Terraform supports multiple cloud providers including GCP and allows you to manage diverse cloud environments using a single configuration language. Then there is Pulumi, which is also part of the general purpose IAC tool. Pulumi is a modern IAC platform that lets you use familiar languages like Python, TypeScript, Go, and so on to define your infrastructure. It offers a declarative approach with strong typing and testing capabilities, therefore making it a powerful choice for complex infrastructure projects. The next category of these tools is configuration management tools, which are also used for IAC. So there is Ansible. While primarily an imperative configuration management tool, Ansible also has modules and playbooks that enable you to provision and manage GCP resources. Its strength lies in orchestrating complex workflows and tasks across your infrastructure. Then there is Chef, which is a mature configuration management tool with declarative approach. It uses recipes and cookbooks written in Ruby to define infrastructure configurations. Chef can be extended to manage GCP resources by using custom recipes and integrations. Then there is Puppet, which is another established configuration management tool with a declarative approach. It uses a domain-specific language or DSL for defining configurations and can be extended to manage GCP resources using modules. Let's now talk about the comparison of IAC tool. So in this particular slide, what we are going to talk about is different IAC tools and compare them in terms of configuration, approach, purpose, reusable templates, and availability. So let's start with Cloud Deployment Manager, which is a native GCP tool. Now it uses YAML or Python configuration files to define desired state of GCP infrastructure. It is a declarative tool. You can use it to specify what you want your infrastructure to look like, and the deployment manager will handle the how part of it. It is ideal for managing complex GCP infrastructure due to its seamless integration with other GCP services. However, it is limited to the GCP ecosystem. Next one is Terraform, which is from HashiCorp, and it is a popular and versatile IAC tool. It uses HCL in a declarative manner to manage infrastructure across multiple cloud providers like AWS, Azure, and GCP, and on-premises environments. Its extensive provider ecosystem and strong community support makes it a top choice for multi-cloud and hybrid setups. Terraform allows you to create reusable templates to define and manage infrastructure components efficiently. The next one is Polomi. Polomi takes a modern approach to IAC by allowing you to use general purpose programming languages such as Python, TypeScript, and Go to define your infrastructure. It is declarative, meaning you describe the desired state and Polomi handles the provisioning and updates. This tool excels at handling complex workflows and application level deployments due to its flexibility and ability to leverage familiar programming constructs. Then there is Ansible, which is from Red Hat, and it is an agentless IAC tool that uses YAML for configuration. It follows an imperative approach, meaning you specify the exact step to achieve the desired state. Ansible is primarily used for configuration management and orchestration, tasks like installing software, managing configurations, and deploying applications. It is known for its simplicity and vast collection of modules for various tasks. Then there is Puppet, which is a mature and widely used configuration management tool. It uses its own Puppet DSL or domain specific language and follows a declarative approach. It has a master agent architecture where Puppet Master Server manages the configuration of agent nodes. Puppet is an excellent tool for managing complex configurations across a large number of systems. It has a strong community and extensive documentation. Then the last on the list is Chef, which is similar to Puppet. Chef is a configuration management tool. It uses Ruby DSL or domain specific language. It can be used with both imperative and declarative approaches, therefore, giving you the flexibility in writing your configuration, that is, cookbooks or recipes. Chef is known for its customization capabilities, and Chef Server, which serves as a central hub for managing configurations. It is a good choice when you need a high degree of control and flexibility in your configuration management process. Let's now talk about the key considerations for choosing a tool. When selecting an IAC tool for use in the GCP environment, several considerations should be taken into account. So let's go ahead and discuss these considerations. So first one is compatibility with GCP services. You need to ensure that the IAC tool supports provisioning and managing a wide range of GCP services, including compute instances, networking resources, storage solutions, databases, and managed services. Compatibility ensures seamless integration and effective management of GCP resources. Then there is declarative versus imperative approach. Consider whether the tool follows a declarative or imperative approach to infrastructure provisioning and management. Declarative tools such as Terraform specify the desired state of infrastructure, whereas imperative tools such as Ansible define step-by-step instructions for configuration. You should choose an approach that aligns best with your team's preferences and workflows. The next one is community and ecosystem support. You should evaluate the size and activity of the tool's community and ecosystem. A vibrant community often means access to a wealth of resources, documentation, tutorials, and community contributed modules or plugins. It also indicates ongoing development and support for the tool. Then there is ease of use and learning curve. You should assess the tool's ease of use and learning curve associated with its adoption. Consider factors such as simplicity of its configuration language, the availability of comprehensive documentation and tutorials, and the tool's overall user friendliness. Choose a tool that aligns with your team's skill level and expertise. In continuation from the previous slide, let's look at some more key considerations for choosing a tool. So the next point to discuss is cloud agnostic versus GCP initiative. You should decide whether you prefer a cloud agnostic IAC tool such as Terraform that supports multiple cloud providers or a tool native to GCP such as Google Cloud Deployment Manager. Cloud agnostic tools offer flexibility in managing multi cloud environments, whereas native tools may provide deeper integration and specialized feature for GCP. Then there is scalability and performance. You should consider the scalability and performance capabilities of the IAC tool, especially in large and complex environments. You should evaluate factors such as the tool's ability to manage infrastructure at scale, handle concurrent deployments, and optimize resource utilization to meet your organization's performance requirements. Then there is integration with existing tools and workflows. You should assess how well the IAC tool integrates with your existing development, deployment, and automation workflows. You should consider factors such as compatibility with version control systems, CI/CD pipelines, configuration management tools, monitoring and logging solutions, and other DevOps tools in your tool chain. The next point is security and compliance. You should ensure IAC tool supports best practices for security and compliance requirements for managing infrastructure in the cloud. You should look for features such as role-based access control or RBAC, encryption, audit logging, and compliance certifications. You should choose a tool that aligns with your organization's security policies and regulatory requirements. By considering these key factors, you can choose an IAC tool that best meets your organization's requirements for managing infrastructure in the GCP environment. To quickly recap, we talked about different sets of IAC tools in the GCP environment. So we talked about the native tools, which is the Cloud Deployment Manager. We also talked about general purpose IAC tools, which includes Terraform, Pulumi, and then we talked about configuration management tools, which can also be used for IAC. We talked about Ansible, Chef, and Puppet. And then in this topic, we also compared these tools on various parameters. And then we talked about the considerations for choosing a tool, its compatibility with GCP services, whether it is declarative or imperative, community and ecosystem support, ease of use and learning curve. And then we also talked about whether the tool is cloud agnostic or GCP native, its scalability and performance, its integration with existing tools and workflows, and security and compliance. Identify the key infrastructure as code tools compatible with GCP. In this topic, what we are going to do is we are going to talk about three different types of tools that are compatible with GCP, and these tools are IAC tools. So let's start with native GCP tool. You have Cloud Deployment Manager. This is Google's own IAC service that is designed specifically for GCP. It uses either YAML or Python templates to define and deploy resources, therefore making it ideal for managing complex GCP configurations and leveraging integration with GCP services. The next category is the general purpose IAC tools. So there is Terraform, which is the most popular and versatile IAC tool known for its cloud agnostic nature, declarative approach, and extensive provider ecosystem. Terraform supports multiple cloud providers, including GCP, and allows you to manage diverse cloud environments using a single configuration language. Then there is Pulumi, which is also part of the general purpose IAC tool. Pulumi is a modern IAC platform that lets you use familiar languages like Python, TypeScript, Go, and so on to define your infrastructure. It offers a declarative approach with strong typing and testing capabilities, therefore making it a powerful choice for complex infrastructure projects. The next category of these tools is configuration management tools, which are also used for IAC. So there is Ansible. While primarily an imperative configuration management tool, Ansible also has modules and playbooks that enable you to provision and manage GCP resources. Its strength lies in orchestrating complex workflows and tasks across your infrastructure. Then there is Chef, which is a mature configuration management tool with declarative approach. It uses recipes and cookbooks written in Ruby to define infrastructure configurations. Chef can be extended to manage GCP resources by using custom recipes and integrations. Then there is Puppet, which is another established configuration management tool with a declarative approach. It uses a domain specific language or DSL for defining configurations and can be extended to manage GCP resources using modules. Let's now talk about the comparison of IAC tool. So in this particular slide, what we are going to talk about is different IAC tools and compare them in terms of configuration, approach, purpose, reusable templates, and availability. So let's start with Cloud Deployment Manager, which is a native GCP tool. Now it uses YAML or Python configuration files to define desired state of GCP infrastructure. It is a declarative tool. You can use it to specify what you want your infrastructure to look like, and the deployment manager will handle the how part of it. It is ideal for managing complex GCP infrastructure due to its seamless integration with other GCP services. However, it is limited to the GCP ecosystem. Next one is Terraform, which is from HashiCorp, and it is a popular and versatile IAC tool. It uses HCL in a declarative manner to manage infrastructure across multiple cloud providers like AWS, Azure, and GCP, and on-premises environments. Its extensive provider ecosystem and strong community support makes it a top choice for multi-cloud and hybrid setups. Terraform allows you to create reusable templates to define and manage infrastructure components efficiently. The next one is Polomi. Polomi takes a modern approach to IAC by allowing you to use general-purpose programming languages such as Python, TypeScript, and Go to define your infrastructure. It is declarative, meaning you describe the desired state and Polomi handles the provisioning and updates. This tool excels at handling complex workflows and application-level deployments due to its flexibility and ability to leverage familiar programming constructs. Then there is Ansible, which is from Red Hat, and it is an agentless IAC tool that uses YAML for configuration. It follows an imperative approach, meaning you specify the exact step to achieve the desired state. Ansible is primarily used for configuration management and orchestration, tasks like installing software, managing configurations, and deploying applications. It is known for its simplicity and vast collection of modules for various tasks. Then there is Puppet, which is a mature and widely used configuration management tool. It uses its own Puppet DSL or domain-specific language and follows a declarative approach. It has a master agent architecture where Puppet Master Server manages the configuration of agent nodes. Puppet is an excellent tool for managing complex configurations across a large number of systems. It has a strong community and extensive documentation. Then the last on the list is Chef, which is similar to Puppet. Chef is a configuration management tool. It uses Ruby DSL or domain-specific language. It can be used with both imperative and declarative approaches, therefore giving you the flexibility in writing your configuration, that is, cookbooks or recipes. Chef is known for its customization capabilities and Chef Server, which serves as a central hub for managing configurations. It is a good choice when you need a high degree of control and flexibility in your configuration management process. Let's now talk about the key considerations for choosing a tool. When selecting an IAC tool for use in the GCP environment, several considerations should be taken into account. So let's go ahead and discuss these considerations. So first one is compatibility with GCP services. You need to ensure that the IAC tool supports provisioning and managing a wide range of GCP services, including compute instances, networking resources, storage solutions, databases, and managed services. Compatibility ensures seamless integration and effective management of GCP resources. Then there is declarative versus imperative approach. Consider whether the tool follows a declarative or imperative approach to infrastructure provisioning and management. Declarative tools such as Terraform specify the desired state of infrastructure, whereas imperative tools such as Ansible define step-by-step instructions for configuration. You should choose an approach that aligns best with your team's preferences and workflows. The next one is community and ecosystem support. You should evaluate the size and activity of the tool's community and ecosystem. A vibrant community often means access to a wealth of resources, documentation, tutorials, and community contributed modules or plugins. It also indicates ongoing development and support for the tool. Then there is ease of use and learning curve. You should assess the tool's ease of use and learning curve associated with its adoption. Consider factors such as simplicity of its configuration language, the availability of comprehensive documentation and tutorials, and the tool's overall user friendliness. Choose a tool that aligns with your team's skill level and expertise. In continuation from the previous slide, let's look at some more key considerations for choosing a tool. So, the next point to discuss is cloud agnostic versus GCP initiative. You should decide whether you prefer a cloud agnostic IAC tool such as Terraform that supports multiple cloud providers or a tool native to GCP such as Google Cloud Deployment Manager. Cloud agnostic tools offer flexibility in managing multi cloud environments, whereas native tools may provide deeper integration and specialized feature for GCP. Then there is scalability and performance. You should consider the scalability and performance capabilities of the IAC tool, especially in large and complex environments. You should evaluate factors such as the tool's ability to manage infrastructure at scale, handle concurrent deployments, and optimize resource utilization to meet your organization's performance requirements. Then there is integration with existing tools and workflows. You should assess how well the IAC tool integrates with your existing development, deployment, and automation workflows. You should consider factors such as compatibility with version control systems, CI/CD pipelines, configuration management tools, monitoring and logging solutions, and other DevOps tools in your tool chain. The next point is security and compliance. You should ensure IAC tool supports best practices for security and compliance requirements for managing infrastructure in the cloud. You should look for features such as role-based access control or RBAC, encryption, audit logging, and compliance certifications. You should choose a tool that aligns with your organization's security policies and regulatory requirements. By considering these key factors, you can choose an IAC tool that best meets your organization's requirements for managing infrastructure in the GCP environment. To quickly recap, we talked about different sets of IAC tools in the GCP environment. So we talked about the native tools, which is the Cloud Deployment Manager. We also talked about general purpose IAC tools, which includes Terraform, Pulumi, and then we talked about configuration management tools, which can also be used for IAC. We talked about Ansible, Chef, and Puppet. And then in this topic, we also compared these tools on various parameters. And then we talked about the considerations for choosing a tool, its compatibility with GCP services, whether it is declarative or imperative, community and ecosystem support, ease of use and learning curve. And then we also talked about whether the tool is cloud agnostic or GCP native, its scalability and performance, its integration with the existing tools and workflows, and security and compliance. Outline the steps for making infrastructure changes using Cloud Foundation Toolkit. While general purpose IAC tools provide a solid foundation for managing your infrastructure, GCP offers a specialized toolkit called Cloud Foundation Toolkit or CFT to streamline the deployment of common infrastructure patterns. Let's look at the steps to use CFT to deploy and manage your GCP resources. So it starts with prepare to implement the changes. You need to ensure that you have set up the environment. You have CFT command line interface installed and configured on your local system. You should also explore the CFT blueprints and modules relevant to the infrastructure changes you are going to make. You should review the documentation and examples to understand the available options and configuration parameters. The next step is plan your changes. You need to determine which blueprints or modules in the CFT correspond to the infrastructure components you need to modify. You should either use deployment manager templates, which are YML based, or Terraform configurations, which are HCL based. This would depend on the blueprint or module you are working with. You need to make the necessary modifications to the code to reflect the desired state. The next step is test changes locally. You should use CFT CLI to validate the syntax and structure of your modified templates or configurations. This helps catch any errors before deployment. If available, you should use a dry run feature to simulate the changes and review their potential impact without actually deploying them to your GCP environment. The next step is commit and push changes. If you're working with a team, commit your changes to a version control system like Git for tracking and collaboration. This ensures everyone is aware of the modifications made. You can push your changes to a shared repository like GitHub so others can review them and provide feedback. The next step is deploy changes. You should use CFT CLI to apply your modified templates or configurations. The tool will communicate with GCP and provision or update the infrastructure resources as defined in your code. The CFT CLI will provide feedback on the deployment process. You should monitor this output to track the status of your changes. The last step is verify changes. Once the deployment is complete, you should thoroughly test the modified infrastructure to ensure it functions as expected. You should also verify the changes you made are reflected in the GCP console to confirm everything was provisioned correctly. If everything doesn't go as planned, so which means if all these steps do not give you the desired output, you need to perform a rollback. Now, you can do that by reverting the changes. You can revert the changes using CFT CLI or cloud providers console to roll back your changes to a previous working state. Let's now talk about the benefits of CFT. Using CFT for infrastructure changes provides multiple benefits. So let's start with automation and consistency. CFT automates the deployment process, therefore ensuring consistent infrastructure setup across environments and reducing the risk of human error. Then there is collaboration. Integrating with version control systems like Git facilitates team collaboration and ensures that everyone is aware of the changes made to the infrastructure. Then there are best practices. You should leverage CFT's pre-built blueprints and modules which incorporate GCP best practices for security, reliability, and performance. Then there is flexibility. You can either use deployment manager or Terraform templates based on your preferences and specific infrastructure requirements. Just to quickly recap, in this particular topic, we talked about the steps to use CFT to deploy and manage your GCP resources. Then we talked about benefits of using CFT. So we would get benefits like automation and consistency, collaboration, and flexibility. Compare Terraform, Helm, and Config Connector for GCP IAC solutions. Let's see how these three IAC solutions, Terraform, Helm, and Config Connector, compare in terms of their configuration, approach, and other factors, and where each solution is suitable. So let's start with purpose. Terraform is primarily used for multi-cloud infrastructure provisioning. Helm is designed as a Kubernetes package manager mainly for deploying applications. Config Connector focuses on managing GCP resources natively in Kubernetes. Then there is configuration. Terraform uses HCL for defining infrastructure. Helm charts, which are YML templates with optional Go templating, are used for configuration. Config Connector utilizes Kubernetes custom resource definitions or CRDs in YML format for configuring GCP resources. The next one is approach. Terraform adopts a declarative approach for infrastructure management. Helm also follows a declarative approach, particularly for application definitions. Config Connector uses a declarative approach to manage GCP resources within Kubernetes. The next one is state management. Terraform uses a state file to track and manage the infrastructure state. Helm doesn't have built-in state management but can leverage external tools. Config connector relies on the Kubernetes API server for state management. The next one is flexibility. Terraform is highly flexible and supports various cloud providers, including GCP. Helm is primarily focused on Kubernetes deployments, which limits flexibility. Config connector is limited to managing GCP resources within Kubernetes. The next point is complexity. Terraform can be complex for large scale deployments, and HCL has a learning curve. Helm is easier for Kubernetes users, but templates can become complex for large applications. On the other hand, Config Connector is simpler for Kubernetes native workflows but requires knowledge of Kubernetes. Let's move to the next slide to look at some more points in terms of comparison of GCP IAC solutions. In continuation from the previous slide, let's do some bit of more comparison of GCP IAC solutions. The next point is ecosystem. Terraform offers an extensive provider ecosystem and is widely adopted. Helm has a large collection of pre-built charts and growing community. Config Connector features a growing community and integration with GCP services. Let's not talk about where each tool is best suited for. Terraform is ideal for multi-cloud environments and complex infrastructure. Helm is more suitable for Kubernetes-centric environments and managing applications. Config Connector is best suited for managing GCP infrastructure within Kubernetes, GitOps workflows, and Kubernetes native teams. The next point is managed services. Terraform supports managed services across various cloud providers. Helm is limited to managing Kubernetes applications and related services. Config Connector is primarily focused on managing GCP managed services. Then there is version control. Terraform directly integrates with version control systems like Git. Helm requires external tools for versioning Helm charts. Config Connector integrates with version control systems for managing Kubernetes resources. The last point is customization. Terraform is highly customizable with an extensive provider ecosystem. Helm customization is somewhat limited and focuses on Kubernetes resources. In Config Connector, customization is limited to Kubernetes resources, therefore relying on the GCP APIs. Just to quickly recap, in this particular topic, we compared different GCP IAC tools. These tools were Terraform, Helm, and Config Connector. We talked about various points like the purpose of each tool, configuration, approach, state management, flexibility, and complexity. We also talked about ecosystem best suited for managed services, version control, and customization. In this particular video, we are going to use Terraform to deploy resources in the Google Cloud Platform environment. Now, to be able to do that, there are certain prerequisites we need to meet. So the first one is the Terraform installation. Now, depending on the operating system you have, it could be Linux, Mac OS, or Windows. You can go to the HashiCorp website and download the installer. Now, here the installation doesn't mean that you have to run through a wizard or series of steps to install. Here, the installation means you download the zip file. For example, if you're using Windows, you simply extract that into a folder, and that is it. That is the only installation you need to do. So there are going to be certain files. So for example, there is going to be an exe, terraform.exe, that is going to be there. And we are going to just have a look at that particular file. Then you need to have a GCP account. You need to create a GCP project. And if you want to use Google Cloud CLI or G Cloud CLI, you would have to download that tool. But in this particular scenario, what we are going to be doing is we are going to be using PowerShell to execute certain commands for Terraform. And then before you can execute these Terraform commands and interact with your GCP account and the project, we would need to authenticate with GCP. Now, there is a certain command. For example, you can use the gcloud auth application-default login command. And once you're authenticated, this command will open a web browser and prompt you to log in into your Google account. After successful authentication, your credentials will be saved locally and you will be able to interact with your project. Now, the next thing is you need to set the environmental variable so that you can use Terraform in whichever folder you have saved it. Now, these prerequisites we have already completed. Now, the next step is to start using Terraform to deploy those resources. And the resource that we are going to be deploying here is a Debian virtual machine. Now, in this particular interface on the screen, we are on the compute engine page, and currently there are no virtual machine instances. So what we are going to do is we are going to now switch over to the folder in which we have Terraform files. Now there are certain files that you would require. So terraform.exe is the default file along with license.txt. These are the only two files that are there in the zip file that you download. Rest of these files, some of them you will have to create and rest get created automatically. Now, to be able to do that, one thing we need to do is we need to create a configuration file. Now, that particular configuration file is main.tf. Now, there are two ways to do this. One, you can have a single file or you can have two different files, which is provider.tf and it could be any other name for the second file. So, for example, createvm.tf. Now, the first one is the file in which you would have the configuration for your project. In the provider.tf file contains the project ID, your service account key, which is a JSON file path, and the region, etc. So all this is included in the provider.tf file. The other TF file, which could be something like computevm.tf or main.tf, whatever you want to name it, it will contain the configuration for the resources that you want to create. Let's say if it is a VM, you would need to define the name for the virtual machine type, zone, network interface, and you can even define the boot disk. So let's quickly go ahead and have a look at main.tf file, and then you will be able to understand what I am talking about. So this is the main.tf file. Now this particular portion, this one actually belongs to the provider.tf file. Now, since I am not using two different files, there is a single file that I have. So I have merged both these into a single file. So what we spoke about earlier, so there are credentials. So now this is the JSON key file for your service account. So my service account name is SKS001. And this is the JSON key file. Now, then there is the project ID. Then there is a region in which you want to create the virtual machine. So if you want to skip it, you can skip it. You can simply, comment it and it will take the default region and create that virtual machine. This is the compute vm.tf or the piece of code that will define your virtual machine. So you have Google Compute instance, which is the VM instance. I've given the name Terraform-VM. Machine type is F1-micro. Zone is US-central1-A. Then there is a boot disk. The image from where it is going to create the virtual machine is Debian-cloud Debian-11. Then there is the network interface. So you have NAT IP, which is set to external NAT, and then network is the default. Now, this is the basic configuration that we have defined in the main.tf file. And now this is the file that will be required by Terraform to create the instance. Now, for example, if this particular file is not there and you execute Terraform command, the error message that you are going to see is that there is no configuration file. So some configuration file needs to exist in this particular folder where you have terraform.exe. Now, let's go ahead and switch over to the PowerShell window. So what I'm going to do is I'm going to first enter a command called Terraform fmt. Now, this is going to basically format the configuration file. So I'm going to just go ahead and run this command. Bingo, it runs successfully. The next command that I'm going to run is Terraform init or init. Now, this will download the necessary Google Cloud Provider plugin. So I'm going to just go ahead and press enter. All right, so this runs successfully. The next is I need to basically preview the changes that Terraform will make. So to be able to do that, I need to run a command called Terraform plan. When I press enter, what it is going to do is basically it's going to run through the configuration file. All right, so it's gone through the configuration file. Now, the next command, what it says is use Terraform apply. So I'm going to use Terraform apply. The moment I press enter, it's going to start building the virtual machine, but it is going to take a confirmation from us. So let's go ahead and enter this command Terraform apply. All right, so it's started. So now we need to enter a value. The only value that it is going to take is yes. And I'm going to type yes and press enter. Now, Google Compute Instance.vm instance creating. Now the creation process has started. What we are going to do is quickly jump over to the VM instance page and let's refresh it. There you go. The process is now started and let's go back. So there is a summary of what has happened. It says apply complete. Resources created or added is 1, 0 changed, 0 destroyed. This means one virtual machine has been successfully created without any problems. Now, what happens if I run this command Terraform apply once again using the same configuration file? There is going to be absolutely no change. Once this configuration is done, what we are going to do is we are going to run this command again. And this is where I was talking about consistency. The same thing can be recreated. I can go back, delete that virtual machine and run this script again, and it will again create the same virtual machine. Now, Terraform has compared your real infrastructure against your configuration and found no differences. So no changes are needed. So resources added 0, 0 changed, 0 destroyed. This is what it does. So if it's got the same configuration virtual machine running in your compute engine, it's not going to make any changes. Now what happens if I change the virtual machine name with this script? So let's go ahead and try this. I'm going to make this Terraform VM1 and I'm going to save this script. Let's come back and run those commands again. Okay. Terraform FMT, Terraform init or init. All right, now we are going to basically use Terraform plan. All right, so now it's started to refresh. Okay, look at this. Plan 1 to add, 0 to change, 1 to destroy, which means it's going to take the Terraform-VM virtual machine, it's going to delete it, and it's going to create another virtual machine, which is going to be known as Terraform-VM1. And now let's go ahead and apply. So it will first delete that virtual machine, which is there, and then it will create a new virtual machine. So I'm going to enter the value yes, and we will just see that magic. So here it is. It's destroying Terraform-VM. Now, once that is done, it's going to create a new virtual machine, still destroying. It takes around 45 seconds or so to destroy that virtual machine, basically delete it. So now what is going to happen is once this is destroyed or deleted, it's going to again run the same process to create a new virtual machine, which we previously saw in this video. All right, so this time it's gone beyond 45 seconds. And let's see how much time it takes now. All right, so approximately 1 minute. So it's taken 15 seconds more than it took previously when I tested this. Now, destruction complete after 1 minute, 1 second. Now it's creating. We will go back, refresh the compute engine page, and we will see Terraform-VM no longer exists. What exists is Terraform-VM1. So we will just let this process complete, and then we will hop over to that particular page. All right. Resources added 1, 0 changed, destroyed 1. All right. So we are just going to go back to this particular page. This virtual machine is still listed. What we need to do is we need to refresh this page. So what I'm going to do is refresh. All right. There you go. Terraform-VM1. Terraform-VM is now destroyed or deleted. Now, just to quickly recap, in this particular video, we used Terraform to deploy a compute resource, which is a virtual machine in our scenario. Review GCP's best practices for infrastructure as code. GCP provides a robust set of best practices for IAC to help organizations efficiently manage and deploy cloud resources. Let's look at a comprehensive overview of these practices. The first one is modularity and reusability. You can break down your infrastructure code into smaller, reusable components, which can be modules or templates. This enhances maintainability and allows you to standardize configurations across these projects. You can leverage GCP's deployment manager templates, Terraform modules, or other relevant tools to encapsulate common patterns and configurations for repeated use. You can create your custom modules tailored to your organization's specific needs. Then there is declarative configuration. You can opt for declarative approach, therefore expressing the desired state of your infrastructure rather than the steps to achieve it. This makes your code more readable, easier to understand, and simpler to version control. GCP Deployment Manager and Terraform are both declarative IAC tools natively supported by GCP. Then there is version control. You can use version control systems like Git to track changes to your infrastructure code. This enables collaboration, provides a historical record of changes, and allows for easy rollbacks if necessary. You can implement branching and pull request workflows for better code reviews and collaboration. The next one is infrastructure testing. You can automate testing of your IAC code to catch errors early in the development cycle. This can include unit testing, integration testing, and so on. You can use tools like TerraTest, Kitchen Terraform, and Google's Config Validator or any other specialized testing frameworks depending on your chosen IAC tool. The next one is secrets management. You should never hardcode sensitive data such as passwords or APIs keys into your IAC code. You should utilize secret management solutions like Google's Cloud Secret Manager, HashiCorp Vault, or Kubernetes Secrets to store and retrieve secrets securely during deployments. Let's now talk about the benefits of IAC. So there is continuation, integration, and deployment, or CI/CD. You can integrate your IAC code into CI/CD pipelines to automate the build, test, and deployment process. You can use tools like Cloud Build, Jenkins, or GitLab CI/CD to orchestrate pipelines. Then there is immutable infrastructure. You can consider adopting immutable infrastructure practices where infrastructure components are replaced rather than modified after deployment. This ensures consistent environments and minimizes configuration drift. You can use tools like Kubernetes and Terraform to help implement immutable infrastructure patterns effectively. The next point is documentation and self-service. You can document your infrastructure as code thoroughly, therefore detailing resource configurations, dependencies, and deployment procedures. This helps with onboarding new team members and future maintenance. You can empower teams with self-service tools and interfaces to deploy infrastructure on demand using standardized templates or scripts. The next point is monitoring and observability. You can instrument your infrastructure with robust monitoring and observability tools to gain real-time insights into performance and resource utilization. You can use GCP tools like cloud monitoring, cloud logging, cloud trace, and popular open source tools like Prometheus and Grafana to gain comprehensive visibility into your infrastructure. The next point is security and compliance. You should define and enforce security policies and compliance measures directly with your infrastructure code. You can leverage tools like Forseti Security, Cloud Security Command Center, and IAC specific linters to identify security misconfigurations and ensure compliance. You can employ the principle of policy as code to automate security and compliance checks. Just to quickly recap, in this particular topic, we talked about the best practices for IAC, which included modularity, reusability, declarative configuration, version control, infrastructure testing, and secrets management. And then we also talked about continuous integration and deployments, immutable infrastructure, documentation and self service, monitoring and observability, and security and compliance. Let's now talk about a case study on infrastructure as code or IAC. Now, in this particular case study, what we are going to do is talk about a hypothetical organization, which is Acme Corporation. Now, Acme is rising pretty rapidly into the tech world and they are caught into cloud conundrum. They have their infrastructure on Google Cloud Platform where they have tons of virtual machines and number of databases and several networks. Now, all this is growing rapidly. They are adding more and more virtual machines on daily basis. They are adding more databases along with their applications and creating new networks. So overall, the situation is pretty much out of control. And this is a tangled mess due to their rapid growth. Every time they do a new product launch, they end up creating more and more resources. And obviously, because they are just going ahead and creating without a second thought, there are inconsistencies. There are different ways where people are deploying these virtual machines, databases, or networks. Now, it has also become difficult for them to track changes, and this is basically hindering their growth. It is also putting bottleneck on the agility and also slowing down the releases that they have to do. So therefore, they need to come up with a solution and they need to do it quickly. And let's see how they did it. So there comes the Terraform as the solution. Now, Terraform is going to help them deploy several resources using IAC or infrastructure as code. So let's go ahead and talk about how they did it. So in the phase one, the team meticulously crafted Terraform configurations for each piece of their cloud puzzle. So they had the networks, they had compute resources, which is virtual machines, and each virtual machine could be in different sizes with different operating systems, and there could be different startup scripts that were laid down in the code. And then they had the databases, which we just talked about, saying that they were deploying n number of databases with their applications. Now, with the help of Terraform, they are going to be deploying the database instances, database configurations, and connections. All this, what Acme team did is they scripted their code to deploy these resources. Now, each configuration that they defined, it was like a blueprint, which ensured that every time they are going to deploy these resources, it's going to be deployed in the exact way, whether they had to deploy it in the development environment, testing, or the production. But there will not be any guesswork or there will not be any consistencies because the same script is going to deploy the same set of resources into different environments. Then, moving on to phase two, there was a versioning problem. Now, all the Terraform code lived in version control system, which is the Git. So every change was tracked. So, for example, if any administrator in their team made a change to a script which deployed, let's say, a Debian system, that particular change was tracked and there was a version that was basically added to that particular script. So if there was version 1.0 and the administrator made a change, and if it was a minor change, the script got saved as version 1.1. Now, with the versioning, the team was able to figure out what changes have been made, who has made the changes, and when the change was made. So if there was any chance of rolling back that particular configuration, they were able to do so. Now, moving on to phase three, which is the automation. Terraform was successfully integrated into CI/CD pipeline. Every code change triggered a series of automated steps. So there was plan. Now Terraform analyzed the code, compared it with the current infrastructure state, and displayed a preview of what would change. Then there was apply. Now, if that change was approved with a single command, Terraform brought the infrastructure in line with the code. Then there is a rollback if required. If the deployment went wrong, a single command restored the previous state. So now if we look at it, with the help of Terraform, they were able to resolve multiple problems. So there was inconsistencies in deployment that got resolved because there were scripts which would deploy the same set of resources in the same manner, whether it was the production, testing, or staging environment. Then there was versioning problem. There were inconsistencies. So all this got resolved with the help of Terraform, and versioning got resolved with the Git in the backend. Now, just to quickly recap, Acme Corp was successfully able to streamline their infrastructure in the Google Cloud platform with the help of Terraform and Git to control the versioning of their scripts. Let's now talk about the transformation that Acme Corporation witnessed. So Acme Corporation witnessed a remarkable shift in the following parameters. So there was speed. New environments were spun up in a fraction of time, therefore accelerating feature releases. Then there was reliability. Consistent configurations meant fewer errors and more predictable deployments. Then there is collaboration. Developers and the operation teams work together seamlessly on the infrastructure code, therefore breaking down silos. Then there was cost control. Terraform ensured resources were only used when needed, therefore saving money. Now, the bottom line for this entire case study is that Terraform empowered Acme Corporation to manage their growing cloud infrastructure with the elegance of code. It was like going to a pile of loose Lego bricks to a set of detailed instructions, resulting in faster, more reliable, and more cost effective cloud operations. Now, just to quickly recap, in this particular topic, we talked about a case study where Acme Corporation was struggling to maintain their infrastructure in the GCP environment. And then we talked about what the solution was and how Terraform changed all this. And then there were different phases that were played. So there was a phase one, then there was phase two, and then there was phase three where automation was brought in. And as a result, then we talked about how Terraform transformed the entire cloud infrastructure for Acme Corporation, and it provided several benefits like speed, reliability, collaboration, and cost control. Course summary. In this course, we covered various topics. So we started with defining infrastructure as code or IAC. Then we talked about the principle of immutable architecture in the cloud environment. And then we also talked about the relationship between IAC and immutable architecture in the cloud environment. So let's move to the next slide to look at some more summary points. Then we talked about the key IAC tools compatible with GCP. We also talked about making infrastructure changes using Cloud Foundation Toolkit or CFT. And then we also compared in tabular form, we compared Terraform Helm and Config Connector for GCP IAC solutions. And towards the end of the course, we talked about using Terraform to deploy GCP resources, GCP's best practices for IAC, what we should be doing and what we should not be doing. And then we also talked about a case study of Acme Corporation and how Terraform changed the entire infrastructure, or rather transformed their infrastructure in the GCP environment. So, what's coming up next? It is a course on CI/CD architecture stack in Google Cloud. Let's look at the course objectives. In this course, you will learn the concepts of continuous integration and continuous delivery, which is CI/CD. You will also learn about the components of CI/CD architecture stack in Google Cloud Platform. Then moving on, you will also learn about the process of setting up CI with Cloud Build. Then list the benefits of using Google Cloud Deploy for CD, which is continuous deployment. Then later in the course, you will also compare widely used third-party CI/CD tooling such as Jenkins, Git, and Argo CD. You will also learn to set up a basic CI/CD pipeline with Cloud Build or Terraform. And then later in the course, you will also learn to select an appropriate strategy for managing multiple environments in GCP. Then further in the course, you will also learn to create dynamic environments for feature branches with JKE, which is Google Kubernetes Engine and Terraform. Then towards the end, you will learn the concept of configuration management in GCP, integrate third-party tools with CI/CD pipelines in GCP, and then finally towards the end, you will also learn about the security practices for CI/CD pipelines in the cloud environment. Then you will also go through a case study of a multi-cloud CI/CD setup. And finally, towards the end, you will learn to troubleshoot common CI/CD pipeline issues in GCP. Describe the concept of continuous integration and continuous delivery or CI/CD. Let's start with continuous integration or CI. CI is the frequent merging of code changes into a shared branch, usually the main or the master branch. It is an automated build process triggered by each commit, and automated tests are run to validate changes during CI. Let's now talk about continuous delivery. Continuous delivery is a software development practice that builds upon CI or continuous integration. The primary goal of CD is to ensure your code base is always in a deployable state. This means that with a single click or automated trigger, you could release a new version of your software to production without any extensive manual preparation. Let's now look at the key characteristics of continuous delivery or CD. So there is one-click deployment. The heart of CD is a streamlined, automated deployment pipeline. Once code is deemed production ready, deploying it is simple, reliable process that significantly reduces the risk and effort associated with the releases. Then there is production ready code. CD focuses on code that has not only passed the automated test, but is also functionally sound and potentially releasable to users. This might include new features, improvements to existing features, or critical bug fixes. Then there is not automatic deployment. Unlike continuous deployment, which is a related practice, CD does not automatically push every change to production. It provides the option to deploy, but a human decision is often involved. This allows for additional quality checks or strategic release timing. Then there is additional testing that is required. While automated tests are essential in CD, additional quality assurance steps might be incorporated. These steps could be as follows. It could be acceptance test to verify that the software meets a user requirements. It could be a manual quality assurance, which in some cases might be required to detect issues that automated testing might have missed. Then there is exploratory testing, which is used to uncover unexpected issues or potential usability problems. Let's now talk about CD in practice. So there is code changes and continuous integrations. Developers commit code changes to a shared repository like Git. Automated tests run to ensure that new code does not break existing functionality. Then there is build and package. If the test passes, the code is built into an executable package or artifact. Then there is staging environment. The package is deployed to a staging environment that closely mimics production for additional testing and validation. Then there is manual approval, which is optional. A team member may review test results and approve the release. Then there is production deployment. With approval, the code is deployed to production by using automated tools and scripts. Then finally, there is monitoring and feedback. The software is monitored in production and feedback is gathered to inform future improvement. Let's now talk about continuous deployment. Continuous deployment takes the principle of CD a step further. It eliminates the step of manual approval before deployment and automatically releases every change that successfully passes through the pipeline to production. This means that code changes can go from developers commit to live production within minutes or hours, assuming they pass all automated tests and quality checks. So let's now talk about the key characteristics of continuous deployment. So there is automated release. The distinguished feature of continuous deployment is the automatic release of code changes to production without any human intervention. Then there is high confidence in automation. The practice requires a high degree of trust in the automated tests, quality gates, and overall robustness of your delivery pipeline. Any failures in these processes could lead to faulty code reaching production. Then there is frequent small releases. Continuous deployment encourages smaller, more frequent releases, which can help mitigate risks associated with large, complex deployments. Then there is fast feedback. Teams receive rapid feedback on their changes, therefore allowing them to quickly identify and address issues in production. Let's now talk about the comparison of CI/CD and continuous deployment. So let's start with code changes. When you talk about CI, developers regularly commit small code changes to a shared repository like Git multiple times a day. This keeps the code base up to date and prevents long-lived feature branches that can lead to integration issues. Then there is continuous delivery or CD. Similar to CI, developers frequently commit changes, but focus shifts to always having a deployable version of the software ready. Then there is continuous deployment. The same principle of frequent code commits applies, but the goal is to automate the entire release process so the code changes are automatically deployed to production if they pass all tests. The next feature is automated testing. CI emphasizes fast feedback through automated tests like unit tests, which focuses on individual components, and integration tests, which focuses on how components interact. These tests quickly identify any errors or regressions introduced by new code. CD or continuous delivery includes the same tests as CI but also adds more comprehensive testing such as UI testing, user acceptance testing or UAT, and performance testing. These ensure the software meets functional and non-functional requirements before it's manually approved for production. Continuous deployment builds upon the comprehensive testing of CD. However, there is much higher emphasis on the robustness and reliability of the automated test suite to ensure that any code passing the test is truly production ready. Let's now talk about the next feature, which is build and package. In continuous integration or CI, after passing tests, the code is automatically built and packaged into a deployable artifact. This could be a compiled executable, a jar-var file for Java applications, or a container image for Docker. For continuous delivery or CD, the same build and packaging process occurs as in CI, ensuring a consistent artifact is created for potential deployment. For continuous deployment, this phase is identical to CI/CD because the build and packaging process is essential for creating the artifact that will be automatically deployed. Let's now talk about the next feature, which is deployment environment. In CI, deployment is typically done to a development or testing environment, therefore allowing for manual verification of the changes and early identification of any issues before moving further down the pipeline. In CD or continuous delivery, the deployable artifact is automatically deployed to a staging environment which mimics the production environment as closely as possible. This allows for final testing and validation before a manual decision is made to promote the changes to production. In continuous deployment, the artifact is automatically directly deployed to the production environment after passing all tests. This eliminates manual intervention and speeds up the release process significantly. Let's move to the next slide and look at the comparison on certain more features. Now, in continuation from the previous slide, let's look at the comparison of CI/CD and continuous deployment. So the next feature is manual approval. In CI, continuous integration typically does not involve deploying to production, so manual approval isn't a factor here. However, team might manually trigger a deployment to a testing environment for further validation after automated tests pass. Continuous deployment eliminates manual approval for production deployment. Once code passes all automated tests and quality checks, it is automatically released to users. This requires high confidence in the automation and quality of the testing process. The next feature is deployment to production. While CI can include all manual deployment to test environments, it does not involve automatic deployment to production. The focus is on integrating and testing code, not the final release. Now, in CD or continuous delivery, deployment to production is automated. Now, for CD, deployment to production is automated, but it typically requires a manual approval before the final step. This provides a balance between automation and control. Now, for continuous deployment, the deployment to production is fully automated and happens immediately after code passes all the tests in the pipeline. This allows for rapid and frequent releases. The next feature is frequency of release. In CI, releases are frequent, but not necessarily continuous. The frequency depends on how often developers integrate their code and how quickly the test can be run. In CD, the software is always in a deployable state, but releases are controlled and usually scheduled based on business needs. This allows for flexibility while maintaining quality control. In continuous deployment, releases happen continuously and automatically whenever code changes pass the automated tests. This results in high frequency of releases, often multiple times a day. The next feature is risk management. In CI, the main focus is on early detection of integration issues through automated tests. By integrating code frequently, the problems are caught early and are easy to fix. In CD or continuous delivery, risk is mitigated through thorough testing in the staging environment, which mimics production. This helps identify and resolve issues before they reach users. The manual approval step also provides an additional layer of risk mitigation. In continuous deployment, the rapid pace of releases can increase the risk of introducing errors into production. This methodology requires a mature development process, a robust testing suite, and effective monitoring to identify and address issues quickly. Now, just to quickly recap, in this particular topic, we introduced the basic definitions of continuous integration, continuous delivery, and continuous deployment. We also talked about the practices for continuous delivery and continuous deployment. And then towards the end, we did a comparison of CI/CD and continuous deployment on various features like code changes, automated testing, build and package, deployment environment, manual approval, deployment to production, frequency of releases, and risk management. Describe the components of a CI/CD architecture stack in GCP. GCP empowers DevOps teams with a flexible, scalable, and deeply integrated suite of tools to build and manage robust CI/CD pipelines. DevOps teams can choose from a wide range of services, including Managed Kubernetes, which is GKE or Google Kubernetes Engine, serverless options, which include Cloud Functions and Cloud Run, and virtual machines, which are part of Compute Engine, to create a CI/CD architecture perfectly suited to your unique project requirements. GCP's integrated services like Cloud Build, Artifact Registry, and Cloud Deploy work together seamlessly to simplify the setup and maintenance of your CI/CD workflows. GCP's auto-scaling capabilities for both compute resources and serverless platforms ensure your pipelines can handle fluctuating workloads with ease, therefore optimizing both performance and cost. These benefits are realized through the following components of the CI/CD architecture stack. So the first one is the source code management. You can use source code repositories in GCP for managing your code. You can also connect your GitHub or Bitbucket repositories. Then there is build and test. Cloud Build helps you build and test your code automatically. You can store your built code in artifact registry. Then there is deployment. You can deploy your applications using Google Kubernetes Engine or GKE, Cloud Run, or App Engine. For GKE, you can use Cloud Deploy to manage deployments. Then there is monitoring and observability. You can keep an eye on your application by using cloud monitoring, logging, and trace. Then there is infrastructure as code or IAC. You can define your infrastructure by using Cloud Deployment Manager. You can also use Terraform for more flexibility. Then there is security. You can control access to your resources with Cloud IAM or Identity and Access Management. You can ensure secure deployments with binary authorization, and also you can monitor security with Security Command Center. Let's now talk about source code management. There is cloud source repositories. GCP's fully managed private Git repositories are seamlessly integrated with other GCP services. They provide version control, collaboration features, and triggers for CI/CD pipelines. Then there is GitHub or Bitbucket integration. You can connect your existing repositories on GitHub or Bitbucket for centralized source code management. Let's now talk about build and test. So there is Cloud Build, which is GCP's serverless CI platform. You can define build steps, run tests, and package artifacts such as container images or jar files in a scalable and secure environment. It is triggered by code changes, or you can do it manually as well. Then there is artifact registry. You can store, manage, and secure build artifacts produced by Cloud Build. The registry acts as a central repository for versioned artifacts used in deployments. Let's now talk about deployment. There is Google Kubernetes Engine or GKE, which is a managed Kubernetes service for deploying containerized applications. GKE provides a scalable and reliable platform for running microservices and other modern workloads. Then there is Cloud Run, which is a serverless platform for deploying containerized applications that automatically scale based on demand. It is ideal for stateless, HTTP-driven applications. Then there is App Engine, which is a fully managed platform for running web applications and APIs. It supports various languages and scales automatically based on traffic. Then there is Cloud Deploy, which is GCP's managed continuous delivery platform tailored for GKE. Cloud Deploy orchestrates deployment pipelines and handles rollout strategies and promotions. Let's now talk about monitoring and observability. There is Cloud Monitoring, which collects metrics, logs, and traces from your applications and infrastructure. It can monitor performance, detect anomalies, and trigger alerts for proactive issue resolution. Then there is Cloud Logging. Now, this is a centralized log management service. It aggregates, searches, and analyzes logs from various GCP services and your applications. Then there is Cloud Trace. This is a distributed tracing system to monitor and troubleshoot application performance across microservices and distributed systems. Let's now talk about infrastructure as code or IAC. Google Cloud Deployment Manager is GCP's native IAC service. It enables you to define your entire GCP infrastructure, such as virtual machines, networks, and databases, in a structured and declarative way. You can create templates in YAML or Python that describe the resource that you want to deploy. These templates are essentially blueprints for your infrastructure. Alongside templates, you can use configuration files to specify parameter values that can vary across deployments. So there could be number of instances in a virtual machine group. You can trigger deployments using G-Cloud command line tool or Google Cloud Deployment Manager API. Google Cloud Deployment Manager reads your templates and configuration files and then provisions the specified resources on GCP. Let's now talk about security. There is Cloud Identity and Access Management or IAM, which manages permissions and access control to GCP resources, therefore ensuring that only authorized users and services have access to sensitive data and actions. There is binary authorization, which enforces deployment policies for container images, therefore ensuring that only trusted and validated images are deployed to your GKE clusters. Then there is Security Command Center. This is a unified security management platform that provides threat detection, vulnerability scanning, and compliance monitoring across your GCP environment. Let's also look at some of the additional tools and integration. So there is Cloud Scheduler. It schedules cron jobs to trigger builds, tests, or deployments at specific times or intervals. There is Terraform, which is a popular third-party IAC tool that integrates well with GCP and offers greater flexibility for multi-cloud or hybrid environments. Then there is Spinnaker, which is an open-source, multi-cloud continuous delivery platform that can be integrated with GCP for advanced deployment strategies. Then we have Cloud Tasks. Now this is a tool that can manage asynchronous task execution that is useful for decoupling and queuing tasks in your CI/CD pipeline. Now, just to quickly recap, in this particular topic, we talked about the components of CI/CD architecture stack. So we talked about source code management, build and test, deployment, monitoring and observability, infrastructure as code or IAC, and security. And we also talked about some additional tools. So there was Cloud Scheduler, Terraform, Spinnaker, and Cloud Tasks. Outline the process of setting up CI with Cloud Build. Now, there are certain steps that you would need to follow when you want to set up CI with Cloud Build. So the first step is prepare your repository. You need to ensure your application code is stored in source code repository, such as Cloud Source Repositories, GitHub, Bitbucket, or any other supported repository. You need to create a configuration file which is usually named as cloudbuild.yml or cloudbuild.json in the root of your repository. This file defines the steps Cloud Build will execute to build and test your application. The next step is connecting Cloud Build to your repository. For this, you need to create a trigger. In the Cloud Build section of the GCP console, you need to create a trigger. You need to choose your repository source, and that needs to be done by either selecting GitHub or Bitbucket. Then you need to follow the prompts to connect Cloud Build to your repository and grant necessary permissions. Once you do that, you need to then configure the trigger. You need to specify the branch or tag you want to monitor for changes and select the build configuration file, which is cloudbuild.yml or cloudbuild.json that you had earlier created. The next step is define your build steps. You need to define the build steps in your configuration file, and then you need to run tests. Now, this is an optional step. You may want to skip running the test at that time, but you can add steps in your build configuration file to run unit tests, integration tests, or other automated tests. If any test fails, Cloud Build will report the failure and halt the build. The next step is monitor and manage builds. In the Cloud Build console, you can view the history of your builds. You can see logs and check the status of each step. You can also set up notifications to receive alerts for build failures or successes. The last step is deploy if it is part of your CI/CD pipeline. You can use Cloud Deploy to automate the deployment of your build artifact to the desired environments, which could be staging or production. And then you also have the option to integrate Cloud Build with other deployment tools or services if needed. Let's now look at the example of cloudbuild.yml file in the YML format. Now, this slide displays an example of cloudbuild.yml file that we did mention in the step 2 in the previous slide. Now, this uses the official cloud builder for Docker. So there is the build step, which builds a Docker image from the Docker file in the current directory. Then there is push, which pushes the built image to artifact registry in the specified region and repository. Then there is image that lists the image that will be built. This is important for caching purposes in the subsequent builds. Let's now look at the cloudbuild.json file in the JSON format. This JSON configuration defines cloud build process with two distinct steps, both utilizing gcr.io/cloud-builders/Docker builder image. Now, you are building the Docker image. So there are certain parameters. There is name. So there is gcr.io, which specifies the Docker builder image from Google Container Repository, which is GCR, to execute this step. Then there is args. That is the next parameter. Now, there is certain command that is mentioned there. This command is passed to the Docker builder. And then you also have the build, which instructs Docker to build an image. Then there is -t that specifies the tag, which is the name or optionally a tag for the image. And then you have uscentral-docker.pkg.dev, which indicates the artifact registry in the US Central 1 region where the image will be stored. Then there is project ID. Now, this is an environment variable that is automatically replaced by Cloud Build with your GCP project ID. Then you have the my Docker repo, which is the repository within artifact registry where the image will reside. And then you have my image, which is the name of the Docker image you are creating. And then there is a dot that tells Docker to use the current directory where your Docker file is located as the build context. And then you are pushing the Docker image. Now there is name, which is gcr.io/cloud-builders/Docker that reuses the same Docker builder image for efficiency. Then there is args with certain commands. So this command is used to push the built image to artifact registry. Now there are certain parameters or arguments. So there is push, which instructs Docker to push the image. And then there is the region and the project ID path, which is the full path and the tag of the image to push, matching the tag from the build steps. So how does it work in the cloud build? When you trigger a cloud build using this configuration, it spins up the environment with the Docker builder image. The first step executes the Docker build command, therefore creating a Docker image based on your Docker file and tagging it with the specified name. The second step takes the built image and pushes it to your artifact registry repository in the US Central 1 region. Just to quickly recap, in this particular topic, we talked about the process of setting up CI with Cloud Build. We talked about the steps that we need to follow, and then we also talked about the examples of cloudbuild.yml file and cloudbuild.json file. Summarize the benefits of using Google Cloud Deploy for CD. Google Cloud Deploy offers a host of benefits that streamline CD workflows within the GCP. So let's look at these benefits. So there is managed simplicity. Cloud Deploy eliminates the need for managing CD infrastructure, therefore allowing you to focus on the development tasks. Its user-friendly interface simplifies the setting up CD pipelines with declarative configuration options. The next benefit is seamless integration with the GCP ecosystem. You can easily deploy containerized applications to GKE clusters. It can integrate seamlessly with Cloud Build and Artifact Registry for a cohesive CI/CD workflow. It also leverages the built-in monitoring and logging tools for enhanced visibility into deployment processes. The next benefit is scalability and reliability. Cloud Deploy scales effortlessly to handle complex deployment scenarios across various environments and projects. As a managed service, Cloud Deploy ensures high availability and reliability of CI/CD pipelines. Let's continue to the next slide and look at some more benefits. In continuation from the previous slide, let's look at some more benefits of using Cloud Deploy. The next benefit is enhanced security and compliance. Cloud Deploy can benefit from GCP's robust security infrastructure, including identity and access management, encryption, and network security features. You can also configure, track, and audit deployment processes for compliance with industry regulations and internal policies. The next benefit is accelerated release velocity. Automated delivery processes enable quicker iteration and issue resolution. Automation minimizes manual steps, therefore leading to faster release of new features and update. The next benefit is cost efficiency. Cloud Deploy follows a pay-as-you-go model, therefore eliminating upfront infrastructure costs. It can automatically scale resources based on demand, therefore optimizing resource usage and reducing costs. Just to quickly recap, in this particular topic, we talked about the benefits of using Google Cloud Deploy for CD. We talked about the benefits like managed simplicity, seamless integration with GCP ecosystem, scalability and reliability, enhanced security and compliance, accelerated release velocity, and cost efficiency. Compare widely used third-party CI/CD tooling such as Jenkins, Git, and Argo CD. In this particular topic, what we will be doing is we'll be comparing various third-party tools like Jenkins, GitLab, CI/CD, and Argo CD. The slide shows a table in more detail with comparison of features of Jenkins, GitLab CI/CD, and Argo CD. So let's get started. The first feature that we are going to talk about is purpose. Jenkins is a versatile automation server that can handle a wide variety of tasks, including CI/CD. Its strength lies in the vast plugin ecosystem, therefore enabling integration with virtually any tool or technology. For GitLab, which is a native part of GitLab platform, it is designed to streamline the entire DevOps lifecycle from code to deployment. It offers a cohesive experience for teams already using GitLab for source code management and other aspects of development. Argo CD is specifically built for Kubernetes. It embraces the GitOps philosophy. It treats Git as the single source of truth for applications and infrastructure configurations, therefore ensuring what is in your Git repository matches what's running in your Kubernetes cluster. The next feature is architecture. Jenkins employs a master agent architecture. The master node orchestrates jobs while agent nodes executes the actual tasks. This allows for scalability and flexibility in terms of where you run your jobs. GitLab CI/CD uses a runner-based architecture. Runners, which can be hosted on various platforms including GCP, execute the tasks or jobs defined in your .gitlab-ci.yml configuration file. Argo CD functions as Kubernetes controller. It continuously monitors your Git repository for changes and automatically syncs your Kubernetes manifests with the desired state defined in Git. The next feature is flexibility. Jenkins is extremely flexible due to its extensive plugin ecosystem. You can customize Jenkins to fit virtually any workflow and integrate with any tool and tailor it to your specific requirements. GitLab CI/CD offers a good balance of flexibility and ease of use. It provides enough customization options to accommodate most CI/CD scenarios. Argo CD primarily focuses on Kubernetes deployments, therefore limiting its flexibility for other use cases. However, it excels at managing complex Kubernetes environments and providing robust GitOps capabilities. The next feature to talk about is ease of use. Jenkins has a steeper learning curve due to the vast number of plugins and configuration options. Setting up and maintaining a Jenkins instance can require significant expertise. GitLab CI/CD is generally considered easier to set up and use, especially for teams already familiar with GitLab. The integration with other GitLab features simplifies the setup and configuration process. Argo CD requires an understanding of Kubernetes concepts and manifests. While its core functionality is relatively straightforward, therefore leveraging its full potential may require Kubernetes expertise. Let's move to the next slide and look at some more comparison on different features. In continuation from the previous slide, let's look at some more comparison of different features. The next feature to talk about is integration with GCP. Jenkins can integrate with GCP through various plugins, but setup and configurations are often manual and can be complex. GitLab CI/CD offers good integration with GCP through built-in features and configuration options. You can easily deploy to GKE, Cloud Run, or other GCP services. Argo CD, which is designed for Kubernetes, seamlessly integrates with GKE and other Kubernetes environments hosted on GCP. It leverages native Kubernetes mechanisms for deployment and management. The next feature to discuss is community and support. Jenkins benefits from a large and mature community with extensive documentation, resources, and plugins. You will find plenty of help and support online. GitLab CI/CD has an active and growing community with strong documentation and support. The community is focused on GitLab specific use cases and integrations. Argo CD has a growing community that is primarily focused on GitOps and Kubernetes users. This community is active in developing and improving the tool and sharing best practices. Now let's talk about the last feature, which is best suited for. Jenkins is best suited for organizations needing maximum flexibility and customization, diverse tool chain, complex workflows, and a large community to leverage. GitLab CI/CD is a good choice for projects already using GitLabs, teams seeking a unified platform for the entire DevOps lifecycle, and those who prefer a relatively easy-to-use and well-integrated solution. Argo CD is ideal for Kubernetes-centric environments. It is also suitable for organizations that are embracing GitOps for continuous delivery and teams comfortable working with Kubernetes manifests and concepts. Now, just to quickly recap, in this particular topic, we looked at 3 different third-party CI/CD tools. These tools were Jenkins, GitLab CI/CD, and Argo CD, and we compared them on various features, the purpose, architecture, flexibility, and ease of use. We also looked at different features like integration with GCP, community and support, and best suited for, which is basically the use cases for these particular tools. Setting up a basic CI/CD pipeline with Cloud Build. Now, in this particular topic, what we are going to do is we are going to use a trigger and set up a basic CI/CD pipeline. And to be able to do that, I have already created a first step trigger. I'm going to just go ahead and click and walk you through it. And then once the walkthrough is done, what we are going to do is simply come back to this page and run this particular trigger. So the name is defined. There is a region. Now this is pushed to a branch. And this is a second gen, and it is connected to my GitHub repository, which is first app, and branch is the main. And there are multiple ways you can do this. You can use a cloud build configuration file, YAML or JSON. You can use a Docker file. You can use build pack. And the location could be either the repository or it could be inline. Now, in the inline, by default, there is a sample code that is defined. I'm going to just go ahead and click on open. And what it says is hello world. That is the only thing it will display. And name is Ubuntu and echo hello world. So I'm going to just go ahead and click on cancel. We are just going to use this particular inline YML. And you can override this. You can add whatever code you have. For example, I can simply just take the cloud build -.yml files code here, just copy it and go ahead and paste it there. And it will work the same way, except that when you connect it with a repository, it will go to the repository. It will look for a file called cloud build.yml file. Now, if that file does not exist, that it will throw an error, and we will see that in another topic, what happens when you don't have the cloud build.yml file. And then we can also send the build logs to GitHub. We can do that and require approval before build executes. This we will look at in another topic, where if you check this particular step, the build will be generated, but the approval will be required from a person with build approver role. So I'm going to just go ahead and cancel this out because we have not made any changes. And once we are back on the triggers page, what I'm going to do is I'm going to click on run. And it confirms branch main run trigger. All right, so I'm going to just click on show. And then it will take us to the steps that are being performed, because it's only echoing hello world, which is done here at the end, and the process is done. Now, if I go to the history tab, it will show that particular build is successfully created. So this shows that it's created. It took only 4 seconds. So this was the intent of showing you how to set up a basic CI/CD pipeline using cloud. Now, again, just to quickly recap, in this particular demo, we looked at how to use Cloud Build to set up a basic CI/CD pipeline using inline YML file. And again, just to reiterate, we can also use GitHub, where we need to create a file named cloudbuild.yml file. And if we just enter the same code over there, it will pick up that code and it will generate the build. We will now talk about the strategies for managing multiple environments in GCP in the next few slides. However, before we move ahead, let's quickly look at the strategies listed on the screen. So there is separate projects, then there is shared virtual private cloud or VPC with project-based isolation. Then there is resource labeling and naming conventions. The next one is infrastructure as code or IAC with environment variables. And finally, there is going to be Kubernetes namespaces. So let's move to the first strategy. So let's talk about the separate projects. Now in this, we need to create a distinct GCP project for each environment. So what we are going to get the benefit is there is going to be clear isolation. Now this is going to be the strongest separation of resources and billing. Let's now talk about a disadvantage. So there is going to be overhead. Now when you have multiple projects running, obviously there is going to be a bit of administrative overhead that is going to be there, because you need to manage multiple projects. And if your environment is large and complex, think how many projects are you going to create? And obviously, more projects you create, more administrative overhead is going to be there to manage them. Remember, each project has its own resources, so you will have to manage individual resources within those projects. Let's now talk about another advantage, which is easier permission management. So there is going to be fine-grained access control per environment. Each project you create, there is going to be fine-grained permissions that you can apply. You can apply the principle of least privilege, which means each individual user who's going to be working in these projects, whether they are the testers or the developers or any other user, they will get only the permissions that they are required to have for their work. That's about it. And now another disadvantage is going to be resource duplication. So there is going to be potential for redundant resources across projects. Now, for example, you have production environment, you have staging, and you have the testing environment. There is going to be one web server running across 3 environments. This web server is doing the same task across 3 projects or 3 different environments. So there is going to be resource duplication. You will have multiple virtual machines that you might deploy in the testing environment, and then those virtual machines you may also have to deploy in staging and finally in the production. So of course, with resource duplication, there is going to be added cost. Let's now move to the other advantage, which is simplified resource naming. Now, you don't have to define a complex naming convention to distinguish environments. You can define a simple naming strategy for each environment and then use it, or you can have an organization wide naming strategy and then you can apply that within these projects. So for example, you can have three different naming strategies. So for production, it can start with prod-vm-web server 1, something like that. Similarly, staging, the naming strategy can start for STG or stage-vm-web server 1. And similarly for testing. So you can have three distinct naming strategies for three different environments, but it depends on your organization's naming policy, how you want to define it. For example, in the on-premises environment, most organizations, especially the mid-size and the large ones, they do have a specific naming conventions for each of the resources that is deployed on the network, whether it is the servers, desktops, switches, routers, or even the wireless access points. They have a specific naming convention which is followed throughout. You can do that same for your GCP environment. Now, another disadvantage that is going to be there is shared resource challenge. It is going to be harder to share resources. So for example, if you have database running in one environment, it's not going to be possible to share it with the other environment. So that is going to be a major challenge. Let's now talk about shared virtual private cloud or VPC with project-based isolation. You can utilize a shared VPC with separate subnets for each environment within the same project. So let's talk about the first advantage. So there is network simplification. Now this approach significantly simplifies your network infrastructure. You can share common network resources such as firewalls, VPNs, or NAT gateways across all environments to reduce overall complexity and management overhead. Now, there is going to be a disadvantage that you need to have careful planning. Designing a shared VPC requires meticulous planning to ensure that subnets are properly isolated and that routing rules are correctly configured. You need to consider factors like IP address ranges, security groups, and firewall rules to prevent unauthorized access between environments. Now, this is going to be very important because one wrong rule, for example, allow asterisks, which means accesses for all resources, that is going to put you in great deal of danger. So you have to apply rules very, very carefully. You have to test them out and you have to ensure that rules are working as you intend them to work. Let's now talk about another advantage, which is private communication. Now, there are going to be instances in different environments. So, for example, there are going to be instances in development, staging, or production that can communicate with each other privately within VPC. Now, once this is done, this eliminates the need for public IP addresses or complex routing configurations. So that is going to be one major advantage you will have with shared VPCs. Let's now talk about another disadvantage. So there is going to be less isolation than separate projects. We just talked about separate projects in the previous slide. Now, if you talk about VPCs with project-based isolation, there is going to be less isolation when you compare it to separate projects. While subnets will provide a great deal of isolation, they don't offer the same level of separation as entirely separate projects do. Now, there is a potential risk of misconfiguration or unintended interactions between resources in different environments. If multiple environments share the same VPC, there is a risk of resource contention, especially if some environments experience spikes in traffic or resource usage. This could impact the performance of other environments. Now, you will have to carefully plan this shared VPC because, like I had just mentioned, if there is one wrong rule or misconfigured rule, it's going to put all your resources in great deal of danger. So you will have to ensure that your rules are perfectly designed, they are tested and then deployed. And in the similar manner, you have to test out your shared VPC environment as well. Let's now talk about another advantage, which is the centralized network management. With fewer VPCs to manage, you can centralize your network administration. Now, if you have different VPC in different environments, so there are going to be n number of VPCs you will have to manage. Now, if there is a shared VPC that is being shared across different environments, then obviously there are going to be fewer shared VPCs that you will need to manage. It will make things easier for you because you will be able to apply consistent security policies, monitor traffic, and troubleshoot issues. By sharing resources, you can also reduce costs associated with network infrastructure. So, for example, if there is a shared VPC, there are certain subnets that are being used across different environments. Obviously, the cost of those IP addresses or the network infrastructure will go down because you are not setting up different networks for different environments. So, let's look at the last disadvantage. So, there is going to be increased complexity of firewall rules. Now, when you have the shared VPC, managing firewall rules will become more complex, and you need to ensure that the correct rules are applied to each subnet to maintain the desired level of isolation and security. Now, for example, if there is allow asterisk or allow all rule defined, and that is the first rule in the firewall, that is going to be very difficult to manage because you are giving access to everything to everyone. That is going to be risky. So therefore, you need to deploy the rules very carefully. You need to test them out, and you need to ensure that they work as you intend them to do. So for example, you can test out these rules in a testing environment before you deploy them into the production network. Let's now talk about resource labeling and naming conventions. The idea here is to apply consistent labels, which are nothing but key value pairs, and naming conventions to resources. So these resources could be your virtual machines, storage buckets, or even databases, servers. Now you want to clearly indicate which environment they belong to. So for example, one key value pair that I can think of is environment:dev. So key is the environment and the value is the dev. So it could be env:staging, env:prod. So that is how you will distinguish between the environment. So there are going to be some advantages or disadvantages or pros and cons, we may even call them. Let's talk about the first advantage, which is the flexibility. Now, this approach makes it incredibly easy to add or remove environments without the overhead of creating new projects. You can simply adjust the labels or names of your resources. With consistent labels, you can easily automate tasks like applying specific policies, managing backups, or scaling resources based on the environment. Now, one of the disadvantages is going to be risk of confusion. When you are using resource labeling and naming convention, they will heavily rely on strict adherence to naming conventions. If there are inconsistencies or errors, it will lead to confusion and potentially misconfigurations or accidental changes to the wrong environment. So for example, if this is a staging environment, but you accidentally named it as dev, the key value pair that you defined as env:dev, now obviously you are not making changes to the dev environment, but it is actually the staging environment. Now, when you go back to the dev environment, you will find the changes have not been applied. So that is going to be a bit problematic for you. Let's now talk about another advantage, which is shared resources. You can share resources across environments when appropriate, as long as you carefully manage permissions. Now, this is particularly useful for non-production resources like monitoring tools or even shared databases. Now, another disadvantage that we would want to talk about is less isolation than separate projects. While you can achieve some logical isolation with labels and naming, it is not as strong as physical separation of different projects. There is slightly higher risk of accidental changes impacting other environments if not managed carefully. Let's now talk about another advantage, which is cost efficiency. Labeling and naming conventions help avoid the costs associated with managing multiple VPCs and other resources that might be duplicated if you were using separate projects. Now, another disadvantage is maintenance overhead. Maintaining consistent labels and naming conventions across a large number of resources can become challenging if your project continues to grow. Now, if you have, for example, just about 50 resources, maybe 10 virtual machines, some VPCs, some storage buckets, then it is fine. You can manage naming convention and resource labeling. But if your project grows into hundreds of virtual machines and several web servers, several networks, and hundreds of storage buckets, then it's going to be very difficult task to maintain them. So you need to establish a clear guidelines and potentially automate the process. Manually, it's going to be very difficult to maintain these resources and apply the consistent naming convention and labeling. So it's better to automate this process, and that is where you will achieve 100% consistency if you automate it properly. Let's now talk about infrastructure as code, or IAC, with environment variables. Now, in the GCP environment, you can use tools like Terraform or Cloud Deployment Manager to define your infrastructure configuration as code. In one of the previous topics, which was using Terraform to deploy resources in the GCP environment, we saw how we can use Terraform to deploy these resources. So we did deploy a virtual machine, and that is what this thing is all about, where it's talking about infrastructure as code with environment variables. Now you can utilize these variables within your IAC template to manage environment-specific settings. So for example, you can define your database connection strings, you can define your API endpoints, you can also define your service account credentials. So we did use service account key JSON file within the configuration that we created for IAC in the Terraform environment. So that is all comes under environment variable, and that is what you define in the provider.tf file, or you can create a single TF file, which is the configuration file. Now, one of the good thing about using environment variables is that you don't need to hard code values directly into your IAC templates. You can define placeholders, which are the variables that are replaced with actual values during deployment. Now, these values can be sourced from environment variables set in your deployment pipeline, configuration files, or secure storage mechanisms like Google Cloud Secret Manager. Now, in the Terraform configuration, even though we didn't do that, but we can do things like even define the database password. So it could have a variable like db_password, and we can reference it in our resource definitions. Now, during the deployment, we could simply pass the actual password value as an environment variable. Therefore, we can be assured that this is not going to be exposed in plain text in our code. So instead of putting the actual password, what we are simply doing is we are taking the environment variable and we are passing it through the configuration file in the Terraform environment. So now let's talk about the advantages and disadvantages, or pros and cons. So the first advantage is automation. Now, when you have IAC, or infrastructure as code, combined with environment variables, you can automate the provisioning and management of your infrastructure across different environments. The benefit that you will get is it will reduce the manual effort, minimize errors, and accelerate deployment cycles. You can create reusable modules or templates that will encapsulate common infrastructure patterns and configurations. Or you can create reusable modules or templates that encapsulate common infrastructure patterns and configurations. Therefore, what you achieve is common consistency and reduced duplication of effort. Let's now talk about a disadvantage. So there is going to be management of secrets. We will need to handle sensitive data like passwords and API keys. Now this requires extra care. We need to safeguard them properly. We need to implement secure mechanisms like Secret Manager to store and retrieve secrets during deployment. Now this will ensure that they are not exposed in the plain text. So instead of hard coding these values or passwords or API keys into the configuration, we would rather use environment variables and store them into Secret Manager and retrieve them during the deployment. Let's now talk about another advantage, which is version control. Let's say you created a configuration file, like the one we did in using Terraform to deploy resources in the GCP environment video. Now, once we create that configuration file, what we do, we check that into Git. So basically, we mark it as version 1.0. Let's say tomorrow we need to make certain configuration changes. So what we do is we check out that file from Git, we make edits, we check that file out, we make edits, and we check that file back into Git. Now, what we have done is we have created another version, and depending on the amount of edits or changes that we have applied in that configuration file. So for example, if it is a small change that we have made, it could be 1.1. And if there is a major set of changes that have been applied into that configuration file, then we might save it as version 2.0. So that versioning is always tracked. What is the benefit that we get? Now, tomorrow, if we want to go back to version 1.0, all we need to do is we need to check that out from Git, and we'll be able to use that same particular version. Let's now talk about another disadvantage. So there is going to be testing and validation. Now, it's going to be very critical for you to thoroughly test your IAC configurations to ensure they work as expected. Now, this can involve unit integration or end-to-end tests to validate the behavior of your infrastructure in different environments. Let's talk about an example. So you rolled out a virtual machine using Terraform and you named it as Terraform-VM. Now tomorrow, without consciously thinking, you made that change into your configuration file and you changed the name to Terraform-VM1. Now you go ahead and apply the change into the environment using Terraform. Now what happens? All of a sudden, your Terraform-VM, which existed earlier, will disappear. It will get destroyed or deleted because now the same set of configuration that you had earlier applied to deploy that particular virtual machine will wipe out because it is using the same set of configuration except the virtual machine name is different. So you need to be very cautious. You need to test out everything in your testing environment before you use those configuration files in the production environment. Let's now talk about another advantage, which is the consistent deployment. IAC ensures that your infrastructure is deployed consistently across environments. So the advantage that you get is there is a reduction in the risk of configuration drift. Again, the same example. You take that configuration file, you run that configuration file or you execute it using Terraform into 3 different environments, you will get the same consistent virtual machine or any other resource that you are deploying through that configuration file. It would be consistent with the same configuration. So basically what you are doing is you are rolling out 3 different resources with the exact same configuration. Now that is going to be the consistency, and with the consistency, what happens is there is going to be reduction in the manual errors. Remember, you are not manually deploying a virtual machine or a storage bucket. Now, if you do that, which is basically the manual configuration, what is going to happen is you might forget to figure out certain settings or certain configuration changes you might forget to make. So for example, if you're doing the manual configuration, you might fail to do the exact replica of configuration in all 3 different environments. So for example, you might do different network settings across 3 different environments. So the result of that rollout across 3 environments is going to be different. So that is where IAC helps you reduce the manual errors because the same configuration file will be running across all 3 different environments and it's going to be giving you the same consistent results. Let's now talk about another disadvantage, which is the debugging complexity. Now, if there are issues that happen to take place during the deployment or the runtime, debugging IAC configuration can be more challenging than in traditional manual approaches. Debugging requires an understanding of interactions between different resources and variables. So for example, the DB password or DB underscore password environment variable may not work as you intend it to work, or API key is not working as it was supposed to work. So the API configuration is failing. You will need to have certain amount of knowledge to be able to use IAC configuration files. Let's now talk about another strategy, which is Kubernetes namespaces. Now, within a single GKE or Google Kubernetes Engine cluster, you can create separate namespaces for each environment, which is development, staging, or production. Now, this allows you to logically isolate resources while still benefiting from the shared infrastructure. Now, think of a namespace as a virtual cluster within your GKE cluster. Each namespace has its own set of resources. For example, it has pods, services, and deployments. Now, these resources within a namespace are isolated from the resources within other namespaces. You can have unique resource names within a namespace, but can be duplicated across namespaces. So, for example, if there is certain pod with, let's say, name 1, the same name can exist in another namespace. Now, that is the unique thing about the resource naming convention within a particular namespace. And as far as traffic within the namespaces go, you can apply network policies to namespaces to control traffic flow between them. So there can be certain policies which can prevent the traffic from one namespace to another namespace. So you can isolate them completely using these particular policies. And Kubernetes also uses RBAC or role-based access control within the namespaces. You can easily define roles and permissions and grant these roles and permissions to users or service accounts for specific namespaces. Now, this ensures developers only have the access to their development environment, for example. Now, if you want developers to have access to only a particular namespace, you can use RBAC permissions and roles to give them access to only that particular namespace. Rest of the namespaces, they have denied access, which means they won't be able to access. Now let's talk about the advantages and disadvantages. Let's look at the first advantage, which is the Kubernetes native. If your applications are already containerized and running on JKE, using namespaces is a natural fit. You can use namespace and leverage Kubernetes' built-in isolation mechanisms and simplify environment management. By sharing the underlying GKE cluster infrastructure, you can also potentially reduce costs compared to running separate clusters for each environment. Let's now talk about a disadvantage which is not suitable for all workloads. If you have significant non-containerized workloads or require strong isolation at the infrastructure level, for example, separate VPCs, namespaces might not be a good choice in this scenario. Let's now talk about another advantage, which is resource isolation. Namespaces provide logical separation of resources, therefore preventing accidental interactions between different environments. For example, a misconfiguration in a development deployment will not affect your production environment. You can configure network policies to control traffic between namespaces, therefore creating secure and isolated communication channels. Let's look at another disadvantage, which is limited physical isolation. While namespaces provide logical isolation, they share the same underlying cluster resources. So, for example, they share the same nodes, they share the same network. This means that a major issue with cluster can potentially impact all the namespaces. So, for example, if there are nodes that fail within that particular cluster, it will impact all the namespaces that are running within that particular cluster. Let's now talk about another advantage, which is RBAC or role-based access control integration. Namespaces work seamlessly with Kubernetes RBAC. Now, this will make your life easy to manage access control and ensure that different teams or users have only access to the environment they need. So again, the principle of least privilege is also applied here. You will be granted access only to the level where you need to perform your work, but any extra access or permissions will not be granted. Let's now look at another disadvantage, which is increased complexity. Managing multiple namespaces within a single cluster can add some complexity. Now, especially when you talk about the networking, RBAC configuration, or resource allocation, you need to carefully manage these namespaces. And if that doesn't happen, there is going to be resource contention that can occur between namespaces. There could be a possibility that one namespace starts consuming more resources within that particular cluster, so which means there is going to be a resource shortage for the rest of the namespaces. Let's now talk about choosing the right strategy to manage multiple environments. So first of all, it all depends on your environment. It all depends on your organization policies. It all depends on your specific requirements for specific projects or specific scenarios. So there cannot be one single strategy that will fit in all scenarios. So let's look at some of the possible scenarios here. So there is scale of your organization. Now, larger organization might lean towards separate projects because they want strict isolation. They will have tons of resources. They will have hundreds of virtual machines, storage buckets, networks, VPCs. They might want certain set of isolation amongst all. If there is a small organization that has only 10 people and they are in the Google Cloud, now in this scenario, if the organization is small, they might even just prefer using labeling rather than creating separate projects. Then there is complexity of infrastructure. Now, if you have very complex network requirements or you have many shared resources, shared VPC might be a better fit than other strategies. So you may not need separate projects. Shared VPC might be a better choice in that scenario if you need to share resources. Then there is IAC adoption. Now, leveraging environment variable is a natural extension for multi-environment management. Now, with the IAC, we talked about if you use environment variables, there are certain benefits you get. Like, for example, you don't need to hard code your credentials or API keys. Just as an example, you can fetch them from Google Secret Manager at the time of the deployment. Well, just to quickly recap, in this particular topic, we spoke about different strategies for managing multiple environments. We talked about separate projects. We talked about shared virtual private cloud or VPC with project-based isolation. We talked about resource labeling and naming convention. We also talked about IAC with environment variables. And finally, towards the end, we did talk about Kubernetes namespaces. And then at the very end, we did talk about choosing the right strategy to manage multiple environments. So, for example, there might be a possibility that a smaller organization may not go for separate projects, but may work with labeling. That would suffice for them. Another example could be that if you have a lot of resources to shared VPC might be a better choice than separate projects. In this topic, you would learn to create isolated Google Kubernetes engine environments automatically for each new feature branch in your GCP project, which is going to be SKS 001 using Terraform and Cloud Build. In short, we are going to be using two different products, which is going to be Terraform as well as Cloud Build. Now, there are certain prerequisites that you have to meet. So first one is you would need to have a active GCP project. In this case, it's going to be SKS 001. And you would also need to have the GKE and Cloud Build APIs enabled. You would need to have the Terraform installed. And this can be done on your local machine. For us, it's already been done. And then you would need to have a Git repository. Basically, you would need to have your application code hosted in Git repository. It could be GitHub, GitLab, whichever, but we have used GitHub in this case. And then you would also need a GCS bucket. Basically, you would need to create a cloud storage bucket. And in this case, we have created and we have named it as SKS-Terraform. Now, what are the steps that you would need to do? So in this case, what we have done is we have created a local directory or a local folder named an-app. So basically an app. And what we have done other than this is in this, we have created a subdirectory called Terraform. Now, Terraform need to basically have the files created within itself. So these are going to be some Terraform related files. And now let's go ahead and see what is going to happen. So once we have these files, so there is going to be a cloudbuild.yml file that is going to be outside in the root directory. Now, in the Terraform subdirectory, you would need to have main.tf, variables.tf, and versions.tf. These are the three configuration files you need to have. And basically, these are Terraform configuration files. And if these files are unavailable, then your Terraform does not work. Basically, it would look for these configuration files. Now, going back to the main directory, we are going to switch over and we're going to see what is the configuration that is mentioned in .yml file. So there is cloning of directory, which it is going to do, then fetching the specific feature branch, checking out the feature branch, and then it's going to run various Terraform commands like init and then plan. And then moving on to main.tf file, it's going to have a lot of configuration, which is the provider, project, region. Then there is going to be variable and resources, etc. So all this is going to be mentioned. And it's going to also have the SKS-cluster, which is the Kubernetes cluster that we spoke about earlier. So that is going to be also mentioned here. And once you have defined all these settings, and you don't have to have exact same configuration, you can define your own configuration. Let's move over to variable.tf, and basically it defines the region, etc. Now what we are going to do is we're going to move over to Cloud Shell, and then we are going to basically execute some commands. But before we do that, we are going to just go ahead and create a new file called test1. Now, for me to be able to execute Cloud Build, to execute a trigger automatically, I need to add that test1 file, or test1.txt file actually. So I made an error over there. So I'm going to just go ahead and clear the window and add .txt at the end. So I have added that. Now, once I do that, after that, I need to commit this file, but I need to have the comment that needs to be added for that particular commit. Now, without this, it will not accept that file. So I'm just going to say a new sample file. Now, file has been committed, and now I need to push this to the Git repository on GitHub. And command is git push and the new feature branch. So this is successfully done. Now we quickly move over to Cloud Build. And if I refresh this window, notice that the trigger is automatically executed. Now, in this particular topic, what we talked about is how to configure a feature environment with Terraform and Cloud Build. And we saw the basic configuration and the process how to do it. So basically, you need to create the feature branch on GitHub, and then you need to run certain commands. And there is some Cloud Build configuration, which is the cloudbuild.yml file that needs to be present on the root of local directory. And other than this, you need to have some of the Terraform files. Let's now talk about configuration management. Configuration management is the practice of maintaining consistent and accurate settings, parameters, and configurations for your infrastructure and applications throughout their lifecycle. It ensures that your systems are deployed and operate as intended, therefore minimizing errors and ensuring repeatability. Let's now talk about the key aspects of configuration management. So there are different aspects. So there is IAC, there is detection and remediation of configuration drift, there is management of secrets, there is policy enforcement, and then there is continuous configuration automation, or CCA. So let's look at each one of them. Let's first talk about IAC, or infrastructure as code. Cloud Deployment Manager, which is GCP's native IAC tool, allows you to define your infrastructure resources, which could be your virtual machines, networks, databases, storage systems, in declarative templates, which could be defined in YML or Python. Now, these templates can be versioned, tested, and deployed repeatedly, therefore ensuring consistency and reducing manual errors. So you define a script, you can use it to deploy n number of systems. The same system can be deployed n number of times. So there is going to be always the same deployment that is going to be there, which means if the first time it got deployed successfully, the rest 9 times it's also going to get deployed in the same fashion. So there is going to be absolutely no changes in the configuration. So that is very important. So another tool that you can use is Terraform. It is a popular third-party IAC tool that integrates well with GCP. Terraform's declarative language allows you to define complex infrastructure configurations and manage their lifecycle across multiple providers. In the topic, using Terraform to deploy resources in GCP, we saw how we can deploy a resource. In that particular topic, we did deploy a virtual machine using Terraform. Now, if we use that particular script or the configuration file, we can deploy that same virtual machine hundreds of times and it's going to get deployed with the same configuration. Then there is detection and remediation of configuration drift. So there is config connector. Now this tool helps you manage GCP resources directly from Kubernetes, therefore ensuring consistency between Kubernetes configurations and the actual state of your GCP resources. You also have cloud asset inventory. Now, this is a comprehensive inventory of your GCP assets and their configurations. Now, it makes it easier for you to identify and address drift or unauthorized changes. Then there is management of secrets. In the GCP environment, you have Secret Manager, which is a centralized service for securely storing and managing sensitive data like API keys, passwords, and certificates. It integrates well with other GCP services, and it also helps you avoid hard coding secrets into your application code and configuration files. So, for example, in the Terraform configuration file, you don't have to put down the hard coded passwords or API keys. In one of the previous topics in this particular course, we did talk about how to use environment variables to use these secrets from Secret Manager. Then there is policy enforcement. So there is policy controller. This component of Anthos config management helps you enforce organizational policies on your GKE cluster. You can define policies that restrict resource creation, enforce labeling conventions, or prevent the use of deprecated APIs. Then there is config sync. Now, this tool synchronizes your desired Kubernetes configurations across multiple clusters, therefore ensuring consistency and compliance with your policies. Let's now talk about continuous configuration automation or CCA. You have Cloud Build. Now, this is GCP's CI/CD platform that can be used to automate configuration changes as part of your deployment pipeline. This ensures that your configurations are updated consistently and automatically alongside your code changes. Let's now talk about the importance of configuration management in GCP. So there are various important factors that come into the picture when you talk about configuration management in GCP. So let's talk about some of these. So there is consistency. Configuration management ensures uniformity across your cloud environments, therefore minimizing errors caused by manual misconfigurations or inconsistencies between development, testing, and production. Then there is automation. By automating provisioning and updates, you can accelerate deployments, therefore making them more reliable and reducing the risk of human error. Then there is traceability. Configuration management tools keep a detailed history of configuration changes, therefore enabling you to roll back to previous states if issue arise and gain insights into who made specific modifications. And this could be done through version controlling systems like Git. Then there is scalability. Configuration management simplifies managing large and complex infrastructure, therefore making it easier to scale your resources up or down as needed without introducing inconsistencies. Then there is security and compliance. Configuration management helps you enforce security policies and configurations consistently across your infrastructure, therefore reducing vulnerabilities and ensuring adherence to regulatory compliance. Let's now talk about the best practices for configuration management in GCP. Now, to get the most out of configuration management in GCP, you have to follow certain best practices. So we are going to talk about those. So the first one is embracing IAC or infrastructure as code. You should use tools like Deployment Manager, which is GCP's native IAC tool, or Terraform to manage IAC, therefore enabling versioning, automation, and streamlined collaboration. You should also modularize your code. You should break down your infrastructure into smaller, reusable modules or components. This promotes maintainability, and reusability, therefore making it easier to manage and update your infrastructure over time. Then there is version control everything. You should store your ISE code, configuration files, and scripts in a version control system like Git to track changes and enable collaboration. This would also help you facilitate rollback when needed. Now, when you store your files into Git, anybody who checks out, first of all, they need to have the permission on Git to access those files. Now, if they have permissions, if they make any kind of modifications to any of these files, it gets tracked. Then the next point is you should test thoroughly. You need to implement automated testing to validate your infrastructure configurations before deploying them into production. This helps catch errors early and ensures that your infrastructure works as expected. The next one is automate deployment. You should integrate your configuration management tools with CI/CD pipelines to automate the deployment and management of your infrastructure changes. This reduces manual effort, improves reliability, and speeds up delivery. Then there is monitor for drift. You should regularly monitor your infrastructure for configuration drifts. So these could be deviations from the desired state of your infrastructure. You should use tools like GCP's config validator or other monitoring solutions to detect and promptly rectify drift. Let's quickly recap what we talked about in this particular topic. We talked about configuration management. We talked about the key aspects of configuration management. So there were aspects like ISE, detection and remediation of configuration drift, management of secrets, policy enforcement, and continuous configuration automation. Then we also talked about the importance of configuration management in GCP. So there is consistency, automation, traceability, scalability, and then security and compliance. And finally, towards the end, we talked about the best practices for configuration management in GCP, in which we talked about embracing ISE, modularizing your code, version controlling everything, testing thoroughly, automating deployment, and monitoring for drift. Integration of third-party CI/CD tools. Now, in this particular topic, what we are going to do is we are going to work with a GitHub repository and we are going to automatically trigger builds in Jenkins as well as Cloud Build. So basically, the GitHub repository is going to be centralized, and as and when you do an update, which we will do, it's going to automatically trigger a build at both the ends. One is going to be in Jenkins, another one is going to be in Cloud Build. Now, there is one thing to watch out. The delay is going to happen when you're talking about Jenkins. So it might take a few minutes for that build to get executed. And the reason is that particular Jenkins installation that we have is running in a VM instance called jenkins.vm. And when we are talking about Cloud Build, it is automatically integrated into the cloud environment. So there is hardly any delay. It's probably a few milliseconds build gets triggered as soon as a change is detected in the GitHub repository. Now, there are certain things that you need to do. So you need to have storage bucket, and that storage bucket, you can name it whatever. So I have named it SKS001 my website. Now, this one has the source code inside it. So I have these files that are stored here. So there is index.html, and then there are some styles related files. These are the CSS files. If you are going to be using a service account when you are building your trigger, then what you need to ensure is you need to give storage object admin role for that particular service account. If you don't have that role, you're going to have errors that are going to be popping up, and these errors are going to be permission related. So now, once you have done that, you also need to have another level of role. So we are going to just get inside this bucket, and on permissions tab, then we are going to see there is this all users who need to have the storage object viewer permissions. Since we are not using the service account, so we have not defined that. But yes, all users with storage object viewer permission is what we have defined. Now, let's move to the next place where we are going to be moving into Jenkins. Now with Jenkins, how do you access this particular instance? You can click here. The virtual machine must be running though, otherwise you will not be able to get inside it. So once you do that, you can basically scroll down and you can get your password. The default account is admin and the password is already provided on this page, and for security reason I'm not going to show you that particular password. But what you can do is you can obtain the IP address from this particular page, and then you can connect. So I have already connected to this particular website which is being run on that virtual machine. Now there are certain configurations that you would need to do. So first of all, you would need to get into dashboard, which should be your default landing page. Once you get inside, then you need to go to manage Jenkins, and once you are here, what you need to do is get into plugins. There you would need to install the Google Cloud Build plugin, and I have already done that, and therefore we don't need to do that again. Let me just quickly search for that. There you go, Google Cloud Build plugin, that is already there and it's activated. So now once you have done this, you need to basically create a service account in GCP, and you can do that in the identity and access management on GCP. Once you create the service account, and let's just go ahead and look at it. So I'm going to just go ahead and go to IAM. So I'm going to just go to Google Cloud. From here, I'm going to go to IAM admin, and you can basically create a service account. So here I have created that service account and let it just roll. So I'll show you what that service account is. And this is called Jenkins Cloud Build. That is the service account. So if I click on this pencil icon, which is edit, then the permission that I've assigned is Cloud Build Service Account. So I'm going to go ahead and cancel this. And we also need the JSON key for this particular account. And to be able to do that, I would need to basically, so when you're defining the service account or you're creating the service account, you have the option to generate the key and take the JSON file. That JSON file will get downloaded onto your local system, and that is what you would need in Jenkins. And once you go back to Jenkins in the dashboard, or rather manage Jenkins, what you would need to do is add credentials. So you would need to come down here, credentials, and then you would need to click on this global domain. And once you do that, you would need to add that particular JSON file. And so you basically click on add credentials, and then you would need to basically select. So instead of this, you would need to select secret file, and then you would need to select this file, JSON key that you downloaded. And once you add that file, you just need to go ahead and click on create, and that is how you would be able to add that particular credential, and that has been already added. So now the next thing we would need to do is configure system. So we need to go to manage Jenkins again, which we already are, and then we just basically need to click on system, and we would need to configure it. So there are multiple options. If you have Google Cloud Build option enabled here, or it appears, then you can use that. Otherwise, you need to have the credentials binding plugin, and that would automatically be available. So that is what you need to add here. And then once you configure this, then you would need to basically update your profile and move out. So I'm just going to go ahead and go back, because I don't have not made any changes. So I'm not going to go ahead and do anything. And once I'm done this, now let's hop over to the Google Cloud Build. So I have this trigger, which is called, let me just go back and look at the trigger. So once this page loads, let me just go to triggers. So this is called the feature trigger. And there is another one which is called Jenkins. So let's look at the history quickly. All right. So what we are going to do is we are going to basically look at this Jenkins trigger. You would need to define a trigger, so you can name it whatever you want. So I've named it Jenkins. And now this is second gen. I have given the repository name. The branch is main. And then the cloud build it's in the first app repository on GitHub, and I have not defined a service account. Now move over to the GitHub repository, and this is what my repository is, first app. Now what we are going to do is we are going to look at the cloud build.yml file, and this is the cloud build.yml file. All right, so this is basically sks-my-website. So this is referring to that, and then it is also basically going to go ahead and utilize this cache headers for browser caching. Now I'm going to go back, and what I need to do is basically, I have not made any changes to this, so I'm going to go ahead and cancel it. Now, if I make any change to my repository, for example, let's go to the root of this repository. Let's create a file, or let's rather modify an old file. So I'm going to take this new file, edit it, and just go ahead and delete these lines. I'm going to commit changes, commit change, and I'm going to quickly come back to history. That Jenkins trigger should have triggered by now. All right, so there you go. Jenkins triggers. So there are 3 triggers that are actually referring to first app, and that is the reason you see 3 triggers, but this Jenkins is also triggered. And now if I go back to dashboard on Jenkins, and if I look at the build history, all right, so it has not updated. So what we are going to do is we are going to just wait for some time, and it should show us cloud build pipeline 11 should be visible. So we'll have to just wait. So I'm going to just go ahead and refresh the page to see if it is able to catch that. Because it's running in a separate instance, it might be due to latency why it takes a little bit of time for that build to appear. So right now there is not even a build queue, so which means the build has not been generated here. And usually it takes a few minutes after cloud build to generate that particular build over here. So we'll have to just wait for a couple of minutes and then see what happens. All right, so finally that change has appeared. Now new build has been generated. So if I just go ahead and click on this build, what it is going to do is it's going to tell me, okay, last build 29 seconds ago, stable, successful build and completed. So if I go back to changes, now it says update new file. So I'm going to just click on status, and again it shows us the status that is there. So now what this means is, in total, you have created a GitHub repository, you have configured cloud build with a trigger, and you have also created a trigger in Jenkins. Now, as and when you do your updates in the GitHub repository, what it is going to do is it's going to trigger a build on both the ends. And then you can basically, whatever your purpose is to create that build, maybe push it to production or push it to staging and all that, you can define it like that and use it. Now, just to quickly recap, in this particular topic, we talked about configuring storage for generating the cloud build. And we also looked at some of the configuration in Jenkins. And then we did an update in our GitHub repository, which automatically triggered a build in Jenkins as well as in cloud build. Let's now talk about the security practices for CI/CD pipelines. So we are going to talk about the security practices for source code, build environments, build artifacts, and deployment process. So let's start with the source code. So there is version control. You should always use version control system like Git to track your code changes, review commits, and maintain a complete history of auditing. And it can also be used for rollback purposes. So for example, if one script has caused an error, if you have previous versions of that script, you can always go back and roll back your changes. Then there is access control. You should enforce strict access control on your VCS or version control system repositories. You should ensure only authorized developers have right access to prevent unauthorized modifications. Now, even if somebody makes accidental changes, one of the developers who has access, you will be able to track that because you will be able to figure out who made the changes, when the change was made, and what change was made. Let's now talk about the build environment. You should use separate, isolated build environments for each project or stage of your CI/CD pipelines to prevent cross-contamination and limit the impact of any security breaches. Cloud builds ephemeral build instances are a good option for this purpose. Then there is ephemeral environment. You can create and destroy build environments dynamically for each build, therefore reducing the window of opportunity for attacks and minimizing the risk of configuration drift. Let's now talk about the build artifacts. So there is artifact registry. You can utilize GCP's artifact registry to store and manage your build artifacts. For example, container images, compiled binaries, and you should do it securely. Then there is scanning for vulnerabilities. You should integrate scanning tools such as Google's container analysis or third-party solutions to detect vulnerabilities in your artifacts before they are deployed. Now, this needs to be done before the artifact is deployed, because if there is a contaminated or malware infected artifact that gets deployed, it can take down the entire environment. So you have to do it before you deploy the artifact. Then there is image signing. You should digitally sign your container images to ensure their authenticity and integrity. Let's now talk about the deployment process. So there is the principle of least privilege. You should employ this principle of least privilege by granting service accounts and build tools only the minimum permissions necessary to perform their functions. So, for example, if you need to deploy a virtual machine, you need to create a service account, and I'm talking about the Terraform. Now, that service account needs to have certain level of privileges to be able to deploy that particular virtual machine. So, you should give that level of permission to the service account. Then there is binary authorization. You should enforce deployment policies for container images, therefore ensuring that only trusted and validated images can be deployed to your GKE clusters. Then there are security groups and firewall rules. You should control network access to your deployment environments by using security groups and firewall rules, therefore allowing only necessary traffic. Let's move to the next slide and look at some more security practices for CI/CD pipelines. Now, in continuation from the previous slide, let's look at some more security practices for CI/CD pipelines. You should also secure your secrets. Now, there is a secret manager that we talked about. You should never hard code any secret. So it could be your API keys or passwords or certificates into your CI/CD configuration files. You should store them securely in Google Cloud Secret Manager and reference them indirectly in your pipeline steps. So for example, you can use Terraform environment variables to access them. So which means that your passwords or API keys would never be stored in clear text in your configuration file. There will only be the environment variable which will fetch these required API keys or the passwords from the secret manager. Then there is encryption. You should encrypt your data at rest and in transit to protect sensitive information from unauthorized access. And this is pretty much known to everybody that encryption should be used. If you are storing data and if it is sensitive data, then you must encrypt that stored data. Now, if there is data in transit, you should ensure that there is encryption deployed so that the data is not traveling or transmitting in clear text. Then there is continuous monitoring and logging. You should enable comprehensive logging and monitoring of your CI/CD pipeline. You should track build logs, deployment logs, and system metrics to detect anomalies and troubleshoot issues. Then there is Security Command Center. Now, you can use the Security Command Center to aggregate and analyze security data from your pipelines, which provides insights into potential vulnerabilities and threats. Then there is IAC security. We talked about version control earlier. You need to implement version control for your IAC configurations and application code. This will help you track changes it will help you collaborate with the other developers, and it will also help you roll back to any previous state if required. Then there is code review. You should implement code review processes for all IAC changes to ensure they adhere to security best practices and coding standards. So, for example, there are certain coding standards that you should follow. Now, these are usually known as secure coding standards. Your organization, if they have implemented it, you should map your standards against the code that you have written, and you would be able to figure out whether that code complies with the security standards. Then there is static analysis. You should use IAC scanning tools to check for security misconfigurations in your Terraform or deployment manager files. Then there is regular updates and patching. Now there are software updates. You would be using certain CI/CD tools, operating systems, and dependencies. You need to ensure that they are updated to the latest security patches. If you are using any older version, it may have vulnerabilities. Therefore, you need to ensure that you use the latest version which has been securely patched up. Then there is security tooling. You should regularly update and scan your environment with vulnerability scanning tools to detect and address any new security threats. Now, just to quickly recap, in this particular topic, we talked about security practices for CI/CD pipeline. We talked about securing your source code, your build environment, build artifacts, and we also talked about securing the deployment process. And then we talked about securing your secrets, continuous monitoring and logging, IAC security, and finally, regularly updating and patching your tools. In this topic, what we are going to do is we are going to talk about a case study for multi-cloud CI/CD setup. We are going to talk about a hypothetical organization, which is XYZ Corporation, which is a leading provider of financial services. Now, they are facing a particular situation. XYZ Corporation works out of European Union and Singapore. Now, there are two different laws that come into practice when they are dealing with both the regions. So for EU, there is General Data Protection Regulation, which is GDPR, and then there is Singapore's Personal Data Protection Act, or PDPA. Now, these are basically data sovereignty laws that need to be complied with, and that is where XYZ Corporation is facing challenges. Now, these regulations mandate that the customer data to be stored and processed within specific geographic boundaries. Now, on top of this, XYZ Corporation is using GCP, which is the Google Cloud Platform, and they are also using Amazon Web Services, or AWS. Now, they are using the GCP's data analytic capabilities, which is ideal for risk modeling, and they are also using AWS's extensive machine learning services, which are perfect for fraud detection. However, the problem XYZ Corporation is facing is that they have to manage separate CI/CD pipelines for each of these cloud providers, and this is becoming a logistical nightmare for them. So let's move to the next slide and see how XYZ Corporation is going to deal with this particular situation. When you talk about the solution to overcome the challenges that XYZ Corporation is facing, they build a unified multi-cloud CI/CD platform that would streamline development and deployment while ensuring regulatory compliance. Now, this is going to be key because they have to comply with GDPR and PDPA. So, therefore, it is necessary that whatever solution they apply or implement, they must comply with GDPR and PDPA, which is Singapore's law. What does XYZ Corporation do? They go ahead and implement IAC using Terraform. So XYZ goes ahead and implements IAC with Terraform. So how does Terraform help in this particular scenario? They use Terraform to define their infrastructure across both GCP and AWS. Terraform's provider model allows them to write code that could provision resources on either platform by using consistent syntax. This means that a single set of configuration files can manage virtual machine storage, network, database in both the clouds, which means you have the consistent pipelines across both the cloud platforms. And they also get the benefit of version control and compliance. All Terraform configurations were stored in version controlled repository, therefore allowing them to easily track changes and ensure auditability, which is a key requirement for financial institution. And as we talked about in the beginning of the case study, XYZ Corporation is a leading provider of financial services, and therefore auditability is one of the key requirement with the financial firms, and that is where they are going to be able to track the changes and bring in auditability. Then XYZ Corporation also did a multi-cloud orchestration with Jenkins. Now, Jenkins, which is an open source automation server, was chosen as the orchestrator of the CI/CD symphony. It could trigger builds, run tests, and oversee deployments on both GCP and AWS. So XYZ Corporation also embraced pipeline as code principle, defining their CI/CD workflows in Jenkins files, and that were stored along with the application code. Now, this helped them ensure transparency, versioning, and the ability to replicate pipelines easily. Then comes the next point, which is the cloud specific fine tuning. That is where they brought in two different products. One is the deployment manager, another one is cloud formation. With the deployment manager, for GCP specific resources like BigQuery datasets or cloud functions, they use deployment manager templates to ensure compliance with EU GDPR regulations. Now, on AWS, they used CloudFormation. Now, CloudFormation templates handled region specific deployments to maintain adherence to PDPA in Singapore. Then the next point is security and governance, which was basically integrated. So they implemented RBAC, which is role based access control. Both GCP and AWS identity and access management systems role were integrated into pipelines, therefore ensuring developers only had access to the resources and actions they needed to minimize risks. Now, both GCP and AWS have identity and access management systems, so it was easy for them to basically apply rollback access control or RBAC. Then there was data encryption. Data at rest and data in transit were encrypted with cloud provider specific tools, therefore safeguarding sensitive financial information. Then there was continuous monitoring, which is a key thing when you're talking about CI/CD pipelines, because you want to know what is happening with your CI/CD pipeline, and that could only happen when you have continuous monitoring. Now, there were logs from Jenkins, Terraforms, and cloud provider services that were centralized for real-time monitoring and auditing. So, what could be the other types of logs which are from the cloud provider services? We have IAM, we have cloud formation, deployment manager. Now, these were cloud provider specific services, and we can get the log that can be centralized for real-time monitoring and auditing. Now, just to quickly recap in this particular case study, we talked about a multi-cloud CI/CD setup where a corporation named XYZ had to comply with GDPR and PDPA, which is a law from Singapore, keeping the data sovereignty in mind. So they went ahead and implemented solutions like IAC with Terraform, multi-cloud orchestration with Jenkins, cloud-specific fine-tuning, and security and governance integration. Troubleshooting common CI/CD pipeline issues in GCP. Now, in this particular topic, what we are going to talk about is certain errors that may pop up when you are running a pipeline. And to look at some errors, what we are going to do is we are going to navigate to history and then look at some of the common errors. And it is not that these are the only errors that will exist. There could be an n number of errors. But we are going to talk about a couple of basic issues that might just happen to be there because of certain reasons. So, for example, if we look at the first one, now, so if I click on this, what it says is your build failed to run because file cloud build.yml not found. Now, what happens is in the Git repository, if you don't have this file, you're going to face this error. And this is happening because what I had done was cloud build. I had just suffixed it with a dash, and that is the reason this particular error got generated. Now, if I go back to history, another common error is that you might find certain unknown. Now, what it says is, and this is supposed to be trigger name. And why is there a exclamation and unknown written? Because whatever the trigger was, I deleted those, and due to that, this particular unknown error is being shown here. And of course, there was a reason why this build failed, and we are not going to talk about that. And what we are main focused on is why there is unknown. So any trigger that got deleted, you will see this particular exclamation mark and unknown mentioned here. And then another thing that I want to talk about is this, and it is very critical when you're dealing with, all right, so this is also the cloud build error, and we need to find another error which is related to formatting. Now, when you're dealing with YML files, you need to ensure that the formatting is absolutely correct. Now, look at this. Your build failed to run. Failed unmarshalling build config cloud build.yml did not find expected dash indicator. Now, that indicator is there. If I go back to this particular file, this indicator is very much there, but there is probably a space here and there where it got missed out, and YML needs to be perfectly designed as far as formatting goes. If there is any blank space or anything like that, it's going to throw an error. So these were three common errors that we talked about. So one was the cloud build file that needs to exist. Second is the unknown error. If you delete a trigger, this is what is going to happen. And even if you have successful builds, you're going to still see that error based on the deleted trigger. And the third one was basically that the formatting related error where a dash has probably, it's not in its place. So that error got generated. Now, there could be 100 other errors which could be there. And for example, let me see if I can just find another error. And now this is a Docker related error. So it's basically Docker related error, and you would need to have a proper Docker file with proper syntax, formatting and everything. And it says Docker parse error line 1. So from requires either 1 or 3 arguments. So that is where error was encountered, and you would have to basically investigate why this particular error has happened. So for example, I do have a Docker file here, and it has just one basic, echo command that is there. That is what needs to be executed. So you would have to basically investigate these errors very carefully and figure out why they are happening. Now, just to quickly recap in this particular topic, what we talked about was the exclamation related error, cloud build.yml file missing, and third one was the formatting error. And then we also briefly talked about the error from a Docker file. So for example, it says that it requires 1 or 3 arguments. So these were some of the issues that we talked about. And of course, once again, reiterating, there could be 100 other issues that you might come up with. You would have to do some research on the whatever your favorite search engine is, maybe Google or any other search engine. Just find out, what these errors are. You may also want to check the documentation for cloud build if they have any information related to that. Now, in this course, we went through various topics, and we are just going to have a quick look at what these topics were. So we talked about CI/CD, which is continuous integration and continuous deployment. We talked about its components and the best practices for security. Then we also looked at setting up CI with cloud build, and then benefits of using cloud deploy for continuous deployment or CD. Then we talked about third-party CI/CD tooling. And then towards the end of the course, we talked about strategies for managing multiple environments in GCP and configuration management in GCP. So what's coming up next? It is a course on building and implementing CI/CD pipelines for a service.